Hello, and welcome to the full course session on Basics of Electric Vehicle Simulations using ANSYS, your gateway to mastering simulations in the rapidly evolving electric vehicle industry. This is a certified course session, so make sure to fill out the form in the description after completing the session to claim your certificate. You can proudly share your achievement on LinkedIn to showcase your new skills. At Skill-Lync, we're committed to providing industry-relevant advanced engineering courses. We partner with industry experts to offer top-notch training that equips you with the skills needed to excel in your engineering career. Don't forget to subscribe to our channel for more insightful tutorials and updates on engineering tools and techniques. Hit the subscribe button and stay tuned. Here's a brief overview of what we'll cover in this training video. In the first chapter, we'll introduce you to the fundamentals of electric vehicles and their importance in today's world. You will learn why electric vehicles are becoming more popular, what the key components of electric vehicles are, how these components are engineered, the necessity of simulations, and real-world use cases of EV simulations. In the second chapter, we'll explore the reasons for the global shift toward electric vehicles. We'll compare electric vehicles with internal combustion engine vehicles from the perspectives of emissions and performance. You will also learn how energy for propulsion is generated in EVs compared to ICE vehicles, as well as key emissions and how they are regulated. In the third chapter, we'll take a closer look at the vehicle architecture of electric vehicles and explain how it differs from the architecture of internal combustion engine vehicles. You'll gain insights into the functions of key EV components, the common configurations of battery packs, and the fundamentals of electrical engineering as they apply to electric vehicles. In the fourth chapter, we'll focus on the fundamentals of batteries for EV applications. We'll discuss how a battery works, how to choose materials for the cathode and anode, the key performance criteria of batteries, temperature sensitivity, sources of heat generation in batteries, and how to design a cooling system for improved battery efficiency. In the fifth chapter, we'll move on to heat transfer modeling for batteries. You will learn how to analytically measure temperature distribution inside a battery, perform an energy balance on a control volume, derive a governing equation, and arrive at an analytical solution. We'll also discuss the drawbacks of the analytical method and explore how to overcome these limitations. In the sixth chapter, we'll cover the simulation of a battery thermal management system using ANSYS Fluent. We'll guide you through the process of setting up a case in ANSYS Fluent, defining the BTMS problem, boundary conditions and initial conditions, setting up material properties, and activating key physical models. We'll finish the chapter by walking you through the case setup and discussing the results. In the seventh chapter, we'll dive into motor power estimation and motor drive analysis. You'll learn how to estimate motor power for on-road electric vehicles, understand the forces acting on vehicles such as rolling resistance and aerodynamic drag, and perform quick calculations in Excel. Additionally, we'll discuss the classification of electric motors and the factors that influence the choice of an EV motor. In the eighth chapter, we'll explore motor sizing fundamentals. We'll focus on the operation and construction of brushed DC and BLDC motors, introduce the fundamental equations for permanent magnet synchronous machine sizing, and discuss the basics of power converter operation. We'll also cover the analytical design of PMSM using ANSYS RMxprt and Maxwell. In the ninth chapter, we'll turn to external aerodynamics and discuss the basics of fluid dynamics. You'll learn about the two most fundamental forces in aerodynamics and how to perform external flow simulations using ANSYS Fluent. In the final chapter, we'll cover the DC to DC converter in an EV power system. You will learn about the propulsion and auxiliary systems of an electric vehicle, the types of DC to DC converters used in EV applications, circuit simulations of power converters, and magnetic analysis using ANSYS tools. We will also explore the thermal considerations of PCBs using ANSYS IcePack. Thank you for joining us. We're excited to have you on this learning journey. Make sure to subscribe for more updates and detailed tutorials. Complete the training, earn your certificate, and share your achievement on LinkedIn. Let's get started with the basics of electric vehicle simulations using ANSYS.
Hey guys, hope you're all doing good and welcome to the course on Basics of Electric Vehicle Simulation Part 1. This is a course that's specifically designed to teach you the fundamentals of various simulation techniques that are used to engineer various parts of an electric vehicle. Now, an electric vehicle has a lot of mission critical parts, and that is why this is just part 1. In part 1, we will be primarily focusing upon the battery pack. In this module, you will essentially learn about fundamentals of different battery chemistries, how electrochemical potential is used to determine the cell voltage. Then we will primarily be focusing upon the various thermal issues that are associated with large battery packs. And then finally, we will teach you how you can actually simulate the heating and cooling processes of battery packs. Now, before doing the simulation part, we will also introduce you to analytical calculations. Alright, so the course is structured in a fairly simple way. You will be watching a bunch of videos and you can basically watch the videos at your own pace. Now, after each video, there might be certain challenges that you will have to attempt, and you will be working on a couple of projects. Now, the way the course works is fairly simple. You will be watching a bunch of videos and you will be attempting several assignments and projects. Alright, so let's get started with the curriculum and discuss in detail what you will be learning in this course. Alright, so before we take a look at the syllabus, I kind of wanted to explain key learning aids that have been introduced. Now, since this is a fundamental course, it's very important to understand what are the topics that are covered and what are the topics that will not be covered. In addition to that, since it's a fundamental course, we kind of touch upon a lot of points. Now, certain points have to be remembered. Right, so you will basically see this particular symbol against concepts that you definitely have to remember. Now, given the complexity of the subject, it's a given that certain concepts cannot be discussed in detail. So here we will basically use a black box approach. We will essentially take a look at things that we care about and we will not go into excessive detail. Alright, so by the end of this course, you will be able to understand the need for electric vehicles. Though this is an easy point to understand, we actually present logical arguments for why electric vehicles and especially hybrid electric vehicles are a good starting point. Now, once we have done that, we will teach you different vehicle architectures with respect to hybrid electric vehicles and battery electric vehicles, and we will primarily compare and contrast these vehicle architectures in terms of the different components that are found and the different functionalities that they support. Once we have done that, we will help you understand the functional requirements of key components of an electric vehicle. And then, as I mentioned in the start, we will be discussing the fundamentals of battery chemistry, and we will slowly guide you and help you understand the need for a battery thermal management system. So once we have helped you understand that, we will be teaching you how to derive an analytical model to estimate the steady state temperature distribution inside a battery. Once we have done that, we will also discuss the drawbacks of analytical methods, which will help me lay the foundation of computational fluid dynamics. Once we have done that, you will be learning the fundamentals of ANSYS Fluent and you will be simulating a simple battery thermal management system. Now, who will benefit from this course? If you are an undergraduate student majoring in mechanical engineering, automotive engineering, aerospace engineering, or even electrical engineering and are interested in learning about electric vehicles, then you should strongly consider taking this course. If you are a graduate student who is venturing into the EV domain, then this course can add a lot of value. Now, for professionals who have no background in electric vehicles and computational fluid dynamics, this course is going to be extremely useful because this course is short and it covers a lot of topics at a shallow level. Now, for professionals who are already working in the EV domain, you might find bits and pieces here and there that you might find useful, but overall the content is going to be basic. Now, what is covered in this video? In this video, we will be talking about the course curriculum. We will explain to you why electric vehicles are the need of the hour. Now here primarily we will be talking about hybrid electric vehicles as they are a great trade-off between IC engines and pure electric vehicles. Once we have done that, we will talk about key components, their functions and their engineering aspects of an electric vehicle. Now keep in mind that we will not be talking about all the components of an electric vehicle. We'll talk about only key components. So once we have talked about the components and how they are engineered, we'll talk about the need for simulations. Now many companies as of today use computational tools to reduce the engineering times, right? Company can use up to 20 different simulation packages to do different things. Now for an electric vehicle, there are several simulation use cases. You can use computational fluid dynamics to basically design a battery thermal management system. You can use an electromagnetic solver to design electric motors, and you can also use a system level circuit simulator to basically design inverter components. Similarly, your electric vehicle is filled with power converters, right? and there are specific tools that are available to design DC-DC converters as well. Last but not least, your entire vehicle's aerodynamics can be optimized. Last but not least, the entire vehicle's aerodynamic aspects can be optimized by using computational fluid dynamics by performing external aerodynamics. Now, in this particular course, we will be talking only about battery thermal management system, and we will not be talking about electric drive simulations, power converter analysis, and external aerodynamic analysis. Now, let's drill down on each of these topics a bit more. Usually when people talk about electric vehicles, there are 2 points. The first point is that it's highly efficient, and the second point is that it's clean. When it comes to efficiency, I'll talk about how is efficiency defined, and we will compare internal combustion engines and electric vehicles in terms of various efficiencies. Now please note that we will not be diving deep into IC engines. As far as emissions are concerned, we'll talk about the major emissions from IC engines. Though most of you already know it, I'll be talking about why the emissions are bad and then how are emissions regulated. Once we have done that, we'll talk about the benefits of electric vehicles from an emission standpoint. Once we have established the usefulness of electric vehicles, we'll talk about the key components of an electric vehicle. Here we'll primarily focus on battery pack and battery thermal management system. In addition to that, there are key components of an electric vehicle. Now, in addition to the above two, there are several key components of an electric vehicle. There is a battery management system which makes sure that the battery operates in specified operating conditions. Then you have your charger, which has to be designed specifically to make sure that the battery gets charged at the right amount without consuming battery life. Then you have your powertrain components, motor and inverter. Finally, another important aspect of an electric vehicle is the reducer, which is essentially a gearbox. Now please note that the last 4 components will not be covered in this particular course. So once we have talked about the different components of an electric vehicle, we'll talk about how these various components are engineered. Primarily with respect to engineering, there are 2 classic methods. The first method is just build and test it, use trial and error approach, but this method is always costly and time consuming. As I mentioned in the start of the lecture, virtual analysis is the way to go for this. Virtual analysis deals with the use of computational tools to test your components in a quick manner. As we talk about simulations, you will kind of realize that it's very cheap to perform simulations because you don't have to build the product. You will also experience that the simulation can actually run very, very quickly when compared to experiments. Finally, if the course actually adds value to you, you will see that simulations is an extremely scalable process. So once the course takes you through a journey of why electric vehicles are required, what are the various components and how they are engineered, we basically jump into computational modeling of these devices. Here we'll first take up a simple battery and we'll create a 1D numerical model for which we will derive an analytical solution. Once we have discussed the solution, I will also talk about the drawbacks of analytical approach and why for industry scale problems numerical analysis is often the preferred method. And in order to teach you numerical analysis, you will be working on a course project. Here you will be working on a made up battery pack which contains 5 cells and you will be performing conjugate heat transfer analysis on it. Now the course also comes with additional course projects. So here you can actually see a single cell that's liquid cooled. The course will teach you the fundamental concepts to run such a simulation. However, this is an additional course project. You will be given all the supporting files and data points, but you are expected to finish the project on your own. Now, if you need to do more, then there is an additional project where you actually compare the liquid cooled configuration with an air cooled configuration. Here, though the results are obvious, you have to provide quantitative data to prove which cooling system is better. Alright, with that I would like to conclude this video and I'll see you guys in the next one. Bye. Hey guys, hope you're all doing good and welcome to a new video. As of 2020, roughly 3% of all the cars in the world are electrified. Now when I say electrified, it doesn't mean that the cars only contain a battery pack. It means that it can also have a hybrid configuration, which means there can be an engine on board. So though only 3% of the cars are electrified, you can actually see that pretty much every company out there is talking about, creating its own fleet of electric vehicles. So if you figure out the reason why they are doing it, it typically boils down to a couple of things. The first thing is efficiency. The second point is emissions. I think emissions is something that we can all relate to. I'm pretty sure you would have seen someone drive a car which emits a lot of smoke, correct? And when you have a whole bunch of these types of cars, it can cause major damage, right? And that is one of the immediate reasons for thinking about electric vehicles. But usually that's not the whole point. If you take a look at electric vehicles, they are not actually zero emissions. Why is that? Well, if you perform a full energy analysis and if you basically look at the origin of the energy that drives the electric vehicles, you can see that it comes from a coal power plant or some other power plant, right? So that also has to be taken into account into the emission calculations. But usually, controlling emissions in a thermal power plant that's far away from a city is much easier and can be regulated much more carefully than, say, the cars that you or I drive, right? So I think that is one point where a lot of people argue, but you can see that as more renewable energy sources are being tapped to generate electricity, that argument slowly starts to fade away. The second point is efficiency, which is definitely a no-brainer. You will actually be seeing in this lesson that IC engines actually waste a lot of energy in terms of heat. Though these devices have been around for close to 100 years, it's very hard to basically tap the energy that basically goes off in your exhaust, right? In fact, that's where the majority chunk of energy is being lost. Okay, so essentially in this particular lecture we will be diving deep into these two specific topics, right? Efficiency and emissions, and hopefully with data I will make you the judge. You decide which is better, IC engines or electric vehicles. All right, so let's get started. So before we jump on to this lesson, I wanted to give you a quick refresh of the learning aids. So different symbols are used across the lectures and they mean different things. The things that you have to specifically focus on is this symbol. Whenever you see this symbol, that's a topic of focus. And if you are taking this course seriously, then you should definitely consider solving the challenges that are provided in this particular course so that you remember those concepts. And similarly, we use a black box for things that we really don't want to dive deep on. So learning objectives, right? So at the end of this particular video, you will be able to understand the need for electric vehicles. And as I mentioned before, we will basically look at this entire thing from an efficiency viewpoint and also from a emissions viewpoint. So once we have done that, we'll talk about how the energy for propulsion originates. Once we have talked about that, we'll try to understand the different emissions that have to be regulated. And then finally, we will talk about emission regulations and what it actually means. And for that, we will be taking up the Euro 4 standard. So first, let's take a look at the energy chain. As I mentioned, you have this symbol here. So it's very important to kind of understand this entire concept. Feel free to take notes and make sure that by the end of this lecture, you remember this flowchart. It's fairly easy, but it's very useful if you actually remember it. So on the left hand side, we basically look at where the energy comes for electric vehicles. So that's why I've colored all the boxes in blue in color to kind of signify that blue stands for electric vehicles. And on the right hand side, we basically look at the energy chart for IC engine vehicles. So let's start with electric vehicles. So as of today, most of the electricity that's produced, at least in India, comes from coal-based thermal power plant. Right? So you take coal, you basically burn it in a thermal power plant, and then that energy is used to boil water, which is then used to run a turbine, and energy is extracted. So you essentially produce a whole bunch of emissions at the thermal power plant, and usually there are several after treatment systems that are placed inside the thermal power plant to take care of these emissions. Then the electricity has to flow from the thermal power plant via the electric grid to your home, and usually there are losses in this process. And finally, at your home, if you have a compatible charger, a wall mounted charger, you will be able to charge the battery of your electric vehicle. And essentially, when you look at efficiency, there is a narrow way to look at it and there is a broad way to look at it. The narrow way to do that is to basically look at, hey, what percentage of the energy that is stored in my batteries is converted to power at the wheels, right? So that's a narrow way of defining efficiency. And if you want to be really broad and thorough, you have to kind of look at the efficiency in terms of the starting point, right? So how much heat or what's the calorific value of coal, and essentially when you burn a kg of coal, you get some amount of energy, correct? What percentage of that energy is at the end of the day available at the wheels of your electric vehicle? that requires a large amount of data and you need to be really thorough about it. Now, as students of engineering, you should focus on getting that information from literature review. If there is a review paper that has been published in a respectable journal, then that's your starting point. Now, in terms of fossil fuels, again, now in terms of IC engines, the process is again easy to understand. You start with fossil fuels. There is an oil refinery which converts your crude oil into gasoline. This gasoline is then transported to your local gas stations. Again, I don't think there is too much loss in that process. If there is any loss, that's usually loss in terms of vapor. But then once the fuel is actually in your car, there are significant sources that basically results in loss of heat in your IC engine. And at the end of the day, the power that's available is very less. So when we basically look at the narrow definition of IC engines, so I strongly believe is the only thing that young engineers should care about, you will actually see that electric vehicle is definitely the winner. So here what I have done is I've basically tabulated the losses that typically occur in an electric vehicle. And we are first looking at a scenario where the electric vehicle is being operated without regenerative braking. For those of you who do not know what regenerative braking is, it's a simple concept. When your car is actually going down a slope, you don't have to spend power, right? In fact, you're most likely braking. And during this scenario, the electric motor can actually act as a generator and can recover some of the energy and put it back in the battery, right? That's what regenerative braking is. But please keep in mind that here we are looking at a scenario where regenerative braking is not taken into account. And also, if you are interested in learning the exact conditions at which this data has been taken, you should basically visit the website that's actually listed in the bottom, right? fueleconomy.gov. Now, the other thing that you should remember is that these tests are performed at standard conditions, standard pressures and standard temperatures, right? And that can actually be beneficial for electric vehicles. And I'll kind of explain about that when I'm discussing all these numbers. So if you take a look at the loss, the primary loss that an electric vehicle encounters is the loss via the electric drive system. So this includes your losses in electric motor, right? Now that accounts to 20% of the total energy that's actually available in the first place. The second thing is charging. You will actually later learn that during the process of charging, there is a large amount of energy that gets wasted. So when you try to charge the battery and say that through your charger 100% flows in, the 100% energy is not going to make it into the battery. Some amount of that energy is going to be wasted in terms of heat. The other thing is accessory loss. Your electric vehicles have a lot of devices that have to be powered via the battery. Great example for that is, say, the heater that's there in a typical car. If you are living in a cold region, then you cannot go without an heater, right? Now in IC engine cars, that process is actually made very efficient. Once your car warms up a little bit, the heat that is required to keep the cabin at a good temperature can be taken from the exhaust. But in electric vehicles, you don't have exhaust gases. So any heat that has to be generated to keep the cabin at a comfortable temperature has to come from batteries. Now, if you own a car and if you drive a car in a place like Wisconsin or somewhere in Canada, then things can go really, really cold. And your accessory loss can go up to 20 or even 30%, right? Now, remember, all of these things are actually worsened with the age of the battery. All right. So that is why it is very important to understand that this table provides data which was measured at a specific condition. And if you're really interested, you should check out fueleconomy.gov to understand protocols that are followed while testing. All right. So that being said, if you take a look at the same electric vehicle with regenerative braking, you get an additional 17% gain from regenerative braking, which makes the total power available to wheels to 79%. So only 21% is lost, right? So in the previous case, we had 62%, which is still good. Now, if you compare this with IC engines, you can actually see that the power available to wheels is just 12%. Right? And this is primarily because in your engine, the losses are generally around 70%. Now, when we say losses at the engine, it can be a bit misleading. Combustion is a very efficient process, and you will see that most of the engines have 95 to 98% combustion efficiency. The problem is heat transfer. A tremendous amount of heat is actually lost via heat transfer, via your exhaust gas, right? And that is why IC engines are unfortunately not that efficient. Everything else, drivetrain loss, parasitic loss, idle loss, accessory loss, they are very comparable to an electric vehicle. The key problem is the loss via heat, which basically does not play well for the IC engines. Now again, as I said previously, an IC engine car in a region say like Texas might be more efficient than an electric vehicle that's being driven in Wisconsin during winters, right? And that is why you need to understand the standards and test protocols that are followed while generating this data. So I hope at this point you kind of understand why electric vehicles are generally the winner from an efficiency viewpoint. Now from an emissions standpoint, on-road emissions for an electric vehicle are typically zero, right? Now if you are having a hybrid electric vehicle, then yes, emissions from that engine that the vehicle carries do contribute towards the total emissions. But if it's 100% electric vehicle, often also called as the battery electric vehicles, your on-road tailpipe emissions are essentially zero, all right? Yeah, I think that's the accurate way of saying it. Tailpipe emissions are zero. Now, when we say emissions, we talk about soot, we talk about oxides of nitrogen, HC, hydrocarbons, carbon dioxide, and carbon monoxide. Now, we all know that emissions are bad. Gases like carbon dioxide are greenhouse gases, and they contribute to global warming. In addition to this, emissions can also cause poor air quality index. If you're interested in knowing more about air quality index, I strongly recommend you to check out the website airquality.gov. I believe it's called aqinow.gov. If I'm wrong, you just Google it. You will find the information as a first link. But essentially, air quality index data looks at all of these key emissions in several major cities across the world, and it basically tells you what's the permissible amount. So now that we have talked about emissions and why emissions are bad, it's very important to understand how emissions are measured. Now there are several standards which are used to measure emissions. You have lab tests, you have on-road tests which basically measure the emissions as the vehicle is driving in realistic conditions. Usually emissions are measured in kg per kilometer or kg per mile, right? So essentially how much kg of carbon dioxide or carbon monoxide is produced for each and every kilometer at a particular speed. You can also look at emissions in terms of the power produced. So kg per kilowatt is also a commonly followed unit. You can also look at the amount of emissions produced per kg of fuel consumed. That's also followed sometimes. All right. So now that we've talked about it, let's look at what an emission regulation looks like. Emission regulation essentially dictates automotive companies to make sure that their tailpipe emissions are kept to a desired amount. So if you look at 1991, right, you can see that there was a regulation on carbon monoxide, right, but there was no regulation on NOx, HC plus NOx, right? And you can basically see that the amount of carbon monoxide that your engine was allowed to generate was roughly 14.3 to 27.1 kg per kilometer. Now this is a lot when compared to what Euro 4 permits, right? And you can see that as years progressed, these emission regulations have become more tight. And as we are approaching 2020 in India, we are basically adopting Euro 6. And you can see that reducing the emissions further is definitely a challenge. It's not an unsolvable problem, but it is not an easy problem to solve. Why? As they always say, right, you basically, when you try to optimize something, you first pick your low-hanging fruit, and then to move the needle from 95% optimization to 99% optimization, you spend a lot of time and money. And that's kind of what has happened to IC engines. We are at a point where in order to achieve, say, significant improvements in IC engine combustion or heat recovery, the amount of money that has to be spent in terms of R&D is crazy high. And that is one of the reasons why companies prefer going electric. I'm not saying that that's the only reason. That's also one of the reasons. So going electric gives automotive companies an easy option to battle emission regulations. All right. So with that, I would like to conclude this video. I hope through this video you learned a little bit about the difference in efficiency between electric vehicles and IC engine vehicles. And you also learned about the different types of emissions, why they are bad and how they are regulated. And hopefully by looking at the Euro 4 emissions, you understood how emission regulations are framed and what are the targets that are given to companies and how these targets have changed over the last several years. With that, I would like to conclude this video and I'll see you guys in the next one. Bye. Hey guys, hope you're all doing good and welcome to a new video. If you take a look at an electric vehicle, it has specific components that are usually not found in an IC engine vehicle, right? So this is what you call as the vehicle architecture. So in this video, we will first compare the vehicle architecture of an electric vehicle against an IC engine vehicle, and then we will identify key components of an electric vehicle that serve specific functions, right? An example would be the battery pack, power electronics devices, motors, inverters, and so on. We will take key components like this and we will describe their functions. And for certain components like the battery, we will dive deep and we'll talk more about the different types of cooling options that are available in detail, because that's kind of the focus of the course. All right, so let's get started. Alright guys, in this lecture the primary objective is to help you understand the differences in vehicle architecture between an IC engine vehicle and an electric vehicle. So once we have understood that, we want to make sure that you understand the functions of key components of an electric vehicle. Again, the objective here is to not offer in-depth explanation for each and every topic, because I don't think that's possible in a short course, but we try to highlight the functions and engineering behind key components that are unique to an electric vehicle. And once we have done that, we will be diving deep into battery packs. We will essentially focus on the different configurations of battery packs and also talk about why these configurations are needed. Once we have done that, we want to make sure that you understand fundamental electrical concepts, because that's extremely important before you try to understand the performance parameters of a battery pack. So let us all first start out with the architecture of a gasoline vehicle. And I'm assuming this is something that most of you are familiar, right? So you have a fuel tank in the back and you have your engine at the front, right? So most of the modern engines have a fuel injection system, and the amount of fuel that's injected is basically controlled by the ECM, which is the electronic control module or the onboard computer. The power that's produced by your engine is transmitted to the wheels via the transmission, and in some cases there is a propeller shaft that runs from the front to the rear. Exhaust gases that are produced because of combustion are emitted out through the exhaust system, which essentially leaves the vehicle through the tailpipe, right? And your gasoline cars has a small battery pack, typically a 12-volt battery pack, which is responsible for running the starter motor and powering auxiliary systems like blinkers, indicators, and other electrical equipments which actually operate when the engine is turned off. Now, in contrast, if you look at an all-electric vehicle, the primary difference is the traction battery pack, which is placed at the bottom of the vehicle, right? So this occupies a large amount of space and also weight, and this is kind of the main differentiator, right? So with respect to the battery pack, the idea is that's your primary energy source, and from the battery pack, the energy has to go into the traction motor. Now, if you're using an AC motor, you need a device to convert the DC current from the traction battery pack to an AC current, and that is where an inverter comes in. Now, in addition to this, electric vehicles have something called as a DCDC converter. So the idea is again very simple. You have a lot of power electronics components that are mission critical, and all of them require different DC voltages. So a DC-DC converter is essentially an onboard transformer which converts the voltages to the respective value depending upon the application use. And then in addition to this, you have a charge port which is basically used to charge the onboard batteries. And in addition to this, right, you have a strong cooling system. Now, in case of a gasoline vehicle, the thermal system, the cooling system is primarily used to cool the IC engine. But here, there are so many things that you need to take care of. You need to make sure that all the power electronic components and batteries are maintained at reasonable temperatures, because all these components are sensitive to temperature and their efficiency drops pretty badly if their temperature exceeds beyond their normal range of operation. Then finally, we take a look at a hybrid electric vehicle. A hybrid electric vehicle essentially contains all the components. Now the primary difference is that the engine and the battery pack and the electric motor are going to be comparatively smaller when compared to an all electric vehicle or compared to a conventional IC engine vehicle, right? But overall it contains pretty much all the components that an electric vehicle would have, right? And it also contains components that a gasoline vehicle would have, and you can kind of see that from this particular picture. Now with respect to key components that you should remember from this course, first is battery, right? Again, with respect to battery, we have a dedicated lecture on it, so we'll give you more details. Obviously the electric motor. See, the electric motor is essentially what converts the electrical energy from the battery to mechanical energy. Then you have your power electronics controllers. So these are essential hardware that controls the speed and torque, right? Now in an IC engine vehicle, you have your fuel injection system, right? Whereas in electric vehicles, your power electronics controller is responsible for controlling the speed and torque. Then you have your thermal system. The thermal system, as I mentioned before, makes sure that the engine, motor, controller, DC-DC converters are all maintained at the right temperature. And with respect to DC-DC converter, it essentially converts high voltage from the battery pack to a lower voltage that is required by other accessories. Now in this particular course, the power electronics controller is not covered. With respect to thermal systems, the battery thermal management system is covered, but cooling of electric motors, cooling of DC-DC converters, and then radiator design is not covered. And then finally DC-DC converters are also not covered. So now let's take a look at a battery pack. So essentially, battery packs provides direct current, right? Or also called as DC power. Now here we have a simple made up battery pack which contains 4 cells. Now these cells are connected via bus bars, and you generally have an onboard BMS. A BMS stands for battery management system. It is quite different from a BTMS, which stands for battery thermal management system. BMS is essentially the manager. It makes sure that a charge and discharge processes occur as per set operating conditions. You don't want the battery to be charged too fast. You don't want it to discharge too fast. You want to make sure that for mission critical application, the BMS also integrates a notification system to let the operators know about critical performance loss. Now, battery packs come in different sizes and shapes. Not all battery packs require cooling. So for example, in this particular case, you can see that the cells are actually packed inside a plastic container and you really don't need to cool it, right? That's probably because the total operating voltage is very low. On the other hand, you can actually have battery packs in different forms. For example, here you can see that there's a battery pack with a rigid enclosure, and it also has a cooling fan, and here's a vent which is basically used to remove the heat generated from the batteries. Now, if you basically think about batteries that are used for automotive applications, you essentially use cells which are then combined to form modules, which are then combined to form packs. And in terms of cooling, we generally see that for automotive application, liquid cooling is preferred because that gets the job done in an efficient manner and in a compact manner. So the idea is very simple. Here I have a simple 2-cell battery pack with a made up liquid cooling system. So ideally you don't need liquid cooling for a 2-cell system, but here we just wanted to give you the idea. So you can see that there's a cooling jacket which kind of wraps around the 2 cells. You have cold fluid going in through the blue inlet. As it goes through the cooling jacket, it takes in additional heat that is generated from the batteries. And when it comes out on the other side, it comes out as hot fluid. Now, if we can extend the system a bit more, you essentially have a large battery pack that's typically found in an automotive application. So here you can see that we kind of repeat the same structure 6 times. So this structure here, which contains several cells, is what you call as a battery module. So in general, for automotive applications, what is desired is you group cells into modules and you have multiple modules that form a battery pack. And this is advantageous in several scenarios. For example, say that the BMS detects there are certain cells that are at fault. You don't have to worry about replacing or removing the entire battery pack. You might just replace or remove a single module. And from an operational voltage point of view, automotive battery packs have really high voltage. So if the modules are smaller, so the risk of having an operational hazard while operating on a battery module is less because the operational voltage per module is going to be low. Again, the drawback of having more modules is increased manufacturing costs. You will have more interfaces between the different modules, and that can cause problems on its own. Ideally, it's a trade-off between safety, performance, serviceability, cost, and many other parameters. Anyway, so here in this picture, this is what you would call as a battery module. and you combine multiple battery modules to form a battery pack. All right, I hope that makes sense. And as I mentioned slide back, typically when you are thinking about number of modules and number of cells per modules, these are the things that you look at. You look at safety, performance, serviceability, and cost. And depending upon the industry that you're working for, these parameters would change. Alright, so that being said, if you want to learn more about batteries, understand battery ratings, you need to have strong fundamentals in basic electrical engineering concepts. As we all know, batteries store chemical energy and they convert them into electrical energy, right? Electrical energy is nothing but electricity, and electricity is nothing but flow of electrons. An electron is essentially a charge, right? So charge is essentially a material property and the unit of charge is coulomb, right? So the charge of an electron is minus 1.602 e minus 19, right? And similarly, the charge of a proton is positive 1.602 e minus 19. So these are things that you might have studied in your high school physics. Now with this, what you can do is you can figure out the number of electrons that you would need to have a charge of 1 coulomb, right? So that would be 1 divided by this number, which is going to be really huge. Now, when 1 coulomb of charge flows per second in a wire, then the current through that wire is called as 1 ampere. All right. So we know what 1 coulomb is. 1 coulomb is nothing but 1 divided by 1.602 e minus 19. That many electrons. So if that many electrons flows through a wire per second at any given point, then the current through the wire is said to be 1 ampere. All right. Now the other important thing that you need to learn is volt or voltage. So voltage is essentially associated with the work done per unit charge. So if we say that a battery has higher voltage, then what it means is, it means that higher work is available to move a unit charge. In other words, you have the ability to move more charge, and since movement of charge is current, you can essentially say that with higher voltage, your current through the circuit would also be higher provided the resistance offered by the circuit is the same. And that is essentially the law V equal to IR. Voltage is equal to current times the resistance. So to kind of reiterate on that example, let's say that you have a 2-volt battery. The amount of work input to move a charge is 2 times more than the amount of work input when compared to a 1-volt battery. In other words, a 2-volt battery will move 2 times the amount of charge as a 1-volt battery, right? Since it's able to move 2 times the amount of charge, you can essentially say that a 2-volt battery will have 2 times more current than a 1-volt battery. Like I said, this statement is true only if the resistance offered by the circuit is the same in both the scenarios. So in order to kind of understand these concepts a bit more and also to understand a few more concepts like charge flow, capacity, rate of charge flow, and then to understand need for DC-DC converter, we have created a very simple example, and I like to call this as a candy machine example. So this is a made up candy machine. No real candy machine looks like this. How essentially you have a bowl here which stores a lot of candies, and you have this box here, and then you have a curved elbow connector which connects the reservoir of candy to the boxes, right? So here are the key concepts. So current is essentially going to be the rate at which these small balls flow, right? So in other words, if you assume that each of these individual red balls is a charge, the rate at which these red balls flow is what you call as current. And potential difference is going to be the difference in electron in particle density in the reservoir and the right hand side, right? So initially, if you can imagine, the candy jar would be full of candies, right? So it would have more balls on this side and you would have no balls on this side. So that is when the potential difference is maximum. So it is almost very similar to how water flows from an overhead reservoir, right? So there the potential difference is nothing but the difference in height. In this case, it's going to be difference in charge density. So what is charge flow? Well, charge flow again refers to how the electrons actually move, or how the balls move, how the candies move in this example. Now you can see that I've actually used a smooth tube to connect the reservoir on the box. Now if I have a material that is slightly more rough, then the balls are not going to flow out that easily. And that is essentially what resistance is, right? So resistance is going to hamper the flow of current, right? So if you have, so for a given voltage, if your resistance is very high, then the current flow or the rate at which the charge flows is also going to be lower. All right. So that being said, let's just take a look at the animation first that we have made, and then we can kind of come back. So you can see that initially the jar is full of candy. And as I play the video, you can see that the ball starts to flow, and this is essentially what you would call as current. And as the jar gets empty, the potential difference is becoming close to zero, and when the reservoir is out of candy, then there is no longer any flow of new charge, right? So that is why when potential difference, current tends to zero as well. So that is why over time a battery dies, because the potential difference between the cathode and the anode essentially tends to zero. Now here you might have noticed that we have kind of explained most of the concepts. I'm not talking about capacity. So capacity is essentially the amount of charge or amount of candy balls that this machine can hold in the starting place, right? So here you can basically see that the balls are flowing at a particular rate. Say that 3 balls per second or something like that. And in 10 seconds, say that the tank is getting empty. So that means how many balls did we have? Well, it's 3 times 10, which is 30 balls, correct? So that is what you call as capacity. And here is an interesting thing. So if you have a capacity of 30 balls, you can kind of play with 2 parameters. What you can do is you can reduce the speed of the balls. So instead of having 3 balls flow per second, you can reduce the rate so that only 1 ball flows out per second. So in that case, it would take 30 seconds for all the balls in the candy machine to transfer to the brown box, right? And that is exactly how batteries work. Batteries have capacity, which is typically listed as amp hours. So essentially they can provide X amount of amps for Y amount of hours. So the capacity would be X times Y. Now, once you know the capacity, you have 2 variables to play with. You can make sure that you draw the current slowly so that you have the battery last for a longer time, or you can draw a large amount of current and the battery capacity is going to last only for a smaller amount of time. In other words, it's going to behave exactly like the candy machine. Now, need for DC-DC converters. So one thing that I wanted to let you know is, as the potential difference is draining, the current is actually dropping and the potential difference actually drops as well. But there are so many power electronics components in your vehicle which would require the voltages to be at a particular level. And that is where a DC-DC converter comes in. So as a battery is operating, its capacity drops over time. As the capacity drops, the DC-DC converter essentially makes sure that it steps up the voltage according to the requirements of a particular device. A DC-DC converter is very similar to a pump. So for example, say that you are pumping water from an underground sump. As the water level decreases, the flow rate is going to also decrease. But to a certain extent, I can achieve constant flow rate by actively increasing the pump power, right? And I can take it a step further and I can essentially have a sensor that measures flow rate, and I can basically have a controller which would increase the power so that the flow rate would be closer to the set point. And this is going to work till a particular level of water level, and at that point the pump might experience cavitation and the system might not work. But essentially that's what a DC-DC converter is. Okay, all right. So to kind of reiterate the example, the capacity of the candy jar is analogous to the capacity of a battery pack, and the flow of the candy balls is essentially like flow of charge, which is current. And the difference in density of the charge on the left hand side and right hand side is basically what you call as potential difference. So now that we have talked about the fundamentals of battery, the other thing that we need to talk about is the sources of heat generation in a battery. Now, why is this important? Since the course is eventually going to teach you how to design a battery thermal management system, you need to understand the sources of heat generation within a battery. And there are 3 concepts primarily. One is the internal resistance, which is essentially because of ohmic resistance. The second source for heat generation is the chemical reactions. Batteries at the end of the day produce electricity through chemical reactions. And you will actually later learn that there is a possibility for this chemical reaction to kind of run in an unbounded way, very similar to a chain reaction, which results in sudden increase in temperature. And this concept is called as thermal runaway, which is a dangerous phenomenon that occurs especially lithium-ion battery packs, because they have a very narrow range of operation, right? So in order to prevent thermal runaway, you need to make sure that temperature variation across all the cells of your battery pack is kept to the required minimum. Okay, so we will be talking more about batteries, but let me kind of touch upon DC-DC converter. So what does it do? Well, it steps up or steps down DC voltage according to the requirements of any other onboard electrical devices. While designing DC-DC converters, the primary challenge is efficiency, making sure that the conversion process is efficient. And your DC-DC converters should be packaged to occupy the smallest possible space. And this is kind of true with most subsystems that are generally available in a car. You also need to make sure that the weight of the DC-DC converter is fairly low, or at least as low as possible. And another unavoidable problem is parasitics. Parasitics is essentially loss that's caused in DC-DC converters because of its interaction with various electronic components. Now, generally, how are these challenges overcome? Well, parasitic losses are geometry dependent, and usually 3D simulations are performed to measure the capacitance, inductance, and resistance of various parts of an hardware. And then once you do that, you can perform system level simulations to obtain the required current and voltage waveforms along with the parasitic losses. Then once you kind of do this, you can then kind of repeat the process, right? You can iterate the same concepts again and again till the performance and the losses are within the desired range. Now, as I mentioned at the start of the presentation, we will not be discussing DC-DC converters anymore in this course. The other key component that is used in electric vehicles is the electric motor, the traction motor. The motor essentially converts the electrical energy to mechanical energy. And with respect to the challenges, it's always about getting more efficiency and minimizing losses. Again, packaging is very important, and also making sure that the electric motor's weight is optimized helps in overall efficiency of the vehicle. Now, electric motors also have to be cooled. Again, it depends upon the size of the car, but if for passenger vehicle applications, your electric motors might have to be cooled. So you will have to integrate, or you'll have to make sure that cooling paths are designed and cooling systems are basically integrated with the electric motor as well. And how are these challenges generally overcome? Well, it's typically done by 2D or 3D simulations where Maxwell's equations are solved to basically perform an electromagnetic analysis on the electric motor. When you solve the Maxwell's equation, you basically solve for the magnetic field, and you can essentially determine the performance characteristics of an electric motor and also determine various losses that are typically found in the electric motor. So again, the process is very similar to what I mentioned in DC-DC converter. Once you figure out a reliable way to measure key performance parameters, you would modify your design. And for electric motor, this can be on the CAD side, this can be on the armature side, or this could be on the winding side. You have different configurations, and there are really powerful tools nowadays which can make your life very easy. And by using a template based system, you can design different iterations before actually building one. And just like DC-DC converter, we will not be discussing electric motor further in this course. Alright guys, with that I would like to conclude this video, and I'll see you in the next one. Thank you. Bye. Hey guys, hope you're all doing good and welcome to a new video. So most of us know how a battery works and what are the various parts in it. However, do we know how the battery gets a particular rated voltage? Well, that's what we are going to be talking about in this video. A battery stores chemical energy and converts the chemical energy into electrical energy. Now let's just break that down into steps, right? So electrical energy is essentially current, and in order for current to flow, there has to be surplus of electrons in one location and there has to be scarcity of electrons in other location, right? And that is when electrons are going to flow, and this is what you would call as current. So if you take your battery, you have your cathode, you have your anode, essentially the electrodes, right? So the idea behind designing a simple cell or choosing the chemistry of a cell is fairly simple. It turns out that there is something called as a reduction potential, and electrode materials have reduction potentials. So what does reduction potential mean? So reduction potential is a property of the electrode which basically tells us how easy it is for that particular electrode to accept electrons, right? So if we take a particular material, for electrodes, say fluorine, if it has really high reduction potential, that means it's going to accept electrons very easily. Similarly, if you have a material that has a really low reduction potential, it cannot accept electrons easily. In fact, it's going to be extremely willing to give up the electrons, right? So I hope you kind of see the pattern here. If the electrode has really low reduction potential, it's going to give up the electrons. In other words, it can create potentially surplus electrons. And if your reduction potential is very high for the other electrode that you have in your battery, then that is going to be really willing to accept these excess electrons. And that is how battery packs are chosen. You take up electrodes and you make sure that one electrode can give up the electrons and the other electrode can just catch the electrons that the first electrode gives up. And this difference in reduction potential is going to determine the voltage of the battery. And that kind of makes sense because reduction potential is measured in volts. So if you subtract the reduction potentials between the cathode and anode, you're going to end up with the reduction potential of your cell. All right. So let's kind of go over a presentation where I talk about this in more detail. And let's take a look at some chemical reactions along with their reduction potentials. All right, let's get started. All right, guys. So let's first discuss the learning objectives of this session. So we need to make sure that you understand the fundamentals of batteries and you get sufficient idea on how cathode and anode for a particular battery can be chosen. And then the third objective is to understand the key performance parameters of a battery. Then the fourth point is to understand the effect of temperature on battery performance. This is also called as temperature sensitivity. The fifth objective is to help you understand the sources of heat generation in a single cell. The sixth and the final objective is to help you understand how a cooling system to basically manage the thermal performance of a battery can be designed. Alright, so battery 101s. Now these are concepts that you definitely have to remember. So make sure that you are taking notes, make sure that you are trying to memorize the concepts because it's going to be very helpful for you. Now batteries have two terminals, anode and cathode, right? Anode is the negative terminal and cathode is the positive terminal, right? Now if you take anode loses electrons easily, right? In other words, anode oxidizes easily. On the other hand, if you take cathode gains electrons easily, and essentially another way to say that is cathode reduces easily, right? So this concept is a bit confusing to a lot of people because cathode is actually gaining electrons, but we are saying that it's undergoing reduction, right? So how can something that's undergoing reduction be gaining something, right? So it kind of seems counterintuitive, but there is an easy way for you to remember this. Just remember the words oil and rig. So oil is OIL, and you can remember that it's nothing but oxidation. I stands for is, L stands for loss. So oxidation is loss of electrons, and reduction, right? Reduction is gain, RIG. So reduction is gain of electrons. So remember the words oil and rig to understand what reduction and oxidation is. So in other words, going by reduction potential, we know that cathode is going to have a very high value of reduction potential because it can accept electrons easily, and anode is going to have a really low value of reduction potential, right? And that's kind of the whole idea. And in a battery at any given time, you have a combination of reduction and oxidation that's taking place in these two terminals. And that's why these reactions are called as redox reactions, right? Reduction and oxidation reactions. And the other thing that is very important is for automotive applications, you would prefer a battery that can be charged. And any battery that can be charged again is what you would call as a secondary battery. So choosing cathode and anode, as I mentioned before, you need to make sure that between the cathode and anode, there has to be a very good difference in reduction potential. So let's take a look at UC Davis's website, LibreText, where these values are documented. So these are off reactions, and you can see that for each and every off reaction, the reduction potential is listed. And the baseline guy is hydrogen. So the hydrogen entry in this table is what is referred to as the standard hydrogen element. You can see that its reduction potential is set to 0. I don't think its absolute value is set to 0, but for the sake of convenience, it is set to 0. It's made to 0 so that you can compare the reduction potentials of other half reactions with respect to the standard hydrogen element. And you can kind of see that lithium has the lowest reduction potential, and that's one of the reasons why lithium ion batteries are so popular. Because of the high reduction potential, you can essentially have really high voltage per cell, and that's essentially what you call as energy density. And if you have very high energy density, you can almost say that you can get more miles from your electric vehicle for a smaller battery pack weight. These two things are not directly correlated, but you need to keep in mind that this statement is not always true. Alright, so if you look at elements that are below the standard hydrogen element, you can see that the reduction potential is now positive and increases. And on the other end of the spectrum, you have fluorine, which has a very high value of reduction potential. So if you make sure that your anode is lithium and if your cathode is made up of fluorine, you will basically have maximum difference in reduction potential. Now, if cell voltage is the only criteria that you care about, then this would be the only strategy that people would use to create batteries. But as it turns out, there are other parameters as well. So if I scroll down this page, you can kind of get to see a different view. So here you can see that this is where your standard hydrogen element is. On the bottom, you basically have lithium, right? So this is kind of the ordering is opposite to the previous table, but this is a much more cleaner looking table. So you can see that positive values of potential, reduction potential, indicates that particular half reaction is going to have the tendency to accept electrons, right? Whereas lower potential means that that particular half reaction has a tendency to lose electrons. Alright, so this is a very important table. Do bookmark this URL if you're interested in learning more about this topic. Alright, so coming back to the PPT, let's take a look at key performance parameters that determines how a battery pack is going to perform. Obviously, voltage is one. We already looked at it. It's the difference in reduction potentials between the electrodes. So the battery chemistry is something that typically a chemical engineer plays with. They try to come up with different strategies, different chemistries that can be supported in battery packs. And the idea is to not only optimize for voltage, but to optimize for other things such as C rate, cycle life, thermal runaway, specific energy, and cost per kilowatt hour. So we already know what voltage is. So now let's discuss C rate. So C rate is defined as current drawn divided by current drawn for 1 hour battery life. So what does this mean? So for example, let us say that you have a battery pack that has a capacity of 2 amp hour. So in other words, for 1 hour it can provide 2 amps. So say that you have your mobile phone, right, and you are using a 2 amp hour battery to charge it. So if your mobile phone is drawing 2 amps, the battery is going to last for 1 hour, correct? If your mobile phone is drawing 1 amp, then the battery is going to last for 2 hours. In other words, the current that's being drawn, and if you multiply it with the duration, that should be equal to the battery capacity. So what is C rate? Well, C rate is nothing but the current drawn by the device divided by current drawn for 1 hour battery life. So if you take 2 amp hour, right? So what's the amount of current that you need to draw so that the battery life is 1 hour? Well, it's very simple. It's 2 amps, right? If you draw 2 amps, then the battery is going to last for 1 hour. So say that your actual device also draws 2 amps. Then you get 2 by 2, which is 1. And that would be the C rate. Now, if you look at the unit of C rate, that's going to be a time inverse, right? Going to be 1 by hour or 1 by second. Now, what is C rate of 0.1? Well, C rate of 0.1 means you're drawing really small amount of current. You are essentially drawing 0.2 amps per hour, right? So if you're drawing 0.2 divided by 2 is 0.1, right? So C rate is very important because it affects battery lives. And a chemical engineer, when they are exploring different chemistries, they also want to make sure that the battery supports high C rates, because in specific scenarios, especially with respect to electric vehicle applications, your C rate might have to be high. For example, say that you are accelerating, right? You want more current to be drawn. Your battery's life should not be affected because momentarily the current drawn is too high. So chemical engineers are generally play with the chemistries to make sure that the C rate values supported by the batteries are high enough so that the battery life doesn't get damaged. Then you have something called as a cycle life. So cycle life basically says how many cycles of charge and discharge a battery can withstand. Now ideally for EV applications that should be a lot. So you need to kind of first define what a cycle means, right? So when we say that a battery has to go from fully charged to some percentage, right? So some percentage of usage, that percentage of usage is what you call as depth of discharge. So if you have a battery and say that 80% of the battery life is consumed before you charge it again, then that's essentially one cycle where the depth of discharge is 80%. All right. So now what would you do? You would charge the battery again and then say that you start using it again, and for the second time the battery's capacity drops by 80%. In other words, there is only 20% battery life remaining. So this is cycle number 2. So you want to make sure that the battery lasts several cycles before replacement, because if it's not going to provide the promised cycle life, a customer who is going to buy an electric vehicle from you is always going to have range anxiety, and that directly affects the sales. So any automotive companies that makes battery packs keeps a strong eye on cycle life. The next key performance parameter is thermal runaway. As I discussed before, it's essentially a chain reaction which leads to spontaneous heat generation, which increases the temperature of the battery by a really large number, right? It can go as high as 300 degrees Celsius for certain lithium ion chemistries. You can read more about that in this particular reference. The other parameter is essentially specific energy, which is energy per kg. This is again a very important parameter, and this is directly related to the difference in reduction potential between the electrodes. And I think as in any engineering application, the cost is going to be the driver. So cost can be modeled in several ways. You can look at cost per kg of battery if battery is kind of the main driver, or you can basically look at cost per kilowatt hour, and that's a common metric that is used with respect to automotive application, because you can then compare how much dollars you save by having an electric vehicle when compared to having a gasoline vehicle. All right. Now you need to understand that the above list is not comprehensive. There are more parameters that define the performance of batteries, but I would like to think that the parameters listed here are really fundamental, and oftentimes if you understand these parameters very well, you would be able to understand the comprehensive set of parameters that's listed in this particular reference. So temperature sensitivity. Now batteries are sensitive to ambient temperatures and heat generation. Now there are certain variations of lithium ion chemistry based batteries which have different temperature sensitivity limits, and if you're really interested in learning more about that, I would point you to the reference that's listed in the footer. One interesting thing that was actually pointed in that particular text was within the United States, the variation in ambient temperature across all the states resulted in a difference of battery life amongst the cars that were sold in these states, and this difference was up to 4 years, which is really crazy, right? That kind of shows how important temperature sensitivity is. In other words, so you need to make sure that while designing a battery pack, the temperature non-homogeneity is as low as possible. Thermal runaway, I think we have already talked about that a bit. So the above points essentially let us know that a battery thermal management system is essential for electric vehicle applications. Especially when you have larger battery packs, you have more cells, you need to make sure that whatever cooling strategy that you use results in a lower non-homogeneity of temperature amongst all these cells. Alright, so since temperature of the cell is kind of the key performance parameter, it's very important to understand the sources of heat generation in a battery. We already discussed this once, but this is the first time we are going to be looking at a mathematical equation. The heat generation inside a cell can be modeled as 4 parts. Joule's heating, which is because of internal resistance. Entropic heat generation because of irreversibilities in the system. aging related effects and mixing related effects. Now, if you write down these equations in a mathematical form, you get the equation that is basically shown here. Now, this is a differential equation for heat generation. We can actually use this equation to predict how the temperature inside the battery pack is going to change. And that is what we are going to be doing in the next class. One of the things that I want to make you understand is that it is perfectly fine even if you do not understand what each of these terms do. If you get an accurate representation for these terms in terms of having the values to compute these quantities, then create a mathematical model which calculates the temperature inside a battery efficiently, right, and accurately. Now here is an important thing. That is the first requirement for you to be able to design a cooling system. You need a way to estimate the temperature distribution accurately. This can be a numerical model or it could be an experimental setup, doesn't matter. So once that is there, you can basically look at a majority of the constraints, right? So you first look at the key performance parameters of your battery, right? Once those parameters have been satisfied, then you basically look at additional design criteria. For example, what's going to be the amount of space that this battery pack is going to use? What is its weight going to be, right? Based upon this, a cooling solution can be designed. And when you use a cooling system, then there is going to be efficiency loss. And if you remember from the vehicle architecture lecture, if the ambient temperature becomes very low, for example, in states like Wisconsin, you basically use power from battery to heat the batteries so that it's maintained at the correct temperature. In those situations, you end up wasting a large amount of power, right? So a cooling solution has to be able to do that as efficiently as possible, right? You cannot go without heating the cabin, right? You cannot go without maintaining the batteries at the right temperature. That is a cost that we have to pay, but we have to make sure that it is done in the most efficient way possible. But then once this is done, you kind of repeat the process over and over again till you essentially get that desired cooling system. From a cost point of view, the primary thing that affects your decision is the type of cooling solution. You can go for an air-cooled solution, a liquid-cooled solution, or even end up using something like a phase change material. For automotive applications, liquid-cooled solutions are better, and there are a lot of reasons, right? So you want to make sure that your battery is first not exposed, because in case of an accident, you want to make sure that the battery is sealed as much as possible and takes as less of a damage as possible. So since the entire system is going to be sealed, air cooling is no longer an option. So the primary option is going to be liquid cooling, where you basically run liquid coolant across all the cells and make sure that everything gets cooled. All right. Now phase change materials can also be used, and sometimes phase change materials are used in conjunction with liquid cooling. All right. That being said, that brings us to the end of this lecture, and I'll see you guys in the next one. Thank you. Bye. Hey guys, hope you're all doing good and welcome to a new video. So in this class we will be talking about heat transfer modeling for batteries. Now the way heat transfer can be modeled in batteries is fairly simple. We first split the batteries into a series of control volumes, and then we write an energy balance equation, right? And what you would generally notice is when you perform this energy balance equation, you would apply Taylor series to figure out a differential form of an equation which basically says that the energy is balanced. This differential equation is what you would call as the governing equation. Now in certain cases, these differential equations can be solved very easily, right? So you would usually solve differential equations by integrating them, correct? In certain cases it's possible, in certain cases it's not possible. And oftentimes when the geometry becomes very complex, getting an exact solution by performing integration is very hard. So we will essentially do that in today's lecture. I'll show you how to derive an equation which basically predicts the steady state temperature distribution, right, in a domain, in a 1D domain with heat generation. Once we do that, we will kind of perform some parametric studies in Excel, right? And I would show you the results, but I'm not going to show you how to do the Excel calculator. I think that would be a great assignment for you guys. All right, that's it. So let's get started. All right, guys. So in this video, we will primarily be looking at how analytical measurement of temperature distribution can be made. And for that, I'm going to be taking a very simple example. Essentially, we are going to take up a one-dimensional domain and derive the energy balance and then solve it. Once you have solved the analytical equation, I will show you a calculator that I wrote using Google Sheets, which can basically plot the temperature distribution for this 1D problem. Once you have done that, we'll talk about the drawbacks of analytical methods and techniques and solutions to overcome these drawbacks. Alright, so now I'm going to be switching to a different view where I will explain the problem statement and derive an analytical solution. Alright, so what we are basically going to do is we are going to consider a 1D problem, right? So let me kind of explain what a 1D problem would be. Say that this is your battery, okay? The battery basically is rectangular in shape, right? Now, the reason why I'm going to say that this is actually 1D, though in this case it's actually not 1D. In fact, if I basically take the thickness into account, it's clearly a 3D shaped object, right? So why am I saying that this is 1D? Well, I'm saying that it's 1D because of the key assumptions that I'm going to make. Alright, so first let's just consider this as the x-axis, this as the y-axis, and then this as the z-axis. Alright, so the first thing that I'm going to assume that the temperature variation along x-axis is much more significant. The temperature variation is much more significant than temperature along y-axis and temperature along z-axis. So what can be an example for this? Well, ideally this diagram would not be a good example for an 1D beam. Something like a fin, for example, if you take it like this would be a great example for 1D because the majority of the variation in temperature is going to be along the x-axis, and along the y-axis and z-axis, because of the small thickness and because of the low resistance, it's okay to neglect heat transfer that is taking place in that direction, right? Formally you would do this by calculating something called as the Biot number, right? But in this case we are just not going to worry about that because our aim is to not solve a heat transfer problem. But we are not going to be discussing that. We are going to say that in this particular example, the temperature variation along x-axis is much more significant, right? So we are not calculating a Biot number. We are just assuming that temperature along x-axis is significant. And towards the end of the video, I'll explain to you why this assumption is okay. Alright, so with this particular wall, what I'm going to do is I'm going to pick a small element, right? And this is going to be my control volume. Alright, let me just shade it. And what I'm going to do is I'm going to basically write down some key equations for that particular control volume, for that particular slice. Now, since it's one-dimensional, right, in this particular control volume, you will have the temperature at just one point, right? So this is our x-axis, remember that, and this is my y-axis, right? So along y-axis, the temperature is not going to be changing. So in other words, for this entire rectangular slice that I've taken out, there is just one value of temperature. So in other words, it's very common for me to take this picture and simplify it further by just having a single point which represents the temperature of this entire rectangular slice. And then what I'm going to do is I'm going to add just imaginary lines which basically indicates the border of that particular rectangular piece. Now, along x-axis, the amount of heat that flows into this particular element is going to be Q underscore x, right? So Qx is the amount of heat that flows into this particular element. Now, I'm going to say that the size of this element is dx, okay? So this particular location is going to be x, and this particular location is going to be x plus dx, right? And as you can see, the difference between these two coordinates is dx. So using that logic, if the amount of heat entering the phase that's located at x is going to be qx, the amount of heat that exits out of x plus dx is going to be qx plus dx. And I'm just going to indicate that the heat flux flows outside. So now what is the energy balance? Well, it's very simple. Qx should be equal to Qx plus dx, right? So we are essentially ignoring any heat that can transfer in this direction, right? We are ignoring that because remember we are saying that the problem is one dimensional in nature. Alright, so now what do we do with this? This is not really helpful. We kind of know that Qx is equal to Qx plus dx, but what else do we need? Well, since we are trying to figure out what causes a change in heat flux, we need to somehow convert this into a differential equation, and the key is kind of in this particular term. So if you recall Taylor series, Q at x plus dx is nothing but Q at x plus dq by dx into delta x plus d square q by dx square times delta x square by 2 factorial and so on. So I hope you would have studied this formula at least in your high school or in the first 2 semesters of your engineering mathematics. If it is not clear, I'll kind of give you a different intuition. Say that the amount of money that you have in your bank is changing at the rate of 5 rupees per day. So for example, say today is day number 1. So today is day number 1. You had 5 rupees. So tomorrow is going to be day number 2. You're going to have 10 rupees. And the day after, you're going to have 15 rupees, right? So essentially what I'm saying is the amount of money that you have changes with respect to the days at the rate of 5 rupees per day. In other words, you can write a differential equation for it, and you can see that dm by dd, where m stands for money and capital D stands for the days, is 5 rupees, positive 5. So every day you're gaining 5 rupees. And now I can kind of convert this into a form, right? So what I can basically do is I can say that, okay, right, m tomorrow minus m today by tomorrow minus today is equal to 5 rupees, right? Because dm is what? Rate of change of money with respect to days, right? So the money that you have tomorrow minus money that you have today divided by tomorrow minus today, the number of days, is equal to 5. And let's check this out, right? So for example, consider today is day 1. So tomorrow you have 10 rupees and today you have 5 rupees, and if you divide that by tomorrow minus today, the answer is nothing but 5 by 1, which is 5, right? So if you take this, m tomorrow is nothing but 5 times tomorrow minus today plus money that you had today. Alright, if I just rewrite in a different way, m tomorrow is equal to m today plus 5 times tomorrow minus today. Now let's simplify this further, right? So I'm going to say that m tomorrow is nothing but today plus dt. dt is a small interval of time, and today is nothing but m today. And what is this phi? Well, this phi is nothing but dm by dd, which is our differential equation. And tomorrow minus today is nothing but dt. Now if you basically look at this, this kind of makes a lot of sense. The money that you have today, if you take that and if you add the product of rate of change of money with respect to days multiplied by dt, you would predict the money that you have in the bank tomorrow. Similarly, if you have the heat flux at location x, you can then take the rate of change of heat flux with respect to x, multiply that by dx, and that's going to be the heat flux at location x plus dx. And this is what Taylor series is all about. In fact, the equation that I have drawn a box over is more accurate. This equation in fact was derived from Taylor series, and that will be clear in a second. So in this equation, if we assume that delta x is very small and delta x tends to 0, you can ignore the higher order terms. Essentially, you will get an equation q at, this should be x plus dx. Q at x plus dx is nothing but q at x plus dq by dx into delta x. And you can see that this equation right here matches very well with this equation and this equation that we have written down. So now that we have derived an expression for qx plus dx, we have to take this equation and substitute it in this equation. So we started with qx is equal to qx plus dx, and then I later pointed out that qx is going to be equal to, and for qx plus dx we derived that it's equal to qx plus dq by dx into delta x. Qx and qx cancels out, and we end up with a differential equation which basically says 0 is equal to dq by dx into delta x. Right? So essentially I can kind of rewrite this as dq by dx is equal to 0. The delta x, when you take it to the other side, becomes 0. Now this right here is the governing equation or the differential equation for the particular problem that we have in hand. Now the reason why we basically assume that this is actually one-dimensional is because the aim of this exercise is to actually teach you how to perform energy balance, and we are not trying to solve a particular heat transfer problem. If you want to do two-dimensional analysis, you might as well do the same thing. Your energy balance will include additional terms, right? Now here we are assuming that the domain is one-dimensional so that the derivation can be made easily. Okay, so let's take a look at this equation. dq by dx is equal to 0. So what does this mean? Well, if you write this down in English, it says rate of change of heat flux with respect to x, which is nothing but the position, equal to 0, which means your heat flux does not change with respect to x, which is very interesting, right? And that kind of makes sense, right? If you take a rectangular plate like this, or doesn't matter what shape it is, if you're simplifying the domain to be 1D, at any x location you just have only one point where you are looking at heat flux or temperature. Similarly, in this case it was going to be like this. So if you consider heat flow along these points, there is no reason for the flow to depend on the x location unless you are generating a huge amount of heat. For example, say that in this particular location you are generating heat, right? Only then the heat transfer change, right? So this equation kind of makes sense. It matches with our intuition. So now how do we solve this equation? Well, so here our objective is to not solve for Q, rather we want to solve for temperature. So what is the relationship between Q and temperature? Well, this is where Fourier's law comes into play. We all know that Fourier's law states that Q is nothing but minus K times A times dt by dx, right? So let's take this equation and substitute it into our original governing equation. So we have d by dx of Q, and instead of Q I'm just going to put in K times A times dt by dx, and I'm going to say that this right here is equal to 0. So you can see that essentially what this boils down to is you have minus K times A d square T by dx square is equal to 0. Now why did I remove thermal conductivity and area outside the derivative? Well, for those of you who are not that comfortable with derivatives, in order for me to remove K and A outside the derivative, K and A should not be functions of x. For example, let us say you have phi times x, right? Phi is a constant and x, this is a function. Now say that we are trying to differentiate the function, df by dx is going to be equal to phi. Alright. Now when you try to integrate it, you would basically do something like this, and before you do that you would say that alright, so my integral of df is equal to integral of phi times dx, right? So the dx is taken to the other side. Now since phi is not a function of x, it can be taken out of the integral, right? So you can say phi integral of dx. You're going to get the same result. Similarly, let's take the original function f equal to phi times dx, right? So when you're trying to differentiate it, you have df by dx is equal to d by dx of phi times dx. Since phi is not a function of x, I can basically say that this right here is nothing but phi times d by dx of x. Sorry, I made a mistake here. This should be x. Alright. So similarly, here if I'm taking minus k times a outside the derivative, I'm assuming that my thermal conductivity and area doesn't change as a function of x, or at least within a given element it's not changing. Alright, so once you have it, you can basically take k to the other side, and that's going to become 0. So you have d square t by dx square equal to 0. Now what we are going to do is we are going to integrate this equation. So how do you integrate this? Well, so let's start with integrating it once with respect to dx. Alright, so the integral of d square t by dx square is going to be dt by dx. Right, and this right here, integral of 0 is 0. Right, so we are just going to say that integral of 0 is 0 plus we will get a constant of integration. Now what I'm going to do is I'm going to integrate this again. But before I do that, I have to make sure that I take my dx on the other side. So I'll have an equation, integral of dt is going to be integral of 0 times dx plus integral of k1 times dx. So what is the integral of dt? Well, it's just temperature, but as a function of x. So I'll just put it as t of x. What is integral of 0? Well, integral of 0 is just 0. Plus, if you want, you can basically add a constant of integration there. So let's just call that as k2. Plus, integral of k1 dx is nothing but k1 times x plus another constant k3. So what I'm going to do is I'm going to say that k1x plus k2 plus k3, and I'm just going to say that my constant k2 is actually a sum of k2 plus k3. So then I will have an equation k1x plus k2. Now here's the thing, how would you find k1 and k2? Well, this is where you would need something called as boundary conditions. If you know that at x equal to 0, the temperature is say 50 degrees Celsius, and at x is equal to L, the temperature is 20 degrees Celsius, you can actually solve the system. So let's kind of do that. When x is equal to 0, you can kind of see that T1 of 0 is going to be equal to K2, and we know that T1 of 0 is 50 degrees Celsius, which means K2 is now 50. Similarly, let's look at the other boundary condition. We know that T1 of x equal to L is nothing but K1 times L plus we already know K2 is 50, and T1 of x equal to L is nothing but your right hand side temperature, which is 20. Right? So in other words, what I can say is I can say that K1 is nothing but 20 minus 50 divided by L, or I can write it in a generic form, which is nothing but 20 is the temperature on the right hand side, TR minus TL divided by capital L. Right? So K1 is nothing but TR minus TL by capital L. So for those of you who don't understand what TR, TL and capital L are, Well, in the 1D example, right, we had different points, correct? So L would be the length of the domain, right? And TR would be the temperature in the last node, and TL would be the temperature in the first node. Okay, so if you look at this right here is difference in temperature by difference in distance. So this is essentially the slope, right? And if you look at the equation a bit more carefully, this right here is very similar to y equal to mx plus c, where m is the slope, right? In other words, if I plot this particular equation, I'm going to get a straight line, and it's very simple. The straight line, in order to draw a straight line, you have to make sure that your temperature at the left and the temperature at the right have to be anchored correctly. And if you do that, then you get your profile. So if L is the length of your domain, this point, the coordinate of this point is nothing but 0, comma TL, and the coordinate of this point is L, comma TR, right? And that's based, and this straight line is what you would call as the temperature distribution. Now imagine that we have a battery pack like this. What I'm going to do is I'm going to draw a line radially, and I'm going to say that this is my x-axis and this is my y-axis. Alright, I can estimate that, okay, if I know the temperature at the interior of the battery, and if I know the temperature at the surface or the skin of the battery, I can determine the temperature distribution, right? If you have an equation just like this for the battery pack, then you can figure out what the temperature distribution is. So once you have the temperature value at any point in the battery, you can figure out if a particular cooling solution reduces the temperature non-homogeneity inside a cell. Alright, but here's the problem, right? So in this particular case, this equation is not going to be applicable because we assumed a 1D domain, right? Now in this case, what we have to basically do is we have to probably convert our differential equation into cylindrical coordinates, and do the calculation. In fact, that is what you would be doing as part of your assignment. Now let's kind of summarize what we did. We derived a governing equation which basically dictates how the temperature changes in a 1D domain. Now, so the key assumptions are that the problem is one-dimensional, and the second thing is there is no heat sources, and then the third thing is that we assume that thermal conductivity is constant and doesn't change with respect to the position. Alright, so with that I would like to conclude this video. In the next video, what I'm going to do is I'm going to derive a similar set of governing equation for a 1D problem, but this time we are going to introduce heat generation as well. Alright, I'll see you guys in the next one. Bye. Hey guys, hope you're all doing good and welcome to a new video. In the last class, we derived a governing equation that dictates how the temperature changes in a 1D domain where there is no external sources of heat. So this time what we are basically going to do is we are going to take a 1D domain, right? So again, you can draw it in any shape you want, but what I'm saying is along the x-axis is where the temperature difference is going to take place. So in other words, all I need is just a single point to represent that particular location, and I just need one value of temperature in that location. And obviously these are your boundary points. So now what we are also going to do is we are going to say that there is going to be a volumetric source of heat generation, right? So in this entire volume there is going to be some, and I'm just going to call this as Q triple dot, right? and I'm going to say that this is the amount of energy that's introduced in watt per meter cube. So it's very similar to how a battery would generate, but the only thing is, though the heat generation is applied to the entire rectangle, only these nodes are going to be affected, right? That's because this is a 1D problem. If it's a 2D problem, then you will have nodes throughout the area, then those nodes will also get a share of the generated heat. So now, just like we did last time, we are going to first draw a control volume around a single node which is at the interior, and let's just isolate that node. So this right here is the x location, this right here is the x plus dx location. Alright, and just for the sake of it, what I'm going to do is I'm going to say that the area of cross section is going to be a meter square. Alright, so now the incoming heat is going to be q at x, the outgoing heat is going to be qx plus dx, and the volumetric heat generation is going to be q triple dot. Now we know that the volumetric heat generation as units of watt per meter cube, and the heat flux as units of watts. So now if I basically write an energy balance, which basically says that my input heat plus generated heat is equal to the heat that actually goes out, that would be wrong because we have broken the dimensionality of the problem. So qx as units of watt, you cannot add a quantity that has units of watt per meter cube and then expect the results to be watts, right? So this essentially says that our equation is wrong. So how do we take watt per meter cube and convert it into watts? Well, it's very simple, right? If you are able to multiply this with another quantity that has units of meter cube, then you would essentially get units of watt. And what is it that has units of meter cube? Well, that's volume, right? So what I can do is I can basically say qx plus q triple dot multiplied by volume of the entire control volume is going to be equal to qx plus dx, and this is going to be correct. And volume is generally area times dx, right? So this is where our cross section area comes in, so I can retain this. And just like we looked at in the last lecture, qx plus dx is nothing but qx plus dq by dx into delta x. So I can cancel qx right off the bat, and essentially what I have is q triple dot a times dx is equal to dq by dx into delta x. Now we are going to apply Fourier's law here. Q is nothing but minus ka times dt by dx. If we take this equation and substitute it here, we would get d by dx of minus ka dt by dx into delta x is equal to q triple dot a times delta x. So this right here should be delta x or dx, depending on how you want to call it. Now what I'm going to do is I'm going to take the area of cross section out of the derivative and also the thermal conductivity. So we will have minus ka times d square t by dx square is equal to q triple dot a times delta x, and you have another delta x here. So we can take a times delta x and we can cancel it out on both sides. So essentially the differential equation that we have is nothing but d square t by dx square is equal to Q triple dot by A. Now remember, we are going to assume that the volumetric heat generation is constant throughout the volume, so it's not going to be a function of X. So essentially Q triple dot, and sorry, this has to be thermal conductivity K, right, not the area. Both of these are constants. So what we are going to do is we are going to take this, we are going to multiply right hand side with small dx before we take the integral. Alright, so integral of d square t by dx square is going to be dt by dx, and here we are going to have Q triple dot by K, and there is a negative sign, right? So there is a negative sign here, so let me just carry it over here as well. And integral of dx is going to be x plus a constant. Now we can kind of do the same thing again. So I'll first multiply and then integrate on both sides with respect to dx. And since Q triple dot by K is a scalar, I can take it out of the integral sign, plus integral of C1 times dx. So integral of dt by dx with respect to dx is going to be t of x, and on the right hand side we have Q triple dot K multiplied by x square by 2, plus we are going to have C1 times x plus another constant. Now in the same example, so here let's call TL as the temperature on the left hand side node and TR is the temperature on the right hand side node, and let's figure out the values for C1 and C2. So when x is equal to 0, we know that temperature is equal to TL. So if you take this and solve it, you essentially get the equation T left is going to be equal to C2, right? So that's a straightforward result. Now we also know that at x equal to L, the temperature is going to be TR. So if we substitute this, we basically get TR is equal to minus Q triple dot by K times L square by 2 plus C1 times L plus C2, which we know that it's TL. So I can basically say that TR minus TL plus Q by K into L square by 2 is equal to C1 times L. So in other words, C1 is going to be equal to TR minus TL divided by length plus Q times L divided by K into 2. Now there is L square here. When you divide it by L, that gets cancelled. So now that we have determined C1 and C2, so let's figure out the final expression. So T of x is going to be minus Q triple dot by K x square by 2 plus TR minus TL by L plus this should be Q triple dot L by 2 times K, and this entire thing has to be multiplied by x plus C2, which is nothing but TL. Now obviously there is room for simplification, but this right here gives us an expression. Now here is the interesting part. If you assume that this 1D model is for a battery, right? Now again, please remember that for a battery pack, it's better if you derive the equation in cylindrical coordinates. But the idea is, if this equation is valid for a battery pack, you can actually model Joule's heating, entropic heat generation, aging effects, mixing effects, and you can solve the equation that we had seen in the previous presentation, you will be able to compute Q triple dot, and from that you can actually estimate the temperature within your battery pack. So now what I'm going to do is I'm going to show you a simple Excel calculator that I wrote to solve this particular equation. So this right here is the steady state temperature distribution calculator. So here T left is 80 and T right hand side is 20 degrees Celsius. And for thermal conductivity, I have the control set right here. So for each and every case, I can basically change the value of thermal conductivity. So currently I'm not changing it. And here you can see that this is the X value, right, 0 to 1. And this right here is the temperature. Oops. Let me just modify this. Alright, so this is the Excel calculator that I wrote to solve the equation that we just now derived. So here what I have done is I'm plotting the X position and the temperature, right? And you can see that I have 3 graphs. So the data for the graph comes from, this table, and this table. In all these 3 cases, you can see that the X vector is the same. It goes from 0 to 1, right? So the only thing that is different is the temperature that I'm plotting. So in this case, I'm plotting temperature for heat generation equal to 0, and that's the blue line. And you can see that when the heat generation is 0, you essentially get a straight line. In this scenario, we basically look at the temperature when the heat generation is equal to 50 watt per meter cube. And in this case, we have 100 watt per meter cube. And what I'm doing is I'm plotting all of them on the same graph. And you can actually see that at the boundaries the values are the same, because that's what boundary conditions are, right? They don't change. And in the interior nodes, the temperatures are actually estimated. So the number of points that I have depends upon the number of nodes. So the number of nodes that I have used for this calculation is equal to the number of rows that you see here, which in this case, if you look at the count, is 11. So I'm looking at 11 nodes in total, and 2 of those nodes are boundary nodes, so I have 9 interior nodes. Alright, so let me summarize what we learned in this particular lesson. We looked at how to derive an energy balance equation for a one-dimensional problem, and we looked at the derivation with and without heat transfer. Now, though we did a one-dimensional analysis, this actually teaches us a lot about batteries. If you want to actually compute the temperature distribution inside a battery accurately, you just have to get the heat generation term accurately. Once you do that, you can actually use this particular equation to get the temperature distribution inside the single cell that you have. Now, yes, your accuracy would be much better, and now the right way to do this would be to derive the governing equation using cylindrical coordinates, because most of your cells are cylindrical in shape. But if you see a cell that's rectangular in shape, then this approximation would be okay. But the one-dimensional assumption would no longer work. You would have to at least use a two-dimensional temperature equation. But the thing is, the derivation process for deriving the 2D equation is exactly the same as the derivation process for 1D equation. Alright, so now that being said, let's discuss the drawbacks of the analytical method. Now, in the examples that I demonstrated, I basically took a simple 1D problem, right? But batteries, battery packs, battery modules have complex shapes. So it's going to be extremely hard to derive an analytical equation for a battery pack. In fact, it turns out that even if you're able to derive the equations, you cannot solve it by using basic techniques such as integration by parts. Alright, and that is why people use numerical techniques, numerical methods to solve these differential equations. And a process called numerical discretization is employed to convert the differential equations into a linear equation. Right, and there are several methods to do it: finite difference method, finite element method, and finite volume method. Right. In fact, the point-based derivation that we had shown earlier is essentially what finite difference method is all about. Right. Though we did not get into it in a detailed way, looking at the derivatives at a point level and then deriving an equation Based on that is the fundamental concept behind finite difference method. So how are complex problems solved? So complex problems are solved by taking the original differential equations and solving them in a discrete domain. And with respect to battery thermal management system, if you want to do this, you have to learn something called as computational fluid dynamics. Computational fluid dynamics, which is often called as CFD, deals with simulating fluid flows using a computer. Alright, with that I would like to conclude this video, and I will see you guys in the next one. Bye. Hey guys, hope you're all doing good and welcome to a new video. When the geometry of the battery pack gets very complex, it's going to be extremely hard and sometimes impossible to derive an analytical model, right? So in this scenario, the only way to achieve a solution is by using numerical techniques. We can use numerical methods. We can employ numerical methods and discretize the entire domain so that we are not solving the original differential equations, but we are rather solving a much more simplified linearized set of equations. This entire process is called as discretization, and there are several techniques called as finite difference method, finite element method, and finite volume method to solve differential equations. Right now, when applied to fluid flow, the most common discretization technique by choice is finite volume method. And computational fluid dynamics is all about solving discretized equations that have been derived using finite volume method on computers. Alright, so let's learn more about fundamentals of CFD. I have a presentation for it, and towards the end of this lecture I'll be showing you how you can build your own CFD solver using Microsoft Excel. It's a fairly simple solver, but I think you'll be able to understand a whole lot about CFD through this particular calculator. Alright, so let's get started. Alright guys, so in this video we will primarily be learning about what is computational fluid dynamics and also try to understand the math behind CFD. So what is CFD? CFD is a computational technique that's used to simulate fluid flows using a computer. Now if you Google Blender animations on YouTube, you will see a lot of cool animations like the one that I'm actually showing on screen. So this particular video was made by the Blast Raider YouTube channel, and you can see that it features a lot of really cool looking smoke animations, liquid animations, and essentially animations of fluids. So this is what you call as computational fluid dynamics. Now these animations are not made very accurately from a physics point of view. They are made accurately from a visual point of view. So it has to look correct. Doesn't mean that it's actually solving the right equations with the right amount of accuracy. Now in the context of CFD, you can simulate both liquids and gases, and towards the end of the video you will actually see that you can co-simulate fluids and solids together to simulate some really interesting applications. Now if you have never heard of CFD, I want you to think about electromechanical systems that you might have encountered in your academic or professional life and figure out how CFD would be useful for that particular system. Right now I actually have the answer to this question in the next slide, so if you want, feel free to just pause the video and think about it for 5 to 10 seconds. It turns out that anywhere fluid actually flows, you can actually use CFD to optimize the system if you really care about the system. In the context of electric vehicles, you might be interested in simulating the flow over the battery pack to make sure that the batteries are cooled efficiently. In the context of IC engines, you might want to see how the air actually flows through the intake port of an internal combustion engine and calculate things like volumetric efficiency. In the context of safety related simulation, you can basically simulate how fire spreads in a room, and the examples can keep on going on. Right, so anywhere there is fluid, which is liquid or air involved, and if it is an engineering system that needs to be optimized, you can definitely use computational fluid dynamics for it. So now the obvious question is, how can a computer do all of these cool simulations? Well, I can give you a short answer, which is computers are very good at solving linear equations, and you might come back to me saying, so what? Well, what I'm trying to say is, if you give the right set of equations, right set of linear equations to the computer will actually solve it for you. And let's kind of take a simple example. So this right here is a common IQ test. Say that you're going to a shop and you're purchasing a packet of milk and coffee, and together the cost is $1.10. Secondly, the cost of milk is $1 more than the cost of coffee. If I say these two statements to you and ask you to find out what the cost of milk and cost of coffee is, you can immediately say, well, the cost of coffee is 10 cents and the cost of milk is $1, right? So the total is $1.10. And this is the answer that 90% of you will give. But that answer is actually wrong, because though it meets the first constraint, the second constraint is not met. If you say that coffee is 10 cents and the cost of milk is $1, together it adds up, yes, $1.10. But the cost of milk packet is not $1 more, it's just 90 cents more. In other words, this problem had to be broken down into two equations, right? So the first equation is the cost of milk plus cost of coffee is $1.10. The cost of milk minus cost of coffee is $1, because the cost of milk is $1 more than the cost of coffee. Alright, I hope that makes sense. Now, human beings are very intelligent. We can convert English statements into equations in our head, and we are somehow able to solve it. The thing that a computer can do really well is solve these two equations. If you give it the linear equations, yes, the computer can actually do it very well. The only thing that the computer cannot do is it cannot take a problem statement, a generic problem statement, and convert it into linear equations. And maybe someday computers would be able to do it, and if they're able to do it, I think that would be really amazing, right? But the challenge here is, for this simple problem, we can figure out what the equation is and we can let the computer know, hey, solve these equations for us. But for simulating fluid flow, right, what is the equation that we need to basically take, that we need to solve? So for complex simulations like this, what is the equation that needs to be solved? Well, it turns out that the answer is a set of complex looking partial differential equations. These are what you call as governing equations, and at the end of the day, the governing equations have been derived by simple principles like mass conservation, momentum conservation, and energy conservation. So here you have a set of partial differential equations, right? For example, the continuity equation states that the mass is conserved, right? This is the mathematical representation of the statement mass is conserved. Similarly, the mathematical statement which represents momentum is conserved is this equation for the x momentum, this equation for the y momentum, and this equation for the z momentum. The reason why you have three equations is because momentum is a vector quantity, and momentum would be balanced along x, along y, and along z. Finally, you have the energy equation, which basically says that energy can neither be created nor be destroyed. So now the challenge is, how do you take these equations and convert it into linear equations? Well, the short answer is discretization. For example, if you have a continuous variable such as dy by dx, you can convert it into discrete representation. Dy by dx is nothing but change, right? You can take dy by dx, which is differential change, and you can convert that into algebraic change or algebraic difference by writing it as y2 minus y1. Sorry, there's a typo. This should be y1. You can write it as y2 minus y1 divided by x2 minus x1. Now, if you think about it, your Navier-Stokes equation consists of terms such as d rho by dt, d by dx of rho u, d by dz of rho w, and so on. So if we are able to write algebraic approximations for each of these terms, then we will be getting our set of linear equations. So let's do it for one term. So let's assume that we have a function, right? So this red line represents a function with respect to x. So these are 2 points of interest where the value of the function is f1, and here the value of function is f2. Now the x location at which the function value is f1 is called as x1, and similarly at x2 the function value is f2. Now if I try to compute the slope, which is also called as a tangent, it's going to look something like this, right? So how do I compute the slope for it? Well, I can just evaluate the value for dy by dx. So that is one thing. Now say that the quantity f1 is already known. If you know the value of a function at a particular location, how would you determine the value of the function at a different location? Well, this is where we can employ Taylor series. We know that f2 is equal to f1 plus df1 by dx plus some constant time d square f1 by dx square plus some constant time d cube f1 by dx cube, and so on. So here, if delta x tends to 0, I can ignore the higher order terms, and looks like I made a typo. I forgot the dx term, so I've included that. We get this expression, and if I move f1 to my left hand side, I basically get the equation f2 minus f1 is dx times df1 by dx. Now if I take dx to the denominator of the left hand side, I have f2 minus f1 by dx is equal to df1 by dx. And there you go. This is basically an approximate equation which takes differential change and converts that into algebraic difference. Now the reason why I called this as an approximate equation is because we ignored the higher order terms. So these two quantities are not exactly equal, they are only approximately equal. But in the process of deriving that approximate equation, we have converted the differential equation into a linear equation. Now just to rearrange it, I can basically say df1 by dx is equal to f2 minus f1 by x2 minus x1. Now this right here is a linear equation, and a computer is going to be very happy to solve it. So what are the steps in CFD? Well, the first thing is you have to discretize the equation. In the previous example, we showed you finite difference method. In addition to this, there are finite element methods and finite volume methods that can be used to derive discretized equations, which would essentially be linear equations. The second thing is to discretize your domain. So this is where you split the domains into either nodes, elements, or volumes. And this is also called as creating a mesh. Once you have done that, you can solve the linear equations. Now these are the three things that a computer can help you with. You can either use a software package like ANSYS, or you can write your own computer programs using programming languages such as C or C++. So once you have done that, analyzing the results, getting the data for engineering from the results, performing any design changes or validation, and if the design is good, communicating that to the product development team and moving on to the next problem, right? All these things are done by the engineer. So you need to understand that CFD would be a great tool, but if you don't have knowledge regarding a particular application, then you might not know what to do with the CFD software or the CFD program that you might have. So we have talked about governing equations, we have talked about discretization. Is that all there is to CFD? Now it turns out that in order to capture certain important key physical aspects that occurs in real life, you have to solve more equations. For example, to capture the effects of turbulence, typically a turbulence model is used. A turbulence model is nothing but a set of equations that govern the conservation of quantities called as turbulent kinetic energy and turbulent dissipation. If you have these equations, they would also be part of your governing equations, and when you solve it, you can basically look at the effect of turbulence. Similarly, if you want to simulate combustion, you basically need to solve an equation for that, which is called as the species transport equation. Similarly, if you want to look at the effect of fluids and structures together, you need to solve Newton's second law on the structural side to basically get the solid, to basically get the motion of the rigid body, and couple it with your fluid solver. If you want to capture the heat transfer on the solid side and the fluid flow on the liquid side, you basically do something called as conjugate heat transfer simulation. So this is where the liquid side is going to basically help you get the convective heat transfer part, and the solid side is going to be used to capture the effect of conduction, right? So in other words, in CFD, in order to capture a particular physics, you have to always make sure that you have the right equation. With just mass, momentum and energy, you can just perform fluid simulations. If you want to capture solid heat transfer, then you need an equation for that. If you want to capture turbulence, you need equations for that. If you want to simulate sprays, you need equations for that. If you want to simulate combustion, you need equations for that. So this is an important step that you need to remember, especially if you are beginning with CFD. You always start with the question, hey, what is the physics that I'm trying to capture? And then for each of the individual physics that you're trying to capture, you have to figure out what is the equation that needs to be solved. Once you have that set of equations, you then go ahead and set up the required parameters for that particular equation. Finally, you would need something called as boundary condition, which basically tells the computer what are the values at the boundary of the computational domain. This is very important to get an unique solution, because at the end of the day you are solving differential equations. In order to get an unique solution, you need to basically provide the boundary conditions and also the initial conditions. The number of boundary conditions obviously depends upon the number of equations that you're solving. In addition to this, there are things like steady simulations and transient simulations. Steady simulation is where things are not going to change with respect to time, so the time derivative is essentially zero. Or you can perform transient simulations if you're interested in capturing the effect of time on a particular variable. Alright, so now let's build our own simplified CFD solver. So here, this is the governing equation that we are starting with. Now you can see that this equation is very similar to what we had in our one-dimensional steady state heat equation. In the one-dimensional equation, we just had d square t by dx square is equal to 0. In two dimension, you just have another term to capture the curvature or the second order derivative in the y direction. So this right here is the equation. Alright, so now what you can do is you can take these two terms and you can convert that into a linear form and then solve it using a computer. So let's basically take a look at how this is done. Now this is my original differential equation. So what I'm going to do is I'm going to use Taylor series first, right? So for example, what does Taylor series do? Well, if you know the value of, say, the temperature at a particular location, say x, you can actually figure out what is the temperature in the neighboring location, which you can call as x plus delta x. And similarly, you can use that temperature to estimate the temperature value at x minus delta x. Right, so here the temperature would be T x minus delta x, and here the temperature would be T x plus delta x. And at this point, this is temperature at x. So T at x plus delta x. So what is it going to be? Well, it's going to be T at x plus dt by dx measured at x multiplied by delta x plus dou square t by dou x square computed at x delta x square by 2 factorial plus dou cube t by dou x cube at x delta x cube by 3 factorial and so on. Similarly, t at x minus delta x is going to be tx, and the alternating terms are going to be negative, plus dou square t by dou x square delta x square by 2 factorial, and then minus, we essentially have the same term. Now what I want to do is, if I can call this as equation number 1 and this is equation number 2, I want you to add this. So when you add it, you basically get tx plus delta x plus t at x minus delta x is equal to 2 times tx, and these two terms are going to cancel out, plus 2 times dou square t by dou x square into delta x square by 2 factorial. Plus you have all the higher order terms, right? So now what I'll do is I'll just ignore my higher order terms, and what I can do is I can just simplify this a bit. So this 2 and 2 factorial can cancel out each other. So I have tx plus delta x plus tx minus delta x, and if I move this 2 delta x to the left hand side, I have minus 2 times minus 2 tx, and this is going to be equal to dou square t by dou x square times delta x square. So I can simplify this further. I can just say Tx plus delta x minus 2Tx plus Tx minus delta x divided by delta x square, and this right here is dou square T by dou x square. Now this is an approximate equation because we obtained it by neglecting some terms. Now I'm just going to simplify this equation a bit more so that it's easy to remember. So if you remember, x is basically the center point and x plus dx is the point on the right hand side. So if I go to the graph here, you can see that if this is your point at which you're looking at temperature, this is the right hand side point and this is the left hand side point, right? So I can basically say that this right here is T right minus 2Tp plus T left by delta x square, and this is going to be d square T by dx square. Now you can kind of use the same concept to derive d square T by dy square, and the result is going to be T top minus 2Tp plus T bottom by delta y square. Right? If we add this, we get our original differential equation, right? So I'm going to say that T right minus 2Tp plus TL by delta x square plus T top minus 2Tp plus T bottom divided by delta y square is equal to dou square T by dou x square plus dou square T by dou y square. And if you look at the original governing equation, we know that this term is equal to 0. And the other assumption that I'm going to make is I'm going to say that delta x is equal to delta y. So what I can basically do is I can say that delta x square is equal to delta y square, and I'm just going to call both of them as delta x square. So Tr minus 2Tp plus TL plus T top minus 2Tp plus T bottom divided by delta x square equal to 0. So if you simplify this, you would get T right plus T left plus T top plus T bottom divided by delta x square is equal to 0, and then you have minus 4Tp in the numerator. I can take delta x square to the other side and it becomes 0. So essentially I will have Tr plus TL plus Tt plus Tb is equal to 4 times Tp which means that T at point is equal to Tr plus T left plus T top plus T bottom divided by 4. And this right here is my governing equation, and you can see that that is what I have done. So alright, so now that we know what the governing equation is, what the discretized equation is, how do we actually simulate this problem? So this is where I wanted to introduce a simple tool for you. So this is essentially a CFD solver that's built on Excel. So what I've actually done is I've basically taken my rectangle and I've divided my rectangle individual cells. So each and every element here is a cell, and this right here is basically what you call as a discretized domain. In the real world, this could be a rectangular plate, it could mean anything. But here we are dividing the rectangular plate into individual volumes or elements, right? And inside each and every element, there is just one value of temperature, right? Though this element is big, the temperature value does not change. You just have one value of temperature. And you can see that certain cells in our mesh are colored in gray. So these are your boundary conditions. Your boundary conditions do not change. And you can see that for all the cells that are actually in the inside of our mesh, there is a starting value. And this starting value basically dictates the initial conditions. Now if you basically look at any of this particular cell, let's take this cell, if you look at the formula, right, the value at that center point is equal to value in the left hand side, top, right and bottom summed together divided by 4, which is exactly the linear equation that we derived. And you can look at any of the nodes that are on the interior. If you just double click on it, you can see that the value at this point is equal to the value at the left hand side cell, which is G10, plus value in the top cell, which is H9, plus value in the right hand side, which is I11, and I10, and then the value of the cell in the bottom, which is going to be H11. Alright, and this right here is what you would do in CFD. In this case, the domain is very simple, it's rectangular. But if you take a battery pack, the geometry is going to be much more complex. So for example, what's going to happen if the top boundary condition is changed to 900? So when I change to 900, you can see that the values are all changing. So I'm iteratively solving the temperature in all the nodes so that we basically get the condition that, you know, temperature at each point is the sum of all temperatures in the neighbors divided by 4. And you can see that the boundary conditions do not change. They are always the same. The corner points can be ignored. It really doesn't matter what you put in the corner because that's not used into the calculation at all, because if you look at this cell, it uses only the top, right and bottom points. It does not include the top, right and corner point. So we are okay. And you can see that the moment I change the value from 300 to 900, I'm getting a graph which basically shows the variation. And this is what you would call as post-processing. So whenever you do CFD, you basically start with discretized equation, then you discretize the domain, you have an equation, governing equation that you want to solve, and then you have boundary conditions. Then you post-process the results. But the other key part of post-processing is understanding what we are trying to say here. Though I'm seeing a bunch of numbers, it really doesn't mean anything. So what I'm going to do right now is I'm going to introduce a color map. I'm going to click on format and I'm going to select conditional formatting. I'm going to go to color scale, and what I'm going to do is I'm just going to click on this guy and I'm going to apply this color scaling. Immediately you can see that there are some nice colors. I'll explain what those colors mean. I'm going to say that if it is 300 Kelvin, the color should be green, and if it's 500, it should be yellow, and if the temperature is say 900, it should be red. And you can immediately see how heat transfer takes place in this particular case. The top domain, the top of your rectangular plate is heated up, and you can see that the temperature values are very high. And what you can do is with this simple calculator, you can do a lot more changes now. I can now change the temperature of the right side boundary, right? So let us change that to 500 Kelvin. You can see that it's immediately iterating, and your temperature distribution along the midway of the rectangular plate has now modified, and you get a new contour, right? So this essentially is basically the fundamentals of CFD, right? You basically have the geometry, which in this case is just a rectangle. Then you select the discretized equations. Then you select the equations that you want to solve, which in this case is just a 2D heat conduction equation. And then you mesh the geometry, which we are luckily able to do because of Microsoft Excel, which is already a cell-based software program. And then we provide boundary conditions, initial conditions, and we iterate. You can see that it takes a certain amount of time for the solution to change. And a good way to look at that is, if I set this back to 300, you will see that the graph continuously changes, and after some point, the graph stops changing, but the numbers are still changing, right? This is essentially saying that the results are converging, and that's a very good indicator. So for example, if I change this back to something like 800, you can see that the graph changes, but then at some point it stops changing, but the solver is still trying to solve it to a higher value of accuracy, right? And this is where things like residual and things like iterations come into play. But overall, it doesn't matter how complex of a model you take and simulate, all these fundamental concepts have to be followed in that simulation as well, right? It doesn't matter if you're simulating a battery pack with thousands of cells. It doesn't matter if you're simulating a fighter jet. The fundamental principles behind performing computational fluid dynamic analysis is exactly the same. You need the geometry, you need to mesh it, you need to select the governing equations, you need to provide the initial conditions, boundary conditions, solve it, and then finally post-process it. Alright, with that I would like to conclude this video. I hope through this video you learned the fundamentals of computational fluid dynamics. I'll see you guys in the next one. Bye. Hey guys, hope you're all doing good and welcome to a new video. In this class, you will be learning how to perform simulation of a simplified battery thermal management system. So the geometry has been shared with you and the boundary conditions will be discussed in this particular lecture. We will be going over how to set up this problem from scratch. As I'm setting it up, I'll be explaining the thought process behind several model choices that I'm making. Now, please do remember that this is an introductory level course, and hence I will not be able to go in depth with respect to physical models that's being used and the math behind them, right? So I want you to kind of trust me with the model choices that I make. All right, so that being said, let's get started. All right guys, so let's go over the learning objectives of this video. By the end of this video, you will definitely be a bit comfortable about using ANSYS Fluent to simulate battery thermal management systems. Right, so in this video I'll explain the problem statement, make sure that you understand the boundary conditions and initial conditions that are required for the problem. You will be able to understand what type of material properties has to be provided, and then you will be able to understand what additional physical models that we use for this simulation. And finally, by the end of this video, I would have given you a full demo of how to set up a basic BTMS simulation from scratch, and we'll take a look at some results and discuss those results. So most of you might already know what ANSYS Fluent is. It's a very powerful computational fluid dynamics software and can be used for a wide range of CFD applications. In this particular video, I will be demonstrating how you can simulate the flow through a simple BTMS that is shown here. In this case, it has 5 cells. This is going to be the inlet. So air is going to come through the inlet, and as it actually interacts with all these cells, it's going to remove the heat that is generated from these cells by forced convection. Our idea is to understand what the steady state temperature is going to be of these cells when the incoming air is flowing at a particular velocity. Now the heat generation in the batteries is modeled by a constant volumetric heat source. So you would essentially say what is the volumetric heat source per cell, and volumetric heat source as a unit of watts per meter cube. So you will be calculating the volumetric heat source for this final project. As far as the boundary conditions goes, the inlet velocity is assumed to be 3 meters per second, and the other thing that you need to calculate, as I mentioned in the previous slide, is the volumetric heat source. With respect to material property, I'm going to assume that my solid cell is made up of aluminum, so the thermal conductivity and specific heats of aluminum will be used. Now, is this correct? Well, that is something that you are going to be figuring out as part of your project. You should also figure out what properties are needed to model the cell correctly, and you need to kind of evaluate if the original assumption that I have made is correct or not for this particular problem. As far as physical models are concerned, since we are interested in the steady state temperature distribution, we are using a steady solver, and we are basically using something called as a density based solver. Now typically for CFD there are 2 types of solvers, density based solvers and pressure based solver. Since this is an introductory course, we are not going to be talking about how density based solver and pressure based solver works. So the only thing that I want you to remember is when the Mach number of the flow is greater than 0.3, it is always better to use density based solver. In fact, if you are dealing with air, it's fine if you use density based solver. If the velocity is a bit low, then it might take a bit more time, but your solution is guaranteed. So that being said, with respect to ANSYS Fluent, you can actually use the pressure based solver for even high Mach number flows, up to 3 to 5. However, for the purpose of this tutorial, we will be sticking with the density based solver. Energy is turned on. So when we say energy is turned on, that means energy equation is also being solved. In addition to this, we are also simulating turbulence by enabling the standard K-epsilon turbulence model. So as far as results, before we jump and run the simulation, I kind of wanted to show you a sneak peek of what you can expect. So here you can see that these are the governing equations that you're solving. Continuity equation for mass balance, xyz velocity, which is nothing but xyz momentum conservation equations, energy, one equation for turbulent kinetic energy and one equation for turbulent dissipation. In the graph, x-axis is the iterations and y-axis is the residual. In general, you want to make sure that your residuals drop. That alone is not going to be the criteria. You should also look at some type of physical quantity. For example, here I'm looking at the volume average of temperature across all my solid cells, and I'm plotting that as a function of iterations. You can kind of see that somewhere after 350 or 375 iterations, the results don't change much. And this is what you call as convergence, right? So you can see that the results deviate less than 5%, right? So that tells you that for this particular operating condition, if you run the problem for 450 iterations, you can expect a steady result. Now keep in mind that this observation has to be made for each and every CFD problem that you might simulate in the future, because you never know for which problem how many iterations are required. Alright, so that being said, let's get started with ANSYS Fluent. Alright, so here I've opened ANSYS Workbench 19.1 and I'm going to select Fluid Flow Fluent and I'm just going to drop it to the canvas here. Right click on Geometry and select New Space Claim Geometry. Alright, so once Space Claim has opened, click on File and click on Open, and you will be loading the BTMS geometry file that has been shared with you. Please note that the extension is SCDOC, which means that this is a space claim file. So once we open it, you would basically see a model tree which contains something called as component 2, fluid volume and cell. So let's take a look at each of these individual components. So the cell refers to the individual cells that you have. The fluid volume basically refers to the volume that's occupied by air, and you can see that the fluid volume has cutouts for the volumes that the cell occupies. And then you have something called as component 2, which is the casing, right? So this is the casing that's basically holding the entire fluid volume and the cells, which we don't want for this simulation, and that's why you can see that this has been suppressed, and you can see that there's a cross mark here. So we will need only fluid volume and cell. Now space claim is an amazing parametric CAD modeler which can be used for geometry cleanup and geometry preparation for CAE simulations using ANSYS products. Now in this basic course, we are not going to be diving deep into how geometries can be created, and hence once you have completed this step, you can close space claim. So the next thing that we are going to do is meshing, so I'm just going to double click on it. Alright, so looks like the geometry has loaded. Rename. The first thing that we want to do is we want to create named selections. So we are going to name the inlet and outlet boundaries so that we can apply boundary conditions in ANSYS Fluent. So I'm going to use the face select option, left click on this particular face and then use right click and select create named selection, and I'm just going to type in inlet. Now to rotate the geometry, use the middle mouse button and just turn the geometry. Click on this face, left click on that face, use the shortcut key N and type in outlet. Alright, so now what we want to do is, we know that the gray body is the fluid volume. So I'm going to go to the body select option, click on this guy, use the shortcut key N, and I'm just going to call this as the fluid volume. And while the body is selected, right click. Looks like I lost the selection, so let me select it again. Right click and click on hide body. So this move will expose the cells that are present. Use Control plus middle mouse to pan, and use the middle mouse to zoom. And what I'm going to do is, I'm going to make sure that body option is selected. I'm going to left click, hold my mouse and just drag over all the individual cells. While doing this, make sure that you do not let go of the mouse pointer. So let's try it again. Left click to unselect everything, left click, hold, drag over all the cells and then hit N and create a new named selection, and we are just going to call this as solid cells. Then click on the mesh option and make sure that physics preference is set to CFD and element size is set to 5. So now right click and click on generate mesh. So you can see that the mesh is generated, but we are able to see only the solid cells. So right click anywhere and click on show all bodies. So here you can see that we have a tet mesh for the airflow and we have mostly hexahedral cells for the solid cells. I'm going to use the section plane icon. Click and left click anywhere and just don't let go of the left click. Drag it over the screen to create a line. So this line is essentially indicating a plane that's going to cut the geometry. Right, you can see that the geometry has been cut. Use the middle mouse button, click and rotate the geometry, and you can see how the mesh has been cut. So right now I have not cut it deep enough. I'm just going to enable the section plane. Look at the geometry like this. Click on new section plane and cut it like this. So now you can see the interior mesh, and here you can see that we have separate mesh for the solid cells and we have a separate mesh for the fluid cells. This right here is what you call as an hexahedral cell, whereas this is what you call as a tetrahedral cell. Now what I can do is I can click on show whole elements, and that is essentially going to tell you, that is essentially going to render the entire mesh. So if you look at it, you can kind of see that the entire thing is divided into volumes and information is shared from volume to the other volume, right? Which is kind of the basis of finite volume method. So now I'm just going to uncheck the section plane, and I think everything looks good. Let's make sure that all of my named selections are there, and I'm just going to close ANSYS Measure. So let's right click on mesh and update so that the mesh information is updated. Alright, so looks like the setup is complete. So now what we are going to do is we are going to right click on setup and click on edit. This is going to open the Fluent launcher. Select double precision, select parallel, and I'm just going to use up to 4 processes to run the simulation. Alright, so looks like the mesh has been loaded into ANSYS Fluent successfully. So the first thing that I want to do is make sure that the solver is set to density and time based, and make sure that steady is selected. So the way ANSYS Fluent works is fairly simple. You would basically work your way from left to right, and whenever required you would basically fill in the details in the model tree. So if you rotate the model, the inlet is colored blue and outlet is colored red. This information is automatically obtained when we created named selections. So let's go to setting up physics, and let's make sure that energy solver is turned on. Click on viscous and select K epsilon. You can see that the standard K epsilon model is automatically selected. The next thing that we are going to do is we are going to go to cell zones. So here you can see that the fluid volume and solid volumes are shown. Fluid volumes type is fluid because the name fluid is found there. ANSYS Fluent can do that automatically. Similarly for solid cells, you can see that the type is solid. So let's click on edit, and I'm going to add source terms. Click on source term panel, click on edit, and let us say that we're going to have one source, and I'm going to say that this is a new input parameter, and I'm just going to call this parameter as volumetric underscore heat underscore source, and I'm going to initially set it to 0, and I'm just going to click on OK and click OK again, click OK again. So then we are going to go to boundaries. Here we first select inlet, we click on edit, and for velocity magnitude I'm just going to click on this drop down and select a new parameter. I'm just going to call this as inlet underscore velocity, and I'm going to set the initial value as 3 meters per second. That's basically what you need to do. You don't have to change anything else. If you're curious about the outlet boundary condition, you can see that it's a pressure based boundary condition, and we essentially say that the gauge pressure is actually 0 at the outlet. So let's click on OK. So the next thing that we want to do is, while solving the solution, we want to basically take a look at the volume average of temperature across all the cells. So this can be done via reports. So as you're solving, you want some reports. So let's click on definitions, select new, select volume report, and let's select volume average. And the report by default is going to be called as report underscore def 0. That's fine. I'm going to make sure that the field variable is temperature, and I'm going to be selecting static temperature. I'm going to be computing it only for my solid cells, and I am going to say that this is an output parameter. So the input parameters are velocity and volumetric heat source, and the output parameter is going to be this volume average temperature. So let's click on OK. Then comes initialization. So let's select standard initialization, and I'm going to basically set the number of iterations as 500, and I'm going to hit calculate and click on yes. You can see that the simulation has started to run, and the residuals are almost flat and they're slowly dropping, but we are not seeing the volume average plot, right? So what I'm going to do is I'm just going to click on stop to stop the solution, click on OK, and we have to make sure that we hit the plot button here, and we need to make sure that we select the report that we want to plot. So click on new. It's automatically going to show you the report that you want to plot. Select it, and you can see that it's going to create a new plot window, and it's going to plot every iteration, which is what we want. And I'm just going to say OK, and I'm going to close this guy. So now you can see that we have already run like 55 iterations. Now if I basically hit calculate again, it's going to run for 500 more iterations, which is fine. So let me hit calculate, and you can see that it prompts a warning message, and I'm going to just say that we want to use the settings for current and future calculations. So let's click OK. Okay, so the plot window is not appearing. So what I'm going to do is I'm just going to click on stop one more time, and I'm going to reinitialize the solution. So that way I delete all the existing data, and I'm going to run the simulation from first. Okay, for some reason the plot is not appearing. So let me just try this one more time. I'm just going to click on stop, and I'm just going to click on OK, and I'm just going to click on plot again, and I'm just going to delete this guy, add a new plot. Select this, let me just add it to the right hand side, and I'm also going to select print to console. So I think maybe last time I forgot this step, but I can't recall. So let me just click on OK again and close this guy and hit calculate to see if the window appears. So I'm just going to use the second option, click OK. There you go. So the plot appears, and you can see that the volume average of temperature is 300, right? And that is kind of expected because we are not seeing any changes with respect to the source, right? The volumetric heat source is 0, so there is no reason to believe that any heat is going to be generated. So I'm just going to wait for the simulation to run for 500 iterations, and till that time let's take a look at the scaled residuals. Alright, so looks like the calculation is complete. So let me just click on OK. And I'm just going to close ANSYS Fluent. Alright, so now would be a good point for me to just save the file. I'm just going to call this as BTMS demo. Alright, so now what I want to do is I want to take a look at the results. So what I'm going to do is I'm just going to click on results, and this is going to open a new program called as CFD post. Alright, so this is CFD post, and you can see that the geometry has been loaded and certain components are not visible, which is perfectly fine. You can always enable them by just clicking on it. So here I can basically look at the solid cells, right? And let's color the solid cells. So I'm just going to double click on them and go to color, and I'm going to select variable, and I'm going to select temperature, and just click on apply, and you can immediately see that the battery pack is colored. And it kind of makes a lot of sense that the first battery is the coldest and the last battery is it kind of makes sense because the first battery gets cooled easily because the second battery is behind the first battery, right? So it doesn't experience the same amount of airflow. And if you just extend that logic, the fifth battery is going to be cooled the least. But that being said, you should look at the color scale range. We are just talking 1 degree Celsius in temperature change. That's because we are not generating any heat. So let's also create a cut plane to kind of understand how the mesh looks like. So click on, and by the way, to rotate, it's left click. To zoom in and out, it's basically the middle mouse button, and if you hold on to control, you can pan it, right? Essentially it's the same control. So I'm going to click on location and I'm going to add a plane, and let's click on OK, and I'm just going to create an XY plane, right? So this is the XY plane, and let's just click on apply, and you can see that that's where it cuts the geometry. What we can do is we can click on the Z coordinate and just slide it to see how it actually moves, and you can set a specific number if you have that in mind, right? I'm just going to cut it so that it kind of cuts the cells exactly in the middle, at least as close as possible, right? I think that's good. And I'm going to just hide the solid walls for a second, and I'm just going to be looking at the plane, and I'm going to just color it by, say, the velocity. Right, so here you can basically see how the velocity flows. You can basically see the velocity field, and as expected, you can see that between two cells you have a pocket where the velocity is very low, right? Which is kind of expected, and that is why the second cell is cooled less, the third cell is cooled even more less, and so on. In the render option, I'm just going to click on show mesh lines, and I'm just going to apply. And you can kind of see both your solid mesh and your fluid mesh. So you can see that inside your solid there is no velocity, right? Because it's made up of solid, and that's why there is no colors there. And outside you can actually see the colors, right? So you can do a lot more post-processing. Feel free to just play with it. One thing that looks very cool that a lot of students ask me how to do is creating volume renders. So the first thing I want to do is hide the plane, and I'm just going to click on this option, which is the volume rendering option, and I'm going to select velocity, and let's just click on apply. This is essentially going to show you how the 3D velocity field looks like. To increase the resolution, I'm just going to bump this parameter to 64. Now this is going to take a bit more time to load, but you can see that the results look much more smoother, and I'm going to just increase the transparency a bit so that you can kind of see what's happening inside, right? So you can see that there are local areas where the fluid seems to be getting accelerated, right? Which kind of makes sense wherever the area of cross section is minimal, right? So when the fluid is going through this path, this is where the area of cross section is minimal, and that's where fluid tends to accelerate, right? So visually or qualitatively this seems to check out. So it seems like we have a reasonable model to start with. So I'm just going to close this guy, and I'm just going to click on the parameters that we created. So you can see that I've created a couple of parameters, volumetric heat source, inlet velocity, and this is the output, right? 300.04 Kelvin. So what I can do is I can now say change the heat source values to 30,000 watt per meter cube, and I'm just going to maintain the same velocity. And let's just click on this guy. I'm just going to retain the result. I'm going to select here, and I'm just going to right click, and I'm going to basically say update selected design points. So Fluent is automatically going to use these values, and it's going to update the setup, and it's going to run the simulation, right? The status can be seen in the bottom left corner. And again, it's going to run through all the 500 iterations, and it's hopefully going to obtain a steady result. So we are just going to wait for this to finish. So I'm just going to pause the video till that time. Alright, so looks like the solution is complete. So what I can do is I can just right click on this, and I can set this as the current design point. So now if I go back to project, and what I can do is if I just click on the results again, this time hopefully it should open up design point 2, where the temperature variation should be slightly higher than what we saw before. But all the views, the volume renderings, should be preserved. Alright, so let's kind of enable the plane, and what we are going to do is we are just going to hide the volume rendering, and I'm just going to select the plane, and I'm just going to make sure that I color it by the temperature. Click apply, and you can see that now the cells are substantially hotter. What you can do is you can play with the range a little bit. You can set up a specified range, so the minimum should be 26 and the maximum should be 30. Let's click on apply. Alright, so now you basically see that this is the new temperature distribution across the cells. Alright, so let me just close this guy, and what I'm going to do is I'm going to run one more design point, which is basically a much more higher value of source, and see how the temperature looks like. And I'm going to add a new value of source, so I'm just going to try 3E5 instead of 3E4, and I'm going to again run 3E5, but this time what I'm going to do is I'm just going to change the inlet velocity to 4 meters per second as well. And we would want to retain all the results, and I'm going to select two cells at the same time using the shift key and right click, and there's an option called update selected design points. So I'm just going to click on this, and okay, so looks like I might be facing a licensing error, so I'm just going to give it a minute to see if it resolves, else I just have to restart it and submit it. In the meantime, I wanted to show you how you can calculate the energy density. So here I'm basically looking at the diameter of each and every cell, right? So you can see that I have one cell where the diameter is 0.01 millimeters. Sorry, this is actually in meters, right? So that's going to be 10 millimeters, and the length of the battery is 50 millimeters or roughly 5 centimeters, and we are saying that there's 2000 joules of energy in that particular cell. Ideally you'll have to look at the specifications of a battery to understand what its capacity is, what its energy capacity is, and then what we can basically do is we can calculate the volume, right, of the battery, right? So volume is just pi by 4 d square into h. So I calculate the volume, and what I'm basically saying is I'm saying that this energy is expensed in 3 hours, so the total seconds would be 10,800 seconds. So then what I basically do is I calculate power as energy divided by time, and power density is nothing but power divided by volume. Now ideally you have to multiply this by the number of cells that you have, right? But again, this is just a made up calculation, the numbers are all made up. What I want you to do as part of this project is I want you to measure the dimensions of the batteries using space claim, and I want you to basically figure out what should be the energy input, what is the right assumption for the time parameter, and then calculate the power density accordingly. So let me just head back to ANSYS workbench, and it looks like the calculation is still in progress. So I'm just going to be pausing the video, and once the results are up, we can take a look at it. Alright, so looks like the solution is up, and you can see that for the same value of each source, when I increased the inlet velocity by 4 meters per second, the temperature did drop by 4 Kelvin, right? Okay, so that's basically how you would simulate a battery thermal management system and then run parametric analysis. So let us assume that the model that we had was a highly accurate computational model of a complex BTMS. Then we can essentially try out different strategies, right? We can basically increase the inlet velocity, and you can actually look at several other quantities such as variance or standard deviation in temperature to understand the non-homogeneity in the temperature, right, in your battery pack. Okay, so that being said, based upon this video, we will be giving you a detailed final project. Take a look at it, and I hope you found this video. Alright, thank you guys so much. Bye.
Hello friends, welcome to the series of courses on basics of electric vehicle simulations using ANSYS. In the second part, we are going to learn about EV motor sizing and motor drive analysis using ANSYS software. Let's first start about this course, what this course is going to include and what are the things will be covered in this course. And we will also see what is the approach for this course. So let's understand about what this course is about. So this course is beginner level discussion on electric motor used for vehicle propulsion. So this is a very introductory level discussion for motor technology. What is the approach going to be used for this course? So the approach here is going to be outside in. So first we are going to take the outside approach and then it will be followed by inside of the system. And here we are going to consider the motor as a system. So initially we are going to consider motor as a black box, and then later on we will see what is the design of a motor and how to step by step carry out the design of a motor. The approach also transfers from basic mathematics, here I will call it as a napkin mathematics or very fundamental maths behind the system, and then we will later on switch to the software based design. So if I give you an analogy of the approach, so this is just an image showing that what exactly we are going to learn in this course. So initially we will be having a look at the entire picture as a big picture or bird's eye view, and then we are going to dive into electric motor for electric vehicle application. Let's start about what are the course contents and at the end of the course what you will be learning. So as I explained, it is introductory course on electric vehicle motor technology, and these are the list of the topics which will be covered in this course. So you will be learning about motor power estimation for EV application. Then you will be learning about motor sizing and factors affecting the choice of propulsion motor. So these are the two important points highlighted over here: motor power estimation and motor sizing. So here I am considering these two as separate things. The next topic which we are going to cover in this course is analytical design of permanent magnet synchronous motor using ANSYS RMxprt. So permanent magnet synchronous motor is one of the popular motor for electric vehicle application, and we are going to see the design of this type of motor using ANSYS software. We will also do the performance analysis of the design motor using ANSYS Maxwell software. So ANSYS has two different modules. One is called template based design and one is based on electromagnetics. So we'll see both. We'll start with the template based design for ANSYS RMxprt and then we will switch to ANSYS Maxwell. So the major fundamentals which we are going to cover in this course are related to motor power estimation and motor sizing. So you might be having a question that what is the difference between motor power estimation and motor sizing? So sometimes it is referred as the same phenomena or same concept, right? But here for this course I would like to make a clear difference between these two. So in some of the cases it may be the same, but here we are not going to consider it same. So what are the important terminologies and how motor power estimation is different from motor sizing? So let's have a look at first motor power estimation. So what do I mean by motor power estimation? So motor power estimation deals with what is the duty of a motor, what motor is required to do, right? What motor is supposed to develop, right? And that is going to also lead to our discussion on estimating the speed and torque on the shaft of the motor. So motor power estimation is basically considering the motor as a black box exercise, and we will assume that all things inside the black box is able to receive input and provide the necessary output. So for a motor, what are the inputs and output? So input is electrical energy and output is mechanical energy. So motor converts electrical power to mechanical power, and we assume when black box approach is taken that input voltage and current quantities are available and output speed and torque are produced. So we are going to understand motor as a black box in motor power estimation. So this is what is the meaning of motor power estimation. If I give you a quick example, let's say you want to actually calculate how much is the power rating of a motor required for the pump which is going to change the level of the water from the ground tank to the top tank. So if you have a 3-story building and you want to have a motor which is going to pump the water from underground tank to overhead tank. So what is the important parameter over here? What is the amount of force required for the water to pump from underground tank to overhead tank? So this is something very much required as a first step for motor power estimation. So water pump motor is just an example. We are going to discuss about an electric vehicle, and we will understand that what kind of duty or what is the role of the motor that it has to play. So the second part is motor sizing. Now, what is the meaning of motor sizing and how is it different from motor power estimation? So in this course, we are going to treat these two as separate terms. In some cases, it may be similar. So what is the meaning of motor sizing? Motor sizing is basically getting the idea of physical size of the motor. What do I mean by physical size of a motor? It means what is the diameter and length of the motor. So usually the motors are of cylindrical structure and they are defined mechanically as dimension and length, right? And fundamentally the motor sizing is nothing but how the required power is actually going to be kept inside the available volume of a motor. So motor sizing is the exercise which deals with determining how much volume will the motor will require, or if for a given volume how much power will the motor be able to produce. So when it comes to calculation of power, we are going to consider the motor as a black box, and when it comes to motor sizing, we are going to dive deep into what is inside the motor, right? But as a very first step, what we need to do is we need to translate this motor power to the motor sizing, right? So that is going to be the first step, where we have a predefined value of the motor power estimated, and for that power indirectly the speed and the torque, and we will be then focusing on how the machine can be designed. So this is what we are going to cover in this course as important terminology. Let us move ahead and learn about the vehicular electrification. So here I am going to talk about the fundamentals of vehicles, and it's going to be somewhat related to history and background of vehicles. So in the first video, we are going to learn the fundamentals of electric vehicles as well, and so that it will be easy for you to understand about motors used for electric vehicles. So let's try to understand from the motor perspective what is vehicular electrification. So electric motors are required in most of the IC engine based vehicles as well. So you might be wondering, where do I need a motor for an engine based vehicle? Because the propulsion power is produced by the engine. Why do I need a motor? Right? So you might think of some applications where, for example, in your car, you may require motors for power windows, you may require motor for wiper, and maybe some other applications for HVAC. So heat, ventilating and air conditioning, that may also require some motors. But actually I'm not talking about those motors. I'm talking about the motor which is very, very important. Can you guess which motor I'm talking about? And yes, it is present in all IC engine vehicles. It is the motor called as starter motor. So electric motors are basically very old friend of an engine, right? And even if you consider other engines in other applications, most of the engines will be starting with the help of electric motor, which is called a starter motor. So let me show you an interesting picture of a starter motor for a two-wheeler engine by Honda. So what you are able to see in this image is basically a cut section view of a two-wheeler engine. So here is the silencer at the end of this, and here is where your piston will be. What you are able to see over here is the starter motor, or it is also called as integrated starter generator for a two-wheeler engine. So this is around 100 to 150 cc engine producing up to below 10 kilowatt power. This type of engine requires a motor to start, and this is what you call as auto start, right? So when you have a vehicle where the engine is started using the battery power, and then the same motor will be acting as a generator. So this is what is inside all IC engines, right? So all IC engines are by default started with the help of motor and battery, or we can consider this as electric start. So can we now consider all vehicles as somewhat electric vehicles? Yes, we can call them as partially electric vehicle or electric start vehicles. So if I talk about the next category of more electrified vehicle, right? So that is possible if the size and power rating of the battery and the motor, which are important electrical components, are higher, or if the size and power increases for a battery and motor, it is known as a hybrid electric vehicle, right? So most of the vehicles are by default micro category of hybrid electric vehicle. So even if you consider your purely petrol or diesel vehicle, they are basically micro hybrid electric vehicle. Why? Because they are going to use electric start. So vehicular electrification is very important thing in order to understand what is a pure electric vehicle, and based on what is the size and power of electric system, that will basically define the category of a vehicle which is mild or full or pure electric vehicle. So let us learn about what are these four categories and how these four categories are classified. So these four categories are basically classified on amount of power which is electrical in that particular vehicle. So EV is a special case where it is one of the category of hybrid electric vehicle. So let's understand how EV is a special case of an HEV. Now, in order to understand this, let me show you one important table which is going to categorize the types of hybrid vehicles. So this table shows the functionality of a typical type of hybrid electric vehicle. So for example, a micro hybrid vehicle can help the engine to start, but the regenerative braking and the motor assist is slightly available, and electric drive is not possible. So what is the meaning of regenerative braking, motor assist and electric drive? Let me explain this fundamentals to you. That regenerative braking is basically when the vehicle is decelerating, the kinetic energy stored in the vehicle can be taken back to the vehicle and it can be stored in the battery. That is called a regenerative braking. The motor assist is something which is related to helping the engine to start, and not only to start but helping the engine during the initial speed or low speed operation of the vehicle to achieve higher amount of speed in the first gear. So for example, if we consider the motor assist case, when your vehicle is in the first gear, your motor can not only help to start the engine, but it can also provide power on the shaft such that the vehicle can propel. So another important feature is electric drive. Now, if the electrical system can provide the full power, whatever is the required power for propulsion of the vehicle, if the total amount of power is provided by the electrical system, then it is called an electric drive. So after you have understood all these three important concepts apart from engine start, now you can easily understand the categories of hybrid vehicles. So a micro hybrid vehicle, by default all vehicles are micro hybrid. As I discussed about a start or integrated starter generator for a two-wheeler engine, it is basically micro hybrid. A mild hybrid vehicle is something where the electrical system is going to take more responsibility and provide the regenerative braking and motor assist features. Full hybrid electric vehicle is one such vehicle where electric system can actually contribute independently to the propulsion power. So here there is no need for an engine to actually start. So a full hybrid electric vehicle can run either on engine or on electric system at all. So this is possible in a full hybrid vehicle. Now, does that mean that you have a CNG kit in your petrol vehicle? No, a full hybrid vehicle is basically going to have a complex control strategy where the power sharing is determined by it. So a full hybrid vehicle is something similar to combination of IC engine along with electric, but the overall control is going to be the master control, which will decide which power is required to be used from either of electric or engine. Now, how do we call EVs and HEV? Here is the answer. So for an electric vehicle, the degree of hybridization is 100%. Now, what is the degree of hybridization? In a full hybrid vehicle, if I do not have any engine, right, or if we eliminate the engine and if we take all propulsion power from electrical system only, then it is called a full electric vehicle. So let me give you an equation for a degree of hybridization. So degree of hybridization is defined with this equation. It's electric system power, or we can call it as electric motor power, or it can be a combination of motor and battery as well. So it's the ratio of electric motor power to the total power, where the total power is the combination of IC engine along with the electric motor. So if you consider the degree of hybridization as 100, so this ratio becomes 1. When does this ratio become 1? When you have this IC engine power component as 0. So therefore we can call electric vehicle as a special category of hybrid electric vehicle. So let us move ahead and now try to dive deep into what are the components of an electric vehicle. So this is how an electric car will look like in terms of a transparent image. So what you are able to see here is a front wheel drive electric four-wheeler, where this is a electric traction motor. So we are going to focus on electric traction motor. Sometimes it is also known as a propulsion motor, or it is called a traction motor. So the motor which is responsible for developing the power on wheels, that is called a traction motor or a propulsion motor. So this is what we are going to discuss about in this course. But at the same time, we need to understand what are the other components, right? So there is a motor over here, and the yellow color represents the traction battery pack. So an electric vehicle requires multiple number of cells and modules to be connected in series parallel, and that is what you are able to see here. So there will be a charging port, and the motor cannot directly drive the wheels. There will be mechanical power transmission on the shaft of the motor, which will be basically a reduction gear. And here you have a different system for controlling the motor. So if you have just a battery and a motor, will you be able to run the electric car? The answer is yes, but you will be definitely not able to control the speed of the electric car, right? So in certain applications like an electric forklift and some other applications, there may not be any need of a power electronic converter, but in order to change the speed, in order to translate the voltage and current from one level to another level, we will definitely need power electronic converters. And there are a lot of other systems which are not included in the image, but there will be auxiliary battery in case of failure, or in case of auxiliary power to other systems. It can be used. There can be a thermal system for cooling of the motor and battery systems as well. So this is just an inside view of an electric vehicle. Now what we are going to learn in this course is about electric traction motor. So let me simplify this in terms of a block diagram. So here is a simple block diagram of an electric vehicle. So the arrow indicates the direction of signals or the power flow. So if I explain you the direction of power flow, the battery is going to provide power to the power electronic converter. Now power electronic converter will change this fixed battery voltage into the required voltage of the electric motor, considering the user inputs. So what are the user inputs? User inputs are basically the accelerator and brake pedals. So from accelerator and brake pedals, this power converter will decide how much is the voltage to be applied to the electric motor. What electric motor is going to do with the voltage and current? It will be translating the voltage and current into speed and torque. And now this speed and torque are going to be applied to the vehicle body, which is going to run under the formatted environment, under environmental conditions which are present. So this is a simple block diagram, and here is the red color block highlighted, which is of our interest. So what electric motor is going to provide on the speed and torque, we can actually work in the reverse direction, and we can try to understand what is going to be the motor power rating in case we are considering the specifications for vehicle body and the given environmental conditions. So there are two kind of approaches where you put an electric motor inside a vehicle and try to identify how much is the top speed and how you are able to control the vehicle, right? The other strategy is you actually back calculate how much is the motor power required from the available conditions, right? So basically you observe the motor from the shaft perspective. This is where going to be our eye for the next part of the course, right? So we are going to look at in this direction from the electric motor. So this is a simple block diagram representation, and let's now try to understand about the electric motor as well. So how does an electric motor look like, or what are the features, right? Or which motor is used for an electric vehicle? So let's answer this question. So if I ask you the same question, which motor is right choice for a given EV application? So let's try to figure out an answer for this question. So actually there are no standards yet established for the choice of an EV motor, because there are lot of technology involved in the design of an EV motor. At the same time, this technology is not matured yet, or people are trying with different types of motor. So how do we decide about a type of a motor, and how do we learn from all those types of different motors? How do we come to a conclusion that this is going to be the right fit? So the answer is actually not available, right? So there is no right motor for an EV application. Why we don't have any standard motor for an EV application? So for example, if you take the application of a pump, so if you have a water pump which is going to change the level of the water from underground tank to overhead tank, people will usually prefer single phase or three phase induction motor. Now that is a quite mature application, and the motor is also quite rugged, right? Or it's quite known that we have usually single phase or three phase supply available as outlet, as a power outlet, and we know that this motor will be easily able to perform the task. Now what is the case in electric vehicle application? So let's try to figure out the answer for this question. So actually the customized motor design is preferred. So there is no standard motor which you can take and place inside the electric vehicle. In order to satisfy the EV requirements, the customized motor design is preferred. So there are actually many choices within the same category of a vehicle, right? So let me try to explain more about this question. So how many types of electric vehicles are possible, right? So you may think in terms of an electric bicycle to electric scooter, maybe it's a four-wheeler or a minibus, or it may be more electric aircraft or a truck and motorcycle as well, right? And maybe drone or maybe some other spatial vehicle applications. So there are wide category of vehicles, right? And what we call as electric vehicle, it's not only electric car, it can be electric scooter, or it can be more electric aircraft as well. So which EV motor is preferable in which application, that is not fixed, right? So there are no standards yet available for the choice of EV motor for all these applications. Now if I reframe the question, if you ask this kind of a question, the answer can be a counter question, and this counter question can be like this: what type of footwear people are going to prefer, right? What kind of footwear human beings will prefer? So do you have any particular answer? Probably no, right? Because there are wide category of footwears available, right? That depends on weather condition, that depends on one's gender, it depends on one's style and comfort, right? So there are no actual answer to the question that which footwear are preferred by humans, right? So this question is also similar. So which motor is preferred for an EV application? It's an unanswered question. So if I talk about different types of footwear, there are equally amount of different types of motors also available. So as you see in the image, there are varieties of motors which are mainly classified as AC motors and DC motor according to the type of supply, but there will be mostly the motors of different categories, right? And each and every motor is going to be meant for a given application. For example, the motor used for drone cannot be used for a bicycle. The motors used for a tractor application may not be suitable for an electric motorcycle. So there are specific motors for specific needs. So once you know this, let's move ahead and let's have a look inside the electric motor. So how does an EV motor look like? So an EV motor is going to be something similar to this. So this is an image of Chevrolet Bolt electric vehicle, and here is the motor which is integrated along with the transmission system. So what you see is the top half of the system. You can see the windings which are coming to the three ends in the terminal box like this over here, and it's basically going to have a permanent magnet rotor inside, where this is a final shaft coming in which will go to the axle, and this will provide power to the wheels. So this is one of the image of an electric vehicle motor. So how does an EV motor look in the situation of a disassembly, right? So if all the parts are going to be dismantled, and if we just focus on what is the motor construction, it will look something like this. So here is the actual internal construction of a popular electric vehicle motor, which is permanent magnet synchronous motor. So what you have is a stator over here, and this stator is basically the steady part of the motor, and the stator is divided into two parts: stator core and the stator windings. So the stator windings are inserted into the laminated stator core with this slot and tooth arrangement. Now at the end of this, there is a rotor inserted, where you have a rotor core which is like this, and the rotor is not having any windings, but the rotor is having permanent magnets. So the permanent magnet bars are inserted into the rotor, and this is how an EV motor will look like. Now if you take a cross section across this, you will be able to understand there is a big circle known as a motor, and there is a small circle known as a rotor which is surrounding the stator. So this is a very fundamental construction of an EV motor. If you are not able to understand at this moment, we are going to dive deep into this once we know about the motor power estimation. This is just to ensure that you have enough idea about a dismantle condition of a motor. So let's not look into this more now and try to understand about the different types of EV motors, right? So if you have understood about various types of motor, so in basic electrical engineering you might have learned about various types of motor. These motors are AC motors and DC motors, and it can be again classified into several things, right? So if we consider for EV application, the two major considerations are the permanent magnet DC motors and AC induction motor. So let's try to have a look and let's try to understand how these two motors are actually going to compete with each other, and which one is more popular, and what automakers are preferring to have as the motor technology. Now, when I say about motor technology, this is not just one choice. This is just one application, and a four-wheeler motor such as Chevrolet Bolt can be of this type. Now, there can be other technology as well, which is called in-wheel technology. So if you see at this image, this motor is completely different than the previous one. So in the previous motor, we had a stator surrounding the rotor, but here we have the outer rotor which is connected directly with the wheel and tire. So this is called out rotor motor, or it is also known as in-wheel motor. So in-wheel motor is where the stator remains fixed and it is attached to the axis or the central axis of the assembly, and the rotor is permanent magnet and you can see the permanent magnets inside the periphery of this part, and stator is having windings over here. So this is one such application of a motor where it's entirely different motor. So EV motors can be of different type, and this particular assembly is in-wheel motor for specifically developed for four-wheel application by Protein Electric company. So there are varieties of different motors, and there are varieties of manufacturers of EV motors as well. So let's move ahead and understand the types of motors for EV. So as I said, there are mainly two types of category of EV motor. One is AC induction and another is a permanent magnet motor. So if we see this two categories, and if we try to see which one is more popular, or without going into the technology, if we talk about which motor is available commercially or which motor is deployed in the vehicles, right? So let's take a survey results done by Adams Intelligence and try to understand which are the motors used in typical electric vehicle. So what you are seeing on the y-axis is number of electric vehicles sold. So for this much number of electric vehicles, how much is the percentage where it is shared by different types of motor? And what are the different types of motor considered over here? One is permanent magnet motor. So mostly the permanent magnet motors are here classified into permanent magnet synchronous motor, and there is another category called induction motor. The third category here is electrically excited synchronous motor, where we do not have any permanent magnets. And one of the category can be switch reluctance motor as well in this category. So electrically excited synchronous motor, induction motor, permanent magnet, synchronous motor. These are the three main categories of electric vehicle, and what you are able to see over the period of years, the number of electric cars on the road are increasing. Now, which are the types of motor used in that electric vehicles? So mostly those vehicles are using permanent magnet synchronous motor, as you can see as a dark blue color over here. But induction motors are equally getting popular. So let's try to compare these two different types of motor, which is induction motor and permanent magnet motor. So if we have a look at another survey result where it is compared in terms of three parameters: weight, cost and efficiency. So let's have a look at this survey results. It's again done by Adams Intelligence Research, and if you can see in the first report, EV motor weight is compared. So weight in kilograms and their proportion of material what is used, that is covered over here. So permanent magnet motors will be lightweight compared to induction motor. That is what we can conclude over here. So how much amount of steel and copper as a material they are going to use, that is also compared over here in terms of weight. So motor weight is a very important parameter in terms of electric vehicle application, because it has to consider its own weight and considering the space or volume available for motor to fit in the automotive application. So one comparison is from the point of weight. Induction motor is going to be not the preference if you are considering the weight criteria. The next is bill of material. What is a bill of material? It is basically the cost of all materials involved in the motor. So this is a typical cost per kilowatt for a motor which is permanent magnet motor. It's around $175, and for an AC induction motor it is slightly less than that. And here is a comparison of different types of material. So REE magnet stands for rare earth magnets. So this rare earth elements basically will be the major factor in the cost of an electric vehicle or the motor used for an electric vehicle. So here is the important comparison. So when you are going to consider a cost of an electric motor, definitely the permanent magnet motors will be more costly. Now, at the same time, if we consider the last part of comparison, which is the efficiency. So efficiency of a permanent magnet motor is way better than an induction motor of highest efficiency. So here the induction motor with the NEMA premium or high efficient induction motor is considered for the comparison. So if it is compared with a permanent magnet motor, usually the permanent magnet motor efficiencies are higher, and here this efficiency is plotted in terms of variation in the speed on the x-axis. So if you consider the factor where your vehicle is running at a lower speed, at a lower RPM, the difference in the efficiency is huge, right? So if you consider this difference of efficiency between the permanent magnet motor and the induction motor, you will definitely be able to compromise on the cost involved for permanent magnet motors. So in a way, permanent magnet motors are better for electric vehicle application, but at the same time, people are also evaluating different types of motor without permanent magnet, and it is basically induction motor and a switch reluctance motor. So induction motor is also popular. Tesla Model S and probably Mahindra E2O, these are some of the examples of car which are using induction motors. So what are the advantages of using induction motor? Basically, whenever the cost is compared for this research report, it is considering the rare earth magnet availability and its mining related cost involved. Now, as the EV demand keep on increasing, the material available for this magnet may also fall short and the price of the permanent magnet may increase. So keeping that into mind, people are also trying to look at the option for new type of induction motor where the efficiency are improved. So this is something about the comparison of PM and non-PM types of EV motors. So this is the end of first video. We will again meet in the next video. Thank you.
Hello friends, welcome to second video of Basics of Electric Vehicle Simulations using ANSYS. In this video, we are going to learn about EV motor sizing and motor drive analysis using ANSYS RMxprt and Maxwell tool. Before we begin with the second video, I would like to explain the legends which I am going to use for this video. So the topics that will be covered is represented by an I, and the topics which I'm not going to touch upon is something represented by this symbol. So here is the symbol of a hand, which are the topics of focus on, and the topics which I'm going to put in a black box, or we are going to just see the overview of that. We will not go into that detail. That is a black box. So these are the learning aids, and I'm going to add this for all the topics in order to keep clear about the level of the discussion we are going to have. Since it is a beginner level course, this will definitely help you to understand what are the contents covered and what are the contents not covered. So let's move on with what you are going to learn in this video, and I have applied the legends here as well. So you are going to learn about motor power estimation for on-road electric vehicle, and that is what we are going to focus on. We are going to do the first point by considering the physics and mathematics of forces acting on a vehicle, and which can be classified into rolling resistance, aerodynamic drag, acceleration and hill climbing. So we are going to treat the physics and mathematics as a black box over here. We will be doing the quick calculation using Microsoft Excel. That is what is included in this video. We are going to touch upon what is the meaning of a drive cycle and how is it important for motor sizing. We are also going to look at classification of electric motors. Now, classification of electric motors can be done in many ways, but what is the way which we have approached? That is only going to be one way, and there are many other ways for classification. So we are going to see this classification as a black box, and will not further classify those machines, and we will not discuss in that detail. And the last topic for this video is going to be factors affecting the choice of EV motors. So what are the factors that will affect the choice of an electric vehicle motor? So this is included in this video, and let's move ahead now with the first topic. So if we assume that this is a propulsion motor, and we say that this motor is responsible for driving the vehicles. So if I consider that this motor is required to run the vehicle, then what is the first thing? In order to start with the design of the motor, I need to first understand what is the value of the torque and speed which is going to be available on the motor shaft. So we are going to understand what is available on the motor shaft, or we will answer this question first: what does the motor experiences through wheels, right? So the shaft of the motor will be connected with a gearbox, and this gearbox can be of different teeth, and this will be directly connected with the wheels, right? So let's say this is the arrangement in a typical electric vehicle. So here we have wheel W, and this shaft is connected over here with this gearbox and some other mechanical power transmission system. So this wheel is going to apply the force and basically the torque and speed on the motor shaft. So the motor is going to experience some kind of force or some kind of load through the wheels, right? So what is that load the motor is going to experience from the wheel? That we are going to learn now. So first thing is, we need to resolve the forces acting on a vehicle body, because on the wheels you have the entire vehicle body mounted, right? So the vehicle body comes in contact with the road surface through the wheels, and basically the wheels are going to experience all the forces. So we need to resolve all the forces acting on a vehicle body. We need to know the range of speed and the torque which are available on the motor shaft. So this is very first exercise which is required for designing an electric vehicle motor, and the motor can be controlled in wide speed range, avoiding the use of multi-speed gearbox. So here is a important thing to be understood. In case of an electric vehicle, you need not to have the gear system like which is a manual gear transmission. So this is going to be a fixed gear of a fixed ratio, and it is going to be single speed gearbox, because we are able to control the motor in such a way that it can produce the required torque and speed. There is no need for multi-speed gearbox. However, in some cases where it's a hybrid electric vehicle or some special vehicle, it can be a choice for a designer to include multi-speed gearbox. So the motor is also controlled in wide speed range, and the gearbox can be only fixed speed gearbox, right? Or sometimes this gearbox may not require at all, because the motor is itself mounted in the wheel, right? So the motor which are mounted inside the wheel, they are called in-wheel motors, and there may not be any gear required at all, right? So the EV motors comes with a variety of conditions. So we have already seen one of the in-wheel motor from Protein in the earlier video. So let us move to the next slide and understand how do we resolve the forces acting on a vehicle body. So we need to understand the theory of forces acting on a vehicle body. So the first step in order to do that is simplify the mechanical load on the propulsion motor shaft. We need to resolve the forces acting on the vehicle body and therefore the motor. So let's move to the next step. we are going to now learn about vehicle tractive force analysis, and this particular analysis is applicable for road vehicles. So remember, if you are talking about some other applications, which is, let's say, electric boat, or if you are considering a drone application, or if you are considering a light aircraft application for passenger transport or any other application, this analysis cannot be applied in those type of vehicle. This analysis is applicable only for road vehicles. So what we are going to learn, we are going to take an assumption of a car body, and we are assuming that this car body is moving with velocity v in forward direction at an angle alpha on the uphill condition. So this theory is based on the vehicle dynamics. So we are not going to touch upon the vehicle dynamics in detail, but we are going to understand which are the governing equations in this case. So basically there are 4 different types of forces applicable on the vehicle. So the first is, the vehicle is required to accelerate from 0 speed to the defined speed, right? So let's say the vehicle is required to travel from 0 to 40 kilometers per hour. So how much is the power required, or how much is the energy required for acceleration? That will be calculated in this category. So the second category is the rolling resistance. If we assume that the vehicle is running at a constant speed of 40 kilometers per hour, how much is the rolling resistance experienced by the tire surface? And that is basically the rolling resistance force on the tire surface. The next is aerodynamic drag. So the vehicle, whenever it's moving, the air is going to apply some force because of air is having some finite value of density, and there will be aerodynamic drag happening. So this aerodynamic drag is also required to be overcome by the motor, which is used as a traction motor. So the aerodynamic drag basically depends on many other parameters such as wind velocity and the design or the aerodynamic design of the vehicle. So when you consider, so let's say this is the front area of the vehicle, and this front area of the vehicle can be different in different designs, and it can be different for a 2-wheeler, it can be different for a 3-wheeler, and it can be different for a different design of 4-wheelers as well. So the aerodynamic drag is something which is dependent on aerodynamic design. We are not going to touch upon the vehicle dynamics theory and aerodynamic drag in detail, but we will know what are the fundamental governing equations. And the last part is basically the hill climbing force. So these are the 4 different types of force which are acting on the vehicle, and we are going to see these forces one after another. So let us now have a look at all the forces individually. So the first force is the rolling resistance, and if I consider this force and if I express this force as a rolling resistance force, I can write this as force available on the vehicle due to rolling resistance denoted as FRR, which is basically proportional to the mass of the vehicle and obviously the gravitational constant. And this constant of proportionality can be replaced by a coefficient called rolling resistance coefficient, and the equation for rolling resistance force acting on the vehicle can be this value. So the mu RR is basically the coefficient of rolling resistance. It depends on the tire design and the road condition. So if the road is a smooth surface, or if the road is going to be a different surface under the rainy condition, this value of rolling resistance is basically going to change. Now this rolling resistance, we are here going to assume that it remains constant with reference to speed, and this force is not dependent on the speed. So whatever is the speed of the vehicle, the rolling resistance force is almost constant, but in reality it is not. So you have to dig into the vehicle dynamics in order to have more accurate equations. But with certain assumption, with certain degree of accuracy, we can apply these equations to calculate the force acting on the vehicle. The next force is aerodynamic drag, and this aerodynamic drag can be represented as this equation, and basically the aerodynamic drag is proportional to square of the velocity, and basically all this constant, which are rho, which is air density, A, which is frontal area of the vehicle, and CD is the drag coefficient, and V is the velocity, which is resultant velocity, and which is basically the vector addition of the wind velocity and the vehicle velocity. So if the wind velocity is opposing the vehicle, we need to consider that effect as well. So this is aerodynamic drag fundamental equation. So this is equation number 1, and the next important equation number 2 which we have learned is aerodynamic drag. Now there are a lot of quantities which are dependent on certain parameters. So here is a tire geometry, tire design, and maybe the road condition which decides the mu RR. Here also there are other coefficients such as CD, which is decided by the aerodynamic design, and this V square basically involves the wind velocity also, and the wind velocity is totally dependent on the environment in which you are considering in which the vehicle is running. So these are the two equations which we have seen. The next two equations will give us further idea about which are the other force. So remember, we are considering this forces in newtons, and we are considering the units in which are represented by this. So velocity in meter per second, weight in kilograms. So this is the unit system which we are going to follow here. Next we are going to discuss about hill climbing force. So the hill climbing force is basically the power required for the vehicle to climb the uphill. Why we are always considering the uphill? Because that will require more power than downhill. Basically the downhill is going to aid forward velocity of the vehicle, and therefore we are not considering that case. So uphill is the case which we have seen in the previous slide. So over here we are assuming that alpha is the angle through which the vehicle is moving on the uphill, and we will consider the same angle alpha constant throughout the velocity of the vehicle. So this can be a similar situation where your vehicle is moving on the flyover, so or your vehicle is coming out of the basement or from the parking area under the ground level. So what is the level of the force that is available or that is going to be exerted on the vehicle? Because now the mass is going to be climbing the level, right, and therefore there will be two forces which are going to be exerted on the vehicle, and which are available from the center of gravity of the vehicle as this component and this component. So let's consider the component which is acting on the opposite side of the vehicle velocity, which is this area, and this is going to be this. So we are going to consider the mg sine alpha as the hill climbing force. Let us now see the equation for the hill climbing force. So the hill climbing force is denoted as FHC, which is mg sine alpha. Here if you consider alpha in degrees, you need to convert this alpha into radians for matching the units of this force in newtons. For acceleration we can apply the simple equation, which is the Newton's law, where the force is equal to mass into acceleration. But basically this acceleration is going to be the combination of linear acceleration experienced by the vehicle body along with the angular acceleration experienced by the moving parts inside the vehicle. Now this moving parts can be the rotor of the motor along with the gearbox. So the gearbox and the rotor of the vehicle will have some kind of inertia, and that has to be included over here. So when we consider the mass of the vehicle, this mass is considered as the moment of inertia, and that is included with 10 to 15% higher than the actual mass of the vehicle body. So when we consider all such forces, right, so we have now addition of all the forces, which is basically a rolling resistance force added with aerodynamic drag force added with hill climbing force, which we have seen over here, along with the acceleration force. Now all these forces together will develop an equivalent force which is called a tractive force Ft. So tractive force Ft is basically motor is required to produce this much amount of force. Now we are talking about the force. How do we come to the power, right? So the power equation is as simple as this: force times speed, right? So if you have force in newtons and speed in meter per second, you can get the power in watts. So this equations are very fundamental equation for vehicle power analysis for road vehicles. So let us now move ahead and do the full analysis with some assumed values. Okay, so here is the total tractive effort and the motor power estimation. So as we discussed in the previous video, we are going to do this thing which is called motor power estimation. We are going to come up with how much is the watt rating of the motor, right? So we are definitely interested in the torque which motor is required to generate. We are interested in the speed range the vehicle is required to cover, and based on this we are also interested to calculate the power, which can be in watts or kilowatts. So let us figure out a way and let's apply all these equations and calculate these parameters. So what we are going to consider? We are going to consider extreme conditions, right? So the maximum value of the speed at which the vehicle is running, the maximum value of the angle at which the vehicle may travel. We are going to consider the maximum value of the acceleration it requires, and we will also consider the maximum rolling resistance which can present. So the total force is addition of all individual components, as I explained in the previous slide, and we are going to do all in one calculation. So let's apply all these four basic formulas and try to figure out how much is the power rating of the motor. And basically when we do so, we are going to do a single point calculation, right? So remember, this is going to be a calculation at given vehicle speed. Let's say vehicle is traveling at v velocity, which is linear velocity in meter per second. All our calculations related to p watts will be at v meter per second. So keep this point in mind, and we will come back to the slide again after looking at this Excel calculator. So let me now open the Excel calculator and show you all these calculations for vehicle power analysis. So here is the Excel calculator which will be calculating all the forces one after another. So if we consider the vehicle body weight or the empty vehicle weight is around 1625 kilograms, and there are 400 kilograms of payload, and the coefficient of rolling resistance is 0.0111, then the rolling resistance force will be the addition of this two weight multiplied by g, which is 9.8 times mu rr. So this is going to come up to 220 newtons. So how do I came up with this? Is basically the Chevrolet Bolt EV. I'm considering the Chevrolet Bolt electric vehicle as a reference vehicle. So I'm referring to this link for the vehicle specifications. So this vehicle specification is given over here as like this, and basically it has battery system of this many number of cells and 60 kilowatt hours of energy, and electric drive systems where you can see the power rating of the motor is 150 kilowatt, and it's a permanent magnet drive motor, and there is a final drive ratio. Basically it's a single speed gearbox which is 7:1, and there are all other parameters of the vehicle mentioned over here. So what are the dimensions of the vehicle? What is the frontal area of the vehicle? I think you can calculate all this from this particular article. So I'm referring to this article and I entered the values in this Excel sheet. So I came to calculate the rolling resistance force as 220 Newton. I'm assuming that the rolling resistance coefficient remains this value. Now how do we actually determine that? Well, in order to do that, we have to be dependent on the actual experiments. So the experimental values will be best suited for here to enter in this calculator. Now for air drag calculation, I am entering the height and width of the vehicle and calculating the frontal area, which is basically the multiplication of these two, and I'm assuming the drag coefficient is 0.308, and I'm assuming the highest speed. So the top speed of the vehicle is 145 kilometers per hour, and keeping all units same, the air drag force comes out to be 880 newtons approximately. Now if I do this rolling resistance and air drag only, basically this is the case where the vehicle is running at a constant speed. So there is no uphill and there is no acceleration. There will be only two forces applicable on the vehicle, and that calculation where you have 220 newtons along with 880 multiplied with the velocity, which is equivalent to 145 kilometers per hour, it will be converted into meter per second, and that comes out to be 44 kilowatts. So the 44 kilowatts is the power required by the vehicle in order to run at a constant speed with this assumptions, where the drag coefficient and the rolling resistance coefficients are very important values. So this is the calculation for these two forces. Now why I have separated this? Because normally the uphill cannot be the case every time, the acceleration cannot be the case every time. So the forces acting on the vehicle, they will not be acting all simultaneously. They may be present or they may not be. So let's assume the hill climbing angle is 10 degrees, which is usually the case with a flyover, and the speed at which the vehicle is running on the flyover, that I am assuming is at 80 kilometers per hour. So if this speed is 80, then we need hill climbing power itself to be 76 kilowatt. So this is the value of the hill climbing power required, and if I assume that my vehicle should run on the flyover at 100 kilometers per hour, basically it will end up having 95 kilowatts of power. So basically this is mechanical power required on the wheels, and if you assume the efficiency of the gearbox, if you assume the efficiency of the motor, the sizing of the motor has to be much higher than this. So these are the forces acting on the vehicle and added one after another over here. Now for your reference, I have added another vehicle as well. So if you consider a lighter vehicle with the similar values, basically, and if you have a low speed electric car, let's say your top speed is 100 kilometers per hour only, then your vehicle will require only 12 kilowatt power to run at 100 kilometers per hour speed, and in order to do the hill climbing it will require 45 kilowatts. So the sizing of the motor or power estimation of the motor will be somewhat less if you have the less weight of the car, and therefore people are talking about the light weighting and the new mechanical design for electric vehicles. So let's go to the acceleration as well, and acceleration calculation is done with an assumption that what is the rate of acceleration you want. So here for a Chevrolet Bolt EV, the acceleration is from 0 to 96 kilometers per hour. It should happen in 7 seconds, right? So imagine the situation where 0 to 100 kilometers per hour is below 7 seconds. The amount of power required for this acceleration alone is 123 kilowatt. So keeping all these values in mind and all this basic mathematics, we can assume that the power estimation for this type of the vehicle is equivalent to 150 kilowatt. So 150 kilowatt may be the continuous rating of this motor used in Chevrolet Bolt EV, but the peak power rating and the peak torque demand can be different. So let us pay attention to the torque values as well. How do we calculate the torque from the force? Well, it's basically very simple. You need to find out the radius of the wheel and convert the all force values into Newton into meter. So basically the torque represented as Newton into meter. Newtons we already have calculated for this 4 categories, and if you multiply with the radius, you can easily calculate the Newton meter torque available on the wheels. So let's do this for the Chevrolet Bolt. So the Chevrolet Bolt has this type of tire, and it has 0.3 meter radius considering the thickness of the tire as well, and 8,840 newtons is the addition of 3 forces acting over here. I'm considering the 3 forces, not all 4 forces simultaneously, and the Newton meter which is available on the wheels, which comes out to be 2,850 Newton meters on wheels. If we assume that the force is this much and the radius is this, and if I consider the gearbox, so basically the gearbox is a reduction speed gearbox where the speed will be reduced, the torque will increase, right? So the torque on the wheels will be much higher than the torque available on the motor shaft, right? So therefore I am considering the final drive gear ratio which is available from this specification as 7:1, and if I do this 2850 divided by 7, which comes out to be 407 Newton meter, and which is approximately the torque which is developed by the motor, which is 360 Newton meter. So these are some of the basic calculations for a vehicle which has all these forces acting around. Now it's the time to get back to the presentation and imagine how this much power can be put inside a motor, and that's where we start with the motor design. So if you remember, we discussed about the forces acting on the vehicle, which are fundamentally the forces required for running the vehicle and which are at typical velocity, right? So what is the meaning of a drive cycle and why we are interested in learning about drive cycle? So fundamentally the drive cycle is something which is going to give us idea about the vehicle speed. So we have calculated power P in kilowatts for running the vehicle at given velocity, right? So we have calculated a single point calculation, but the velocity of the vehicle never remains same, right? If you consider your urban driving or maybe highway driving, you never drive your vehicle at exactly constant speed throughout your ride, right? So that's why, which is very important to consider the pattern of driving, right? So the pattern of driving is basically known as driving cycle. So driving cycle is defined as variation in speed with reference to time. So the constant velocity computation will give us instantaneous power, but if we are interested in overall power or average power or calculating energy from this, we need to pay attention to the pattern of driving. So in order to calculate this, we need to understand what is the driving cycle. I'm going to quickly explain you. Basically, the driving cycle concept was mainly developed for testing the emissions, but now it is also very widely applied for the vehicle testing. So one example is Federal Urban Driving Schedule. So what is this? So here is a graph of Federal Urban Driving Schedule. So this is the data available where you have approximately 1400 seconds on the x-axis and the y-axis is speed in kilometers per hour. So this is how you are running your vehicle if you follow the FUDS. So this is one such standard drive cycle available for test purpose of the vehicle, but you never know what is going to be your drive pattern, and therefore this is going to be the very important point for electric vehicle motor selection, where you need to know what is going to be the peak case and how much is going to be the average velocity, right? So if you consider purpose of the vehicle, if the vehicle purpose is going to be the highway, then you need to assume the average velocity is going to be very high. If you consider the vehicle purpose as urban driving, driving in a city or in a traffic area, which is average velocity which be much less. So these are some of the important points for a drive cycle. Let's move on and discuss about classification of electric vehicle motors. So this classification is based on this reference book, and basically this classification is according to the construction, and there can be another classification according to the type of the flux or maybe type of the supply and so on, right? But here is a main classification related to whether the machine has commutator or not. So basically the commutator function is going to change the type of excitation in the winding from alternating to direct. So if the commutator is present, basically it's a DC type machine, and the DC type machine can be either series shunt separately excited under the wound field category, or it can be permanent magnet DC machine. So this is also one such highlighted category which is popular for electric vehicle motors. If you consider the commutator less machine, basically the question arises, how does the commutation happens then? Yes, the commutation happens, but it is electronic commutation. So for electronic commutation, you have the fundamental requirement of power drive, or basically we call it as a motor drive or inverter in case of a DC supply for a motor. So the commutation basically happens electronically, or if it is the case of a DC motor, or if it is a case of an induction motor, it is not required, right? So the commutation is not required because of the working principle of the motor, right? So let's see the first category, which is the induction machine, and there are two categories. Usually the wound rotor motors are not preferred for EV. The squirrel cage induction motors are preferred. In case of synchronous, there can be three different categories: wound rotor, PM rotor, and reluctance rotor. So this PM rotor type of synchronous machine is very popular for electric vehicle application, and this it can be again classified into two more categories: permanent magnet brushless AC machine and permanent magnet brushless DC machine. Normally it is called as BLDC motor, and this is called as permanent magnet synchronous motor. So again, another classification is doubly salient, where the saliency is present on both stator and rotor. The meaning of the saliency is the poles are projected outside. So the switch reluctance motor is also popular, and the permanent magnet doubly salient motors are also popular for EV applications. So where the stator is going to have rotor. So whether the stator is permanent magnet or rotor is permanent magnet, there can be another classification. Now this can be again classified into flux reversal or flux switching or doubly salient permanent magnet, and this three classification can be again having an option of controllable flux. So flux controllable DSPM, flux controllable flux reversal PM is another category, and this can be the last category. So the doubly salient motor is another classification of electric vehicle motors. Vernier motor is basically going to offer the high torque at low speed, and basically it is also known as the magnetic gearing motors. So the magnetic gearing motor is called Vernier motor from the Vernier effect. So the Vernier permanent magnet motor is also one of the popular machine for electric vehicles. So this is the overall classification of electric vehicle. Now there can be n number of different ways to classify the motors, which can be based on the type of the flux. It can be radial flux, axial flux, or linear flux, and there may be another classification tree. So this is about the classification of EV motors. Now let's learn what are the factors affecting the choice of EV motor. So as we have seen, there are many different types of motor. Which one is going to be the best choice, right? So how do we decide on the type of the motor, power rating of the motor, and configuration of the electrical machine used for propulsion? So there are many factors actually affecting this choice. I have shortlisted here few important governing factors. So here let us talk first about speed and torque requirements. So the very first thing is speed and torque requirement. So what are the speed and torque requirements? So as we have calculated in an Excel calculator in our previous video, you need to understand how much is the speed required on the wheels, how much is the torque required on the wheels, and those speed and torque can be translated through the gearbox, and you can actually take into account the gearing ratio, and you can calculate the speed required for motor and torque required for the motor. So this values can be actually taken as a maximum value for the motor consideration initially. So let's say the highest speed required by the motor in order to run the vehicle at a highest speed, let's say the top speed is 100 kilometers per hour. So for 100 kilometers per hour linear speed of the vehicle, how much will be the angular velocity of the wheel and how much should be the speed of a motor, how much RPM should the motor have, that can be calculated easily, and that will be the deciding factor of the highest speed. Similarly, when your vehicle is going to start with the maximum acceleration, it is required to produce maximum value of the torque, and therefore this torque should be considered as the maximum possible torque produced by the motor, and it can be produced at a very low speed. So at a very low speed, the machine is required to produce the high torque for acceleration. So once this factor we have considered, the second factor is actually related to speed and torque, and that is very important factor known as efficiency. So what is going to be the efficiency of the motor at given torque and speed? So you have calculated maximum speed, you have calculated the maximum torque, but what about the efficiency at all speed and torque? So this is very important parameter to be considered. Why efficiency is very much important? We have already seen this in case of why the battery systems are high voltage, right? And we know that in order to reduce the losses happening because of I²R, we usually choose the high voltage system. But let us talk about efficiency for a motor. Now let's say the motor is having 80% efficiency and all other stages are also similar to 80% efficiency. Then the overall efficiency will be less than 50%, right? Because there are 4 to 5 different stages connected back to back, so the cascaded efficiency at all stages, right, the overall efficiency of the vehicle will be very low. Actually, the overall efficiency depends on the lowest efficiency of each component coming into picture. So the motor efficiency is very important parameter, and because here the motor operates at very different operating points, and therefore it is very important to design and develop the motor according to the efficiency. The third factor is cost and availability of the material. So if you are choosing the permanent magnet material, and if you are choosing let's say some type of copper for winding, right, you need to take into consideration that how much is going to be the availability of the permanent magnet material and what will be the cost, and it may require to be evaluated for the lifetime of the motor, right? So you may think of a motor undergoes a maintenance, right, after let's say some amount of time. Now how much is going to be the cost for repair or replacement of any of the component? So that has to be taken into account, and considering that there is a lot of research going on with the permanent magnet materials for the EV motors, as well as how this cost can be affected in the future. So the permanent magnet material cost is going to be, let's say, volatile. It is not going to be fixed. It depends upon the demand and the supply. So if the supply is going to be less and the demand is high, the cost will definitely rise. So the cost and availability is going to be the deciding factor for the choice of EV motor, because once you design a motor, that design will go into manufacturing, and at least for 5 to 10 years of duration, that particular motor will be in operation and in repair and maintenance. So you need to be sure that for that much duration of time the similar type of material will be available, which is decided at the time of design. So this is another important factor. Now the last factor I want to discuss about is the thermal performance and the reliability. So here the thermal performance is basically how much is the volume allowed for the motor, and there are actually two things we need to consider here. One is a continuous duty and one is a peak duty, or we can say the maximum value of the power which motor can provide for shorter period of time. So usually the motors are rated, the normal motors are rated from S1 to S7 class of duty. So this S1 to S7 class of duty are actually decided based on their operating conditions, right? So for example, there is one motor in the textile industry and which is required to be operated during let's say 12 hours in a day. So 12 hours in a day. Now how that motor will be operated in 12 hours? For that 12 hours the motor may operate at a continuous speed, or the motor may operate like forward, stop, reverse, again forward, stop, reverse. It may be operated like that. It may be operated like forward, brake, stop, reverse, brake, stop, right? So there may be different operating conditions and duration of a typical motor. What about EV application? EV application actually undergoes different condition according to the drive cycle. So based on the drive cycle, the motor is required to produce the power, and because the drive cycle speed is continuously varying, you never know how you will drive your vehicle, right? It depends on many conditions. It depends on the traffic, it depends on environmental condition, and so on. So how you are going to drive your vehicle is going to be affecting the overall thermal performance, right? So the thermal performance may actually affect the life of the permanent magnets, right? So therefore there is a trade-off between non-permanent magnet motors and permanent magnet motors for electric vehicle applications. So some manufacturers are trying to use induction motors and switch reluctance motor, which are non-permanent magnet motor, and many manufacturers, due to advantage of permanent magnet material and their advantages compared to their disadvantages and the cost, they are using permanent magnet materials type of motors. So the thermal performance is again the key aspect where you need to decide on how much will be the overall lifespan and how much will be the life affected due to the every temperature rise. So in order to understand the second point, let us try to have a graph of speed, torque and efficiency from a manufacturer. So we can consider a graph of speed versus torque characteristics of a motor, where we are going to discuss this factor efficiency along with torque speed, and we will also discuss about the type of duty of the machine and its thermal effect. So let me show you this graph. You can see this is a typical graph of speed versus torque. So on the y-axis you have torque in Newton meter, on the x-axis you have speed in RPM. So the highest RPM for this particular motor is 7500, and for 7500 the machine is going to produce a relatively lower value of the torque, which you can see from here. Now this machine can actually produce a very high starting torque such as 150 Newton meter at very low speed regions over here. Now what you see inside this, right, are the actually efficiency contours. What is the meaning of a contour? Contour means the value of the efficiency for given speed and torque. So for example, if I take the RPM which is let's say equal to 1000 RPM and the torque value which is equal to 90 Newton meter torque, and that point will be lying somewhere over here, and that point is having the efficiency of 90% because it is lying on the efficiency contour plot of 90%. So all this points are actually having 90% efficiency. So this particular graph is actually derived from an experimental data of a motor, or it can be derived from the software tools such as ANSYS. So here you can see the efficiency plot will be very useful if you are interested in evaluating the overall efficiency of your entire vehicle, and you may be interested in knowing more about how will be the efficiency point at a different period of a drive cycle. So let me make it clear to you with a few more edit in the diagram. So okay, let me erase all the things. Okay, so here when you talk about a drive cycle, so let us assume that our drive cycle, which is speed versus time, is something of this nature. So here we have this as a nature of speed versus time, and this is how we are running our vehicle. Now for all those speed values, we might have the points in the graph which will be something located over here. So some points during acceleration can be located over here at probably this duration of time. Something where we have the peak speed, those points can be located over here where the torque requirement is not much but the speed is very high, and something, these points may be located over here in the speed torque graph. So you need to consider having all these things together, and you need to understand how all these points will be located inside this and where your maximum points are located. So you need to assume whether your maximum number of points are located in this region, or maximum number of points are located in this region, or maximum number of points are located somewhere over here. So if your points are located in this third case, which I have highlighted here, your efficiency is going to be best because it is 90 to 92% efficiency. So you need to understand how your motor is going to be utilized in this case. So once you have understood this, I think you know now better about the choice of EV motor and how the efficiency is important apart from speed and torque. And as you can see, if the motor is operated at very high speed, the efficiency is very low, such as here. If the motor is operated at very high torque and low speed, the efficiency is very low. So the efficiency actually decreases as you move away from these points where this is the highest efficiency contour, where it may be 94% efficiency for this case. And the other important thing to understand is the plot which is going to be related to the type of duty. So what is that plot? You can see these two plots over here where you have 30 kilowatt motor power rating, which is this plot, and you have another plot which is 50 kilowatt intermittent operation. What is the meaning of intermittent? It is a short duration period, right? So for short duration period, you can actually get higher value of torque and you can actually get more power from the motor for short duration of time. But during this period, the motor may produce higher amount of heat, and you need to know that what is going to be the continuous power rating of the motor and what is going to be the peak power rating of the motor, and you need to understand from manufacturer's data sheet that how much is that duration. So for how much duration I can get 50 kilowatt from a 30 kilowatt continuous motor, and whether the duration is in seconds, few minutes, or for how much, and whether do we need to provide more cooling during that operation or not. So with this, I hope you are now clear about which are the factors affecting the choice of an EV motor. In the next video, we are going to learn more with ANSYS tools that how we can start the initial efforts in the EV motor design. So in the next video, we'll be looking at ANSYS RMxprt, and we'll talk about the template based design for electric vehicle motors. Thank you for watching this video. Hello everyone, welcome to third video of EV motor sizing short course. This course is part of Basics of EV Simulations using ANSYS. Let's have a quick recap of what we learned in video number 1 and 2. In the first part, we learned about fundamental principles of electric vehicle motors, their types, and different materials, and we have also seen an open view or render image of the motor, how an EV motor will look like. In the second part, we discuss about how to decide about speed and torque and power rating of EV motor. So once we have come to a conclusion of speed, torque and power rating of a motor, the next step is the motor sizing with fundamental design equations. So now let's see what is included in the course. So these are the learning aids which I am going to use, and these are similar to the video number 2 which we have followed. So what you are going to learn in this video, you are going to learn about fundamentals of motor operation and construction, fundamental equations of motor sizing, specifically for permanent magnet synchronous motor, basics of power converter operation for a permanent magnet synchronous motor, and analytical design of PMSM motor with ANSYS RMxprt and Maxwell 2D. So these are the things you are going to learn in this video, and if I try to connect with the previous videos, we have already seen some of the fundamentals of motor power estimation. So those motor power estimation can be referred here, and then you can start the paper design of the motor. So let's move ahead and learn about fundamentals of motor operation. So what are the minimum things required for any motor to work? So for any motor to produce rotation, or we can say torque and speed, there are minimum 2 things required. So the minimum 2 things are basically the flux, or we can say the magnetic field, and current, we can say the electric field. So the entire motor theories are dependent on 2 things. One is the magnetic field and the other is electric field. So the electric field and magnetic field are both required in order to produce the speed and the torque. Now if I draw a simple construction of a motor where you have one pole over here and we call it as N pole, and another pole over here we call this as S pole or South pole, the magnetic field are established from north to south. So the field lines can actually provide some force on a current carrying conductor placed in this magnetic field. So how do we have a current carrying conductor placed in a magnetic field? So if I draw a conductor like this current carrying conductor, if it is placed in a magnetic field, then it can produce the required force, and this conductor will move physically according to the force. Now this force is basically the force acting due to attraction and repulsion. So basically what happens inside a motor is, whenever you have a current carrying conductor which is carrying the current in up direction from bottom to top, this will create its own magnetic field. Now this magnetic field and the permanent magnetic field will interact with each other and can produce the force. So the interaction between 2 magnetic field is very much important for the motor operation. So the interaction of 2 different magnetic field is a third part where the motor operation is going to be considered. So one single coil which is placed like this, or I will not call this as a coil, but it's a conductor. Now if there is one conductor and we need to see how we are going to provide this current, how we are going to supply the current in this conductor. So the supply in this conductor can be made through a return path where the return conductor is like this, and this single turn coil can actually be connected through the positive and negative supply of a DC voltage through a commutator, and this becomes a simple operation of a DC motor. So a DC motor operation is very simple, where you have a current carrying conductor placed in a magnetic field. It is going to experience the force, and basically if you have this coil which is allowed to rotate, so now this coil is a construction, and if this coil is allowed to rotate, how this coil can be allowed to rotate? There has to be some rotating arrangement. So then this coil can actually make turns. Now remember, whenever the N pole and S pole are basically going to be fixed, the direction of the current can get reversed due to the commutator action, and because of this the coil can experience the rotations whenever placed inside the magnetic field. So this is very simple construction of the motor. Now coming back to the EV motors, what kind of construction they have. So if I explain you about an EV motor, basically they are brushless DC motor, and let's understand about what is a brushless DC motor. It is very much required that you know the action of a commutator first to know about the electronic commutation for a brushless DC motor. So if I show you the arrangement of a brushless DC motor through this animation is basically created by Renesas Electronics. It's a semiconductor company which provides the motor driver semiconductor chips. So they not only provide the motor driver semiconductor chips which will be based on intelligent control, but they also provide some fundamental learning about the motor. So the power converter engineer will also basically work on the motor fundamental operating principles. So if you have closely look at this, the rotor is basically a fixed permanent magnet rotor, and the N pole and S pole of the rotor are not changing because they are permanent magnet. Now the stator is basically a winding or coil, is a three-phase coil. So there are three phases on the stator poles. So this is one of the stator pole. How the stator pole is created? Basically this stator pole is an electromagnet. What is an electromagnet? Electromagnet is the material whenever excited through electrical current, it is going to produce the magnetic field. So this electromagnet are basically going to produce the required magnetic field. Now let's pay attention to the pole number 1. So here there are three poles, pole number 1, 2 and 3. They are 120 degree apart from each other, and they have three phase winding. Now let's take the case of the pole 1. So whenever the pole 1 is energized with the current flowing in the downward direction, the orientation of the magnetic pole is such that it produces N pole over here on the bottom side and S pole over here and the top side. So this is the downward direction of effect of the current flowing in the downward direction. So you can see in the animation, whenever the current flows in the downward direction, N pole is created over here and the S pole is created over here. Similarly, whenever the current direction is outcoming, the N pole and the S pole changes. Now the same happens with the other two poles as well. So this is how a three-phase coil is excited. And basically if you see the coil connections, if I simplify the coil connections, it will be like this is the first pole winding, this is the second pole winding, and this is basically a third pole winding, and they are connected through a star connection. So because they have this common points, so these are the common points where end of all windings are made common. So this is a star point or a return path, and these are the phase windings where the current will be either incoming or outgoing. So based on the windings which are excited, the N pole and S pole are created electromagnetically. Now those electromagnetically created N pole and S pole will basically generate attraction and repulsion related forces in the air gap available over here. So these electromagnets will try to catch up whenever there is an S pole, and N pole is going to attract, the same S pole is going to repel. So the attraction and repulsion happens in such a way that the rotor actually rotates in counterclockwise direction. So if you have understood that the N pole and S pole available on each and every pole of a stator are created intentionally, right? So if this pattern of excitation is not followed, the motor will not be able to maintain its motion in a typical direction. So this excitation sequence is very much important, and it is also important to know the rotor position for a brushless DC motor. So this is the fundamental operation of a brushless DC motor, and as you can see here, the electromagnets are basically created by windings, right? So when we talk about the conductor, coil and the winding, basically they are the higher order forms of a current carrying conductor. Now if I show you an actual picture of the motor, so this is just for concept, and this is not going to be replicating the actual motor, right? We are going to see now in ANSYS software how does an actual motor will look like. So here I am referring to another render image from Nidec Corporation, which is basically a motor manufacturing company. So motor manufacturing company like Nidec have developed a brushless DC motor for hard drive application, and this is the image of hard drive printed circuit board. And basically what you are able to see, these are the stator part, and these are the stator coil which remains fixed, and the rotor is basically this disc, and there will be permanent magnet mounted over here. So this is a permanent magnet rotor, and the difference between this concept and this product is basically here you have the rotor inside the stator, and here you have the rotor outside the stator. So many applications consider the rotor which is outside, and this is just a simple application of a hard drive. So what you see over here are the stator number of poles, and where you have the winding, where you can see the copper is wound over here like this, and here you have the permanent magnets. So the stator poles and the rotor poles will interact with each other and produce the required torque and speed, and this is the fundamental motor operation. We can actually dive deep into this and go on talking about the motor operation and talk about what is the purpose of that type of construction of that motor, but during this short course we are not going to touch upon that part. So let us now focus on the fundamental sizing equations. So what are the fundamental sizing equation? What I need to decide, let's say I have the torque, speed and the power values. How do I satisfy all these values based on the motor material and the dimension which are available to us? So application specifications are very much important. From an Excel calculator we can take the values of torque, speed and power, and basically the vehicle dynamics team as a part of a large engineering team can come up with a very detailed data on the vehicle speed, torque requirements, and this can include the braking requirements as well. So we are going to learn about how motor can be constructed such that it can match the load demand. Now what do we mean by the construction of a motor? The construction of a motor refers to the dimensions and material. So basically motor sizing activity is deciding on dimension as first part and material as a second part. So if you have decided the dimension and the material together, you can basically go back to your calculations and follow that whether your torque, speed and power requirements are matching or not. And this is basically not a simple calculation as this. There are fundamental difference between a design and a calculation. So design is basically the choice along with the calculation, right? So you need to assume many parameters over here in the design, or basically the sizing of a motor. And let's understand the very fundamental thing which is known as electric and magnetic loading. As I explained in the previous slide, the magnetic loading basically refers to the flux part of motor, and electric loading refers to the current part or coil and winding part of the motor. So the electric and magnetic loading is very much important to be understood for sizing of any motor. Now, what do I mean by sizing of a motor? Let me give you another application where, let's say, if you have a high story building, and on, let's say this is 3-story building, and on the top of that you have a water tank basically supplying the water to all the houses of this building, and below the ground level you have a ground water tank. So this is the ground tank and this is the overhead tank. Now, in order to pump the water from ground tank to overhead tank, you will require a pump which is going to be driven by a motor. So let's say this is the pump and motor assembly. Now, what should be the size of this motor such that the piping which is done from the ground tank to an overhead tank is going to provide the water to all houses? So what are the parameters you need to take care? You need to take care of the height, you need to understand about the flow rate, you need to understand about the diameter of the pipe, and there are many other factors as well. So if you know the fundamentals of your application, it becomes easy for you to then next step is the sizing. So the sizing becomes easy if you have the torque, speed and the power requirement along with the limit of the volume. So if you have any constraint on the volume, or if you have any constraint on the temperature, operating limits of the motor, then this can be the other inputs as well. So if you consider the electric and magnetic loading, that is the very first step of sizing of a motor. Now, as I explained in the previous slide, the force acting on a current carrying conductor placed in a magnetic field B, and the length of the conductor is L, and the current is I. The force will be experienced by the conductor, and that can be written as F equals to BIL. Now, how do we actually get the torque from the force, right? So it's not going to be only one conductor carrying a current enough for the motor. We will have a group of conductors. Now, group of conductors will be placed on a rotor, and this rotor element will have some diameter, let's say d, and the radius can be d by 2. So the force multiplied with the radius will result into the torque. So the motor torque can be calculated from force into radius. So these are very simple equations to understand, to start understanding about the sizing of the motor. Now, if I consider the shear stress which the rotor is going to experience, it can be represented as this equation, where it's product of B into A, where B is basically the magnetic loading, or we can call it as a uniform magnetic field or magnetic field density in Weber per meter square, and E is the electric loading. We are going to learn about electric loading in the next slide. The force F is in newtons, and if you multiply the radius by meter, the force will be Newton meter. I is basically the RMS current flowing through the current carrying conductor, and L is the wire length, T is the electromagnetic torque, and as I said, D is represented as a rotor diameter. So this fundamental equation is going to be a simple equation where you have a stator and the rotor, and this stator and rotor will produce together the required force. So let's say if you have this as a stator arrangement, and let's say there is one slot over here, and this is the overall rotor, and if you consider the coils or windings which are placed over here, then this rotor part is going to experience the force, and all this rotor conductors together will produce the electromagnetic torque. So the B times A is basically the electric loading times magnetic loading, which defines the shear stress available on the rotor. So moving on to the next slide, we are going to now talk about the fundamental torque equation. So how can we actually calculate the torque which is given by force, right? So if we replace the force values by certain parameters which are the design parameters, then we can write the equation of the torque in this format. So this torque equation basically involves AB, and D is the diameter, and this torque is proportional to the square of the diameter. L stands for stack length. So LSTK stands for stack length, and we are going to see the terminologies KW1, which is basically the winding factor, fundamental winding factor. So 1 stands for fundamental thing. Now what is A? So A represents actually the electrical loading, and the electrical loading can be determined as total ampere conductors. Basically these are ampere turns divided by the air gap circumference. So how much is electrical loading per unit area? So that is what is called A. And basically if you have m number of phase and number of turns per phase as NPH, and I is a current flowing through the each conductor, then this 2m into NPH times IRMS divided by pi d is going to be electrical loading, because we are going to have 2 wires of a coil. So that's the factor 2. Now if we consider the next important parameter or the next important equation, which is basically the torque ratio volume. So the ratio of torque to the rotor volume is basically called TRV. So TRV is one such important parameter for the sizing of the motor, and there are other important parameters such as shape ratio, which is usually called as L by D, or sometimes it is also referred as L by D square or L square by D, and so on, depending on the type of the motor. This shape ratio is also a very important parameter for motor design. Let's focus on the TRV. Basically it's a torque ratio per unit volume. So torque ratio per unit volume of the rotor. So what is the volume of the rotor? It can be determined from over here. So pi times d square divided by 4. So if I exclude these terms, 1 time of pi d square by 4, that is going to be the ratio, that is going to be the area, and if we multiply with the stack length, that is going to be the volume. So basically the volume of a rotor, which is going to be like a cylinder like this, and if it has length of L stack over here, and if it has the radius or the diameter which is d, then we can have the volume of this cylindrical construction as pi r square, which is basically pi into d square by 4. So if I replace r as d by 2, it will be d square by 4 multiplied with length. So this is going to be the overall volume of this cylinder. So here, if we take the torque with the rotor volume, then TRV becomes this value. And basically if you consider all this as constant, it's fundamentally the multiplication of A and B, which is electric and magnetic loading. Let's see other fundamental equations as well. This E is basically the EMF produced, or we can call it as a back EMF, which is basically, the full name is back electromotive force produced in the winding, and it can be equated like this. So here the flux equation is B times area. So flux is represented as flux per pole, and it is multiplied with area, where we can write the equation for B is phi divided by A, and this area is basically pi dl divided by number of poles. So here we are representing P as number of pole pairs, and 2P will be equal to number of poles. So this is the equation for the flux per pole and EMF induced in the winding, and based on this fundamental sizing equation you can finally decide about the D, L and A and B values. So you can actually decide about what should be your design choice for number of turns, for current, diameter and so on. So basically torque ratio volume is one such parameter, and other parameter is the shape ratio, which is popularly known as length divided by diameter. So if you calculate these parameters, the next step is to realize the performance of the motor. Now, can we realize the performance of the motor just from the dimensions? No. So there are two important things to be considered. One is the dimension and the other is the material. So when you are considering some value of current, when you are considering some value of flux per pole, basically you can achieve the value of the current and the flux based on the electrical and the magnetic material which is present in the motor. So the materials and dimensions together will help to fix out all this and construct a motor. So let's move on and now understand stator and rotor topologies. So what is the meaning of a topology? Topology means the configuration, the type, or it can be also simplified as how they are created. So what is the style of stator and the rotor? And actually there are many style, or there are many types exist. Let's try to see the rotor types. Rotor magnetic poles, their type and the number of pole pairs are decided based on the type of the magnetic material and the overall requirement of the magnetic field in the motor. So there are two types of rotor, as we have seen in the previous slide: outer rotor and inner rotor. And outer rotor and inner rotor are classification of the motor according to the rotor. Basically the outer rotor motor are something similar to a ceiling fan motor or the hard drive motor, which we have seen earlier. And most of the types of motor are inner rotor, where the stator is basically surrounding the rotor. So if I draw the red part as a stator, and if I have a blue color for a rotor, this is basically the inner rotor configuration. And most of the type of motor are this configuration. The rotor is inside the stator, but the reverse is also true, where the rotor is outside and the stator is inside. So if you consider a ceiling fan motor, basically the ceiling fan motor is of single phase induction motor type, and that is outer rotor motor. So where the center of the stator is fixed to the ceiling, and the periphery of this red color stator consists of split phase winding, and the rotor is basically the blue colored part, and it is connected with the wings, and when the rotor rotates, the wings will also rotate. The outer rotor motor is also popular for electric vehicle application, as we have seen, and this can be directly connected with the wheels. So let's see more types of motor according to the orientation of the magnets. According to the style in which the magnets are inserted into the rotor, there are mainly two types: surface permanent magnet or interior permanent magnet. So here is the difference between surface and interior permanent magnet. So the permanent magnets which are on the outer surface of the rotor, they are called surface permanent magnet. So this is one important classification of different types of PM rotors, whether it's surface permanent magnet or interior permanent magnet. So the interior permanent magnet motor is offering more advantages over here because it is well embraced into the rotor core, and the arrangement of the permanent magnets, or we can say the flux available from this permanent magnet, is going to be more effective than the case of a surface permanent magnet. And also because the rotor is rotating, the centrifugal force will be experienced by this permanent magnet material, and that is also the reason where in case of a high speed drive, the interior permanent magnet can be more preferable. So here the utilization of the core material in this case and this case, it is better for the interior permanent magnet motor. So let's move ahead and now see another difference of axial flux and radial flux machine. So basically we are not going to see the axial flux machine, we will be only focusing on radial flux machine. So what is the difference? This difference is based on the direction of useful flux. So if the direction of the useful flux is radial, or we can say perpendicular to the shaft of the machine, then it is radial flux, and normally it has large length compared to the diameter. So most of the motors which are of this type, where its length is larger than the diameter, then these type of motors are radial flux motors. And axial flux motor is basically compact and sandwich type construction, and their diameter is large but length is small. So if I draw this kind of a motor, it will be something similar to this, where its length is quite small, and this can be another arrangement of, let's say there are two rotors and there is a single stator in between. So radial flux and axial flux machine are another classification based on the direction of the flux, and there are other types of machine also possible which are called transverse flux machine and linear flux machines, which we have seen in the classification of motors. So if I give you a diagram of a radial flux and axial flux machine, it will be look like something this. So here you have the outer rotor and the inner stator, and basically the stator is having windings. So here you can see the winding parts, and all these windings are kept on the stator, and the rotor is consisting of two permanent magnet poles. So this is a simple construction of a radial flux machine. So the direction of the flux is something which is given as this dotted line. So this black dotted line starting from N pole to S pole basically figures out the radial flux machine. Over here the axial flux machine is something different, and the direction of the flux is something which is indicated by this dotted lines. So here what you see is the direction of the magnetic field, and that is going to pass through the stator part, and therefore this will be the rotor, and the other part where the windings are mounted, it's a stator, and the direction of the flux is in the same direction of the shaft, and therefore it's called the axial flux. Here the direction of the flux is actually perpendicular to the shaft, and it's a radial flux machine. So this is an important difference to be understood for motor design. Let's now move ahead and look into the design for the stator. So how do we choose the stator number of slots and winding topology. So the number of stator slots and the configuration of the winding is very important. Now the three-phase winding for a motor can be configured in many different ways. It can be connected in star or delta, which is the most simple connection, but there are other ways of connecting a winding as well. So for stator number of slots, there are certain rules which are followed such that this stator number of slots will be a valid number. So what are these rules? Let's see those rules. So the first is number of slots per pole pair should be always greater than 1. So per pole pair, whatever are the number of slots, that should be greater than 1. And this ratio, or we can say the slots per pole pair, is always higher. So here you have more number of slots than pole pair. So why is it required? Because usually the magnetic poles will be generating much more magnetic effect than the conductors which are there inside the slot. So there may be number of parallel paths in a winding, there may be number of multiple conductors in a slot, and the magnetic effect generated by those ampere turns, which is required to be higher than the effect of the poles. So the second rule is slots per phase per parallel path should be an integer number. So if you are choosing the number of slots and you have 3 number of phases for the motor, then number of parallel paths and the slots should be chosen in such a way that it is resulting into an integer number. It should not be a fractional number. The third rule is number of pole pairs divided by parallel path should be equal to an even number. So 2 times k, where k is an integer, and basically the rule stands here, this should be an even number. So parallel paths should be always equivalent to the number of pole pairs times 2k. So this is the third rule, and pole pairs per parallel path should be an even number. The last rule is number of slots per phase per greatest common divisor of slots and the phase should be equal to an integer number. So here we take gross common divisor GCD of the values of slots and the phase, and that should be equal to an integer number. It should not be equal to floating point number or a non-integer value. So now let's move and let's discuss about why do we need a computer simulation for a motor design. So as we know, there are many different types of shape, geometry and material, and solving the electromagnetic equation is basically required to calculate the torque developed by the machine. So in order to estimate the torque which is developed by the machine with a given excitation, you need to solve the fundamental electromagnetic equations. So this fundamental electromagnetic equation are known as the Maxwell's equations. So basically the computer simulation tool will be solving Maxwell's equation, and it's always better to simulate and virtually test the motor before manufacturing. So the computer simulation for a motor design is very much required in order to virtually test the machine before actually making a prototype or going for the manufacturing. So what is this? What are the steps? So the steps are like this, where you have an electrical circuit, and from the simple electrical circuit you develop electromagnetic arrangement, or we can say the electromagnetic equations. Now those electromagnetic equations will be producing the mechanical forces, and due to the losses of the machine there may be certain thermal effects. So these are the fields of interest, right? So the motor design is not a single activity where you deal with only electrical circuits, where you have resistor, capacitor, inductor, and a source or excitation, but it is also related to electromagnetics. It's also related to mechanical forces which are developed, and ultimately none of the motor is going to be perfect, right, or 100% efficient. So each motor is going to have some kind of losses which will result into temperature rise, and this different field of study, electrostatic, electromagnetic, mechanical, and thermal, basically requires a multi-physics approach for a motor design, and therefore the finite element analysis is one of the method which is preferred for computer simulation. We are not going into detail of finite element analysis, but how it works, basically it divides the geometry into fine number of meshes and it solves the equations for various different types of meshes. When the equations are solved for all the meshes, you have all the performance data for the given geometry. So the finite element analysis and solution of the Maxwell's equation, and these are the complex tasks required for a motor design exercise, and therefore there is a powerful computational requirement and powerful software tool is required for the motor design. So let's now move on and let's go to the ANSYS RMxprt based motor design. Before we jump into the ANSYS tool, let me explain you what is RMxprt. So RMxprt is basically rotating machine expert tool, and it is based on template. So the template are already available in this tool to quickly configure your motor design case. Now, what is a template? So if you remember our analogy to the motor, where there are various types of footwear for human being, right? Similarly, there are many types of motor for different applications. So if I give you an idea about how a shoemaker is going to make the shoes, so shoemaker might have some idea about the dimension and the size and the shape of a leg, right, for which he is going to design the shoes for. Similarly, if you have the fundamental idea of your motor design, you can jumpstart your design with the template based design tool. So this is going to create simple template like this shoe mold. So a shoemaker normally uses this kind of wooden mold for making a shoe, and this is basically a template, and based on this template the shoemaker is going to quickly configure the material around this and make the shoes ready quickly. So similarly, the ANSYS RMxprt is also the tool which will configure your motor quickly. So let's see ANSYS RMxprt first. So here I have opened the ANSYS Electronic Desktop 2020 R1. Basically, the ANSYS Electronic Desktop is a combination of different tools used for electronic and electrical design. So if I click on the new over here, I'm going to basically create a new project. So the moment I click over new, all these points are going to get activated, where I can see open example, save as, or close, and other examples. What I'm able to see over here in the menu is HFSS, Q3D, Circuit, IcePack, Maxwell, and Simplorer. So these are the fundamental tools which are embedded into a common package known as ANSYS Electronic Desktop. And here there are other options as well, where you can get the help and you can configure this GUI from general options. So what are these different packages included in the electronic desktop? So here is HFSS, here is Q3D, Basically HFSS and Q3D are for high frequency design, maybe for example an antenna design. Circuit is basically you can create your schematic. The ISPAC is basically the thermal analysis of electrical and electronics, and it can be applicable to the printed circuit boards as well. Maxwell is fundamentally the electromagnetic software. So Maxwell 2D, 3D and Maxwell circuit and RMxprt is what we are going to start with now. Simplorer is basically a tool where you can do the multiple domain analysis. So let's start with the Maxwell and let's open the fundamental tool over here, which is RMxprt. So here I'm going to open the RMxprt and let's see how we can jumpstart our motor design. So when I click on the RMxprt, this will ask for the motor type, and you can see here there are many different types of motor listed over here, and you can choose any from here. So if I get RMxprt solution and a standard machine type, then this menu will get activated and I can decide which motor I want to start with. So let us start with a permanent magnet DC motor. So basically the permanent magnet DC motor is the most simple version of any motor, and let's start the design. So this is going to create a project over here in the project manager, and this project manager will show the different parts of this project. And what are these different parts of the project? Here is the first machine and stator. If you expand the options, you will find the stator, rotor, commutator, shaft. These are all the components or the constructional parts of the machine. Now, how to jumpstart our design? So basically you can double click on the machine and you can decide whether you have how many number of poles you have. So let's say 2 is the default value. Let me keep it as 4. So we have 4 number of poles, and our reference speed may be let's say 2000 number of RPMs. I need to basically work out a math in order to determine all these values. I'm going to just assume some values in order to explain how RMxprt tool works. So here is the stator. If I double click on the stator, I can decide on the outer diameter. Let me decide it to be 80 mm. The inner diameter of the stator is basically, let's say 60 mm. The length is 100, and we can actually assign the material as well. I'm not going to assign it now. I'm going to just create the geometry of the stator. So here is the green color geometry of the stator which we have, and on that we can actually add permanent magnets. So if you add the length of the permanent magnet, let's say it's 5 and thickness is 2, basically we are going to add 4 pole permanent magnets over stator like this. Now I can click on the rotor and I can decide about number of slots. Let's say they are 14. Outer diameter, I need to keep in mind about the stator outer diameter. Let me check on that. What was the number I fit in? So the inner diameter of this stator is basically 60. So my outer diameter of the rotor should be less than 60. And let me keep it as 55. I'm assuming the air gap of 5 mm. It may not be the right guess. Let me keep it as 2 mm air gap. And the inner diameter I'm taking is at 20, and I'm assigning the length as 100, and I can assign the material over here, and I can choose the slot type as well. So what is the design of the slot which we want to develop? So if I select 4, then it can be like this. So if I do apply and OK, then this is the geometry of the rotor which is developed, right? So if I click on the machine, now here basically what you are able to see is the motor develop which is a 4-pole permanent magnet DC motor. Now basically we need to develop winding over here, and we can do so by actually providing this winding data, and if we fill in all these values, we can actually create the slots and tooth arrangement on the rotor. So this is going to be a wound rotor and permanent magnet stator kind of an arrangement. So this is the arrangement, and this is how quickly you can develop the geometry, you can assign the material, and you can start your analysis. Because I haven't entered all the values for creating the slots, let me open the example for permanent magnet DC motor. How do I open the example? Let me close this first. So I'm going to click on the desktop here. Here you can see there are 4 options: desktop, view, simulation, result, and automation. So these are the 5 options which you can use for quick change of the view. So if I go to desktop and click on close, then I can actually close the standard design, and now I can open the example. So when I open the example, this will actually go through the installation directory, and I can decide on RMxprt folder, and inside RMxprt these many number of designs are present. So let me open the PMDC, and the PMDC one is available over here. So now I am able to open the permanent magnet DC motor, where it's a 2-pole motor, and there are number of slots and tooth arrangement where the winding will be over here inside the slots. So this is the configuration which is already present, and this is the fundamental permanent magnet DC motor. And let's see this example. What are the details given over here? So if you click on the pole, basically the magnet type or the material of the magnet is defined over here. If I click over here on the magnet type, I can actually understand what is the magnetic material I'm going to use for my motor. So if I click over here and basically see this XG196/96 is a RMxprt origin magnetic material, and I can basically go to view and edit material over here, and I can click on the BH curve in order to understand about what is the type of this permanent magnet. So if I see this BH curve, here on the y-axis we have B in Tesla, and on the x-axis we have H in amperes per meter. So this is the BH curve for the permanent magnet, and basically it is the combination of B and H values, and you can actually add and amend those values, and you can actually swap X and Y data over here as well. So there are multiple options, and you can actually change the unit of B and H values as well over here. So if I click on cancel and go back to the material, so here these are the parameters which are entered over here. Most of the values are 0 because it's a default material in the library. So where are all the materials? So in order to see the materials available, I need to select all the libraries. So right now we have selected only project definitions, but we can actually select all the libraries. So when I click on select all the libraries will be included over here, and we will be able to see many such systems. So for example, there is Arnold Magnetics, China Steel, and these are basically the material manufacturers for motors. You have Granta, you have Hitachi Metals, and so on. So these are all the materials available, and if you scroll down through this, there are a whole lot of materials, and I can basically categorize them according to the steel, according to the conductor, and the magnet. So if I click on the type over here, I can make a short list of all types similarly. So here we have all the steels, and then going below we have all the magnets, and basically you can see their characteristics, and you can go to view added material, and this represents the BH curve of manufacturer's datasheet. So the ANSYS supports a wide range of material library, and there are many built-in materials which are used for your reference. Now in case of your material which is not fitting into this, right, or you are not using any standard library, you can basically add your material definitions as well. So it's quite easy to add your own material characteristics and then use it for the analysis. So this is about the material library, and you can see there are basically three categories, where it's magnet and steel and the conductor. So whether it's a core material or the winding material, both are available over here. So this is about the material library, and you can basically filter it out and do the quick analysis for materials over here in this window. And so let me cancel this and let's keep the default values. So this is about the material. And similarly, if you go to the rotor, the rotor steel type is also defined over here. So if I go to rotor steel type and see the BH curve for that, I can see that curve for core material as well. So this is the core material for the rotor core. It's basically the steel, and the BH curve for that is available over here. So let me go back and cancel this, and probably I opened many windows, but I think you can configure the material type when you double click on the different parts of the motor. So similarly, you can decide about the commutator design, where it's type of the commutator, the diameter, length, and the insulation thickness. So once this is available, you can actually go to the analysis and run the analysis in the RMxprt, and it is going to quickly come to the results part because it's just an analytical calculation. So let's do the analytical calculation for one of the example, and let's try to understand what are the results. So in order to do that, I'm going to now choose permanent magnet synchronous motor. So let me close this. I'm going to close this and open another example for permanent magnet synchronous motor. So permanent magnet synchronous motors are here actually named as adjustable speed synchronous motor. So if I open this, I can select the adjustable speed synchronous motor, and I can see the design of permanent magnet motor. So here is the design template readily available. Let's not modify anything, and let's try to run the setup. And if you see this, you can basically zoom in, and you can see what are the things available over here. You can actually have a look at the slots and the winding, and basically the winding configuration is also done available over here. So the difference of the coil in terms of number of slots is 5, and you can see the parallel number of branches are 1. The conductors per slot, there are 52 numbers of conductors. Here you can decide about the wire size as well. So if I basically right click over here, I can actually connect all coils and try to see how these coils are connected. So this coil 1, 2, 3, 4, 5, 6 are representing the different phases. So here you have the in slot number and the out slot number, which are indicated over here, and the A, B, and C are the 3 phases of the motor. So I can disconnect the coil over here, and I can just enable the connection of one phase alone. So this is the connection for A phase, and basically if you see, the A phase winding starts from this part, and basically after 5 number of slots, 1, 2, 3, 4 and 5, this wire is connected to this wire. So basically the coil pitch is 5 number of slots over here, and which we have seen already in the configuration. Here the coil pitch is 1, and you can decide about the coil pitch, and you can actually configure your windings as well, and you can see the winding patterns available over here, and you can basically select the type of the winding, whether it's a whole coil or half coil, or you can make a user defined winding as well. So these are the options available. And if you want to see the rotor alone, basically this is the rotor, and as we have seen, this is surface mounted permanent magnet motor, and we can actually configure this machine in a lot of different ways. So let me explain you how we can configure this machine into let's say outer rotor motor. So I'm interested to configure this machine as outer rotor motor. I need to change the rotor position to outer rotor. So if I click over here and choose the outer rotor and click apply and OK, this is going to change the orientation of the slots, right? So earlier the slots were available on the inner periphery of the stator. Now they are available on the outer periphery of the stator. So how do I make outrunner motor or outer rotor motor? I need to change the dimensions of the rotor now. How do I change the dimension of the rotor? I need to first check the dimension of the stator. So basically the stator outer diameter is 120 mm and inner diameter is 75 mm. So I need to keep in mind about 120 mm as outer diameter, and then I can double click on the rotor, and the outer diameter can be 121. The inner diameter can be 121 and this can be 140. So if I do like this, keeping all other parameters same, then this is going to be configured as the outer rotor motor. And if you zoom in over here, basically you will be able to see the configuration of the stator winding is like this, and the rotor is outside, and basically this can be fitted into a wheel, and I can actually configure the rotor part, right? So if I change the rotor pole type and the thickness of the rotor magnet and the embrace and the offset, I can actually configure my outer rotor motor as well. So the outer rotor motor usually preferred for low power vehicle application. And let me go back to presentation and show you one of the outer rotor motor. So here is the image of an outer rotor motor, and it's basically the wheel of a bicycle. So on the center part of the bicycle wheel, here is the motor, and basically this motor is similar to this kind of a construction. So what you are able to see over here, these are the permanent magnets, and these permanent magnets are basically present on the periphery of the rotor. And here whatever you see in the white color or silver color, these are the segments of permanent magnets. So here are the permanent magnets, and here you have the stator, which is going to be fixed with the axis of the bicycle. So the bicycle center part of the wheel will remain fixed, and that is going to carry the windings. So these are the slots, and these slots will be actually creating the windings. So here these are the windings or the copper material, and this is how you can basically configure your motor. So this blue part is basically the windings, and you can decide the number of conductors you have for slots. And over here what you see is 3 Hall sensors mounted over here. So this is basically a brushless DC motor for a bicycle application. So, and similarly for scooter and other application, even for high power application, this kind of motor configurations are popular. Let's go back to ANSYS and understand about the configurations, and let's actually work out the solution for the given example motor. So here I have opened the first example of adjustable speed synchronous motor, and in order to run the analysis, basically we are going to create multiple files in the same folder. I'm going to save this project into a different location, so I can click on the save as, and I can decide on saving this to my working folder. So let me create a new folder over here, and I'm going to save this into a new folder. So after I have saved to another location, now I will be able to modify the parameters which are read only. So here the things which you can do the analysis and generate multiple files, which will be now possible, and you will be actually saving a copy of the default examples which are supplied with the software installation. So in order to run the analysis, what we are supposed to do is we need to understand the setup of the simulation first. So if you see this setup over here, basically we are going to consider the operation as motor, and we are going to consider the load, which is a constant power mechanical load, and we assume that we have the 550 watt output at 220 volt, and the rated speed is 1500 rpm, and the motor is required to operate at 75 degrees centigrade. So these are the analysis setup which is already done. So if we want to run this, we need to right click on the setup over here, and the setup option is available over here. So just right click on the setup and create and click on analyze. So here is the analyze option, and you can click on that, and this analysis will be done. So when I click on analysis, here is the progress which you can observe over here. In this window, the analysis is running on the local machine, and you can see the progress with this. So basically the analysis has finished, and we can now see the results. So how do we visualize the result, and what are the message manager, right? So here is the message which we have received, and if you see this, the normal completion of simulation on server has happened. So if we see this and try to understand about the results which are produced, so we need to right click on results and click on solution data. So when I right click on the results, there will be many options opening up, and I can click on solution data. And when I click on solution data, I will be able to look at the results of this simulation. So basically, if what you see in this window is the solution. So this is a solution window, and what we are able to see is the finite element analysis input data, and there are many other data available over here. So the full load operation in terms of losses, in terms of different types of losses, and value of the current, and the value of the rated torque, and so on, can be seen from here. So you can actually understand about the material consumption as well. So for the given dimension and for given configuration of the slot and the type of rotor, how much is the consumption of your material. So basically this will really help you to understand quickly about how much is the material required. And there are other parameters as well, such as rotor data, such as permanent magnet, and you can basically understand about what happened to permanent magnets. And there is a design sheet generated, and you can actually copy this design sheet and try to incorporate into your design, which is going to be your very first jumpstart design. So here is the full load data, the iron core losses, total losses, output power, the efficiency value at full load, and the air gap flux density, the stator teeth ampere turns, and so on. So here is a complete design sheet of the motor available to you, and there are actually many parameters which are considered as your input. So whatever we have given as a input in the case setup, that is what is reflecting in the output. So you need to decide about what kind of case you want to set up. And if you want to plot the data, it's also possible to get the value of current over the torque angle. Basically, these are electrical degrees, and if you consider the number of poles, 180 degree over here can be equivalent to the 360 degree mechanical if you have two number of poles, and this input current versus torque angle, which is varying like this. So if you have efficiency versus torque angle, this is the plot which is available. And if you see the air gap flux density, which is varying like this, and you can see the different types of plots. Now basically this is all simple mathematical calculation, and you can see the winding currents under the load. So these are the value of the current flowing from the stator winding, and these are according to our assumption of the control type of the motor. So what is the control type of the motor? It is basically defined over here, and it's a DC control type, and you can see the circuit type and other parameters which we have given as input. So you can change the control type, and the current excitation is going to change. So this is about the first analysis which we have done with the RMxprt. Now RMxprt is just kind of a calculator with a decent GUI or graphical user interface. Now what can be done further? Now can we know that whether this permanent magnet is fully utilized, whether there is going to be a saturation of the stator core or rotor? In order to understand all minute details of the motor, you can actually go to the next level of analysis, which is known as Maxwell analysis. So from RMxprt you can actually develop this motor, and you can know about how this motor is going to function with electromagnetic analysis. So this is an analytical tool, and we are now going to switch to the ANSYS Maxwell. How do I generate an ANSYS Maxwell design? To create the Maxwell 2D analysis, I need to right click on analysis and click on create Maxwell design. So if I select analysis over here and choose the option create Maxwell design, it will open a new dialog box. So basically I can select the setup and give a name to that setup, and I can basically provide a variation as well over here, and I can decide whether I want to get Maxwell 2D design or 3D design. So let me generate a Maxwell 2D design for this standard motor. So if I click on OK, now automatically the design will be created, and there are multiple files which will be added into our project manager. So what you are able to see over here is the RMxprt is creating design on its own related to excitation, related to its geometry, and related to material assignment as well. So whatever you are experiencing, this all process, you might be required to do manually if you do not have this software feature. And basically you can do many more analysis from this tool as well. So if you see, the entire 2D design has been generated, and you can see in the project manager there are a lot of things available. So in order to do this, there are many empty plots which are created. Let me close that. Because we haven't run the Maxwell simulation, we are not getting any result now, but when we have some kind of analysis done over here, we will be able to see some results. So if you see over here, we have around 1/4 part of the motor available over here. So why do we have the 1/4 part of the motor? Because we can take the advantage of the symmetry of the motor and do the analysis at much faster speed, so in less time basically. So if you see now in the project, what we have added is the RMxprt design, which was earlier present, and we have added the Maxwell 2D design as well. So now let's focus on what is there in the Maxwell 2D design. So if you see over here, there are models, there are boundaries, excitation, parameters and meshes created, and here are certain analysis and optimetrics as well, and results will be available over here. So this many results are available once you run your 2D analysis. So, and what you are able to see over here, so these are basically the materials which are assigned to the geometries. If you have done any analysis with the 2D software, you will be knowing that how do you create the geometries. So basically you develop a circle, then you cut out the circle from the bigger one, you make something similar to the stator part, you have the rotor circles, and then you have the permanent magnet, and then you add windings, or we can say the coils, and there will be slot and tooth arrangement. So these are the geometries which are created. Not only the geometries are created, the materials are also added by default. So if you click on coil 1, this is going to be activated. So this is the coil 1, here is the coil 2, and here is coil 3. So if you see this coils, basically these are the 3 different phases, and here is what you have as coil return. So if I click on over here, this is a coil return, and this is also the coil return. And if you see the material type, this is M1924G, which is the material assigned to this area which is highlighted, and this is basically the vacuum. And if you see the rotor, which is of this type, and this is the stator, and so we have the stator material, rotor material, and the coils. So these are the coil groups, and you can basically see the unite and subtrate. Basically these are related to the geometry part. And if you see over here, there is a coil 0, and there are so many materials available over here. So this is really a complex structure. If you start building yourself, it may take a lot of time, and that is why the ANSYS RMxprt tool is developed. So if you just put in your diameters and get quickly your 2D geometry ready for the analysis. So these are the copper, and these are the material. And if we see over here, this is the magnet part, what you see as highlighted in the pink color, and these are the materials which are added over here. So here are the coppers, here are the coils, and this is the coil 1, 2, and so on. And basically you can see there are multiple number of coils. If I keep on minimizing all this, so these are all the coils. Now over here, if I go to this model, and if I see the boundaries and the excitation. So now if I click over here and try to see the excitation, where is phase A coil, phase B coil and phase C coil, I can actually see those coils spread in the different parts. So I need to deselect this one. Okay, now and over phase C, this is the phase C. So over here these are the phase winding excitations given. So all these things are readily available when you translate your RMxprt model into a Maxwell design. So this is about the excitation, the boundaries and the mesh. So here what you have is the main and the magnetic mesh created over here. You can basically configure that data from here. So let's now run the default analysis and let's try to see the setup over here. So the setup over here is going to be the advanced one, and there are solver and general values. So how much is going to be the stop time and what is the step time, and you can basically do the high performance computation over here, and you can do this setup. You can run this setup 1. So when I right click on analysis and click on analyze, Maxwell 2D analysis is going to run on my computer. So if I do this, let's see the analyze, and here it's going to now take a bit long compared to what we have seen for RMxprt, because RMxprt was just an analytical tool, and now whatever is happening over here in the progress, that may take more time depending on the speed of your machine. So now the simulation has finished, and we can actually see some of the results now. So let's see what are the results available, and let's try to see the plots for the torque. If I double click over here, these are the value of the torque over the period of time, and these are the value of the current, and you can basically configure which currents you want to plot and what you want to add into the plot. So this analysis will now give you all detailed values for your motor. So the flux linkages over the period of time, it's basically the sine values, and these are the A, B and C phase flux linkages, the value of LD and LQ flux in the D and Q axis. So over and above this, you can actually get to know about different things related to fields as well. So whatever is this field overlay will give you an idea about what are the fields available and how you can plot this. So if I'm interested to know about the magnetic field intensity, I can select the geometry and generate that plot. So I can select the stator and rotor and permanent magnet, and I can select the fields which are to be plotted for this geometry. And this is what are the options I need to select, and I'm interested to plot the magnitude of the B vector, and this is going to develop the plot for magnetic fields. So once you have finished the analysis, you can actually look into the message manager and confirm that the analysis was run. In order to see the fields and the plot of the fields, you can right click on the results and find out the field overlays over here. In order to plot the field, you need to select a geometry. So let me select all the geometry and plot the magnetic field flux lines A. So here I'm going to have the field flux lines which are plotted like this. So I'm going to create a field plot of flux lines, and if I click on OK, here is the field plot available. And as you can see, these things are available as a rainbow spectrum. So you can see the value of A in Weber per meter square, and these values are available in rainbow spectrum colors. So I can have the number of divisions to be as high as, let's say, 60, and if I apply, I can see the high density of the flux lines. So once you have plotted the flux lines, you can actually create many different plots. So there are many parameters which you can plot, and if you can go to the fields, you can plot flux lines, you can plot H, B values, J values, and you can actually plot the core loss and total losses and temperature as well. So these are the fields available for plot, and here we have plotted the magnetic lines, and let me create the plot for B as well. So if I create the plot of B, this will be created like this. So this is the flux density B Tesla, and you can see the value of the flux density at time period given specified by here, and the degree position of the rotor is 7.5 degrees. So this is the situation inside the motor, and you can actually create a study where you can learn how the motor works and what will happen under different excitation conditions. So whatever is the phase excitation you have given for phase A, B and C, those excitation is going to be creating the field vectors, and you can see the magnetic field density over here. So let us try to plot an animation. Let's try to animate the plot, and in order to do animation we need to have more time values. So for having more time values, we need to have parametric sweep analysis. So how can we do the parametric sweep analysis? You can go to simulation, you can go to optimetrics over here, and in optimetrics option you can actually select the parametric study. So if you create a parametric study, I need to basically create a variable, and let me create a variable over here. So I'm creating a new variable. Let's say I'm going to name this as T1, and basically its unit is time, and I can select the unit from over here, and type of the unit is time, and I can keep it in milliseconds. So once I have created this T1, I can basically assign a parametric setup over here. So now I need to create on add, select the variable T1, and we can have a linear step. Basically the start value is from 0, and we can run it at till the required milliseconds, and I can select this as 10, and number of steps are 1, and I can add this, or I can select number of steps as 2. So I need to delete this, and T1, let me update, and OK. So here you can see there are total 10 millisecond, and there are total 6 steps generated in this. And when you click OK, the optimetrics parametric setup is done. So you can double click over here and see what are the parameters you have set. Now once you analyze this, you will be able to get different scopes available, and you can find out the values of flux density and field intensity at different point of time. So while the simulation is running on my machine, let's go back to the presentation part and let's see what are the things available. So basically, let's now talk about the power converter. We are going to just have a basic idea about what is the operation of a power converter for a three-phase motor. So this is the arrangement where we have a permanent magnet rotor and a three-phase winding. This three-phase inverter will supply the three-phase excitation to this winding. So in the case of an electric vehicle, the battery serves as an energy storage element. The power converter is going to provide voltage and current input to the three-phase winding, and the motor is going to provide torque and speed output. So the entire system can be analyzed into ANSYS electronic desktop, and we can use the Simplorer, which is the part of the ANSYS software, to understand about the inverter operation. And basically it is as equal as schematic and design language. So you can also analyze the operation of the inverter part, and you can also see the inductances and the rotor part as well, and you can make a simulation of motor along with the power circuit. So motor along with the power converter circuit is basically called as a drive, and this drive operation for an EV application can be analyzed using ANSYS software along with the Simplorer tool. So let's move ahead and now talk about what is the difference between Maxwell design and RMxprt design. So the fundamental difference is RMxprt is a template based tool. It is based on the analytical equations, and it uses the simple mathematics and geometry, and it serves as a very good start point for your design. So while the parametric analysis is running on the machine, let me show you the Maxwell circuit options. So if you double click over here, you will be able to see the Maxwell circuit, which is developed by creating the Maxwell 2D model. So let me show you this, and let us now see the analysis done by Maxwell circuits. So the Maxwell circuit has actually created a three-phase inverter over here, and what you are able to see over here is the winding inductances and the mathematical model of the motor. So apart from this, there are ammeters which will be measuring the current, and these are the power devices which are basically forming the IGBT and MOSFET in the real case. So this is a switch which can only conduct in the top to bottom direction because of a diode connected over here, and whenever the freewheeling action is going to happen, that can be represented by this anti-parallel diode connected in parallel with the IGBT, or it can be the body diode of a MOSFET. So these are the switch models, and these are the diodes connected, and if you can see, there are 1, 2 and 3 number of top switches or high side switches, and there are 3 number of low side switches which are represented over here. And as you can see, these switches are triggered by this voltage sources. So these are the voltage sources which are basically 6 different voltage sources, and they will be actually making on and off the switches, and this on and off is going to happen in such a way that they are going to produce the 120 degree of operation. And if you remember, we had a 220 volt motor operation when we started our analysis in the RMxprt. So you can see that it is divided into 110 volt and 110 volt two different DC sources. So these two different DC sources will be actually representing the battery voltage system in case of an electric vehicle. So here is the Maxwell circuit associated with this model, and as you can see over here, it is basically the part of the project itself. So here you have the first folder as RMxprt design, here as a Maxwell circuit, and the last one is the Maxwell 2D design. So these are the options which we have seen in the software, and let us see the progress for the parametric analysis. So the parametric analysis is basically about to complete now, and after this analysis is done, we will be able to see different field plots, and we can actually create the animation from multiple time values. So once the parametric analysis is done, you can actually see the animation from the field plots. So here I have plotted A for this geometry, and I can right click over here and click on animation and create the animation. So this is what the animation is created, and let's analyze this at a very low speed. And when you are able to see, there is higher value of Weber per meter represented as a red color, and the lowest value or the negative values are represented as blue color. So the red and the blue lines are occurring in such a way that they are going to provide the torque for the rotor. So let's try to analyze it from the beginning. So here I have the positive direction of current or positive value of Weber per meter over here, and therefore the rotor is going to get attracted to these coils. And in the next step, what you see is that red values are now going to get reduced, and here you can see the blue values are coming. So here is a negative part, and this is going to actually do the repulsion. So earlier there was attraction part over here, and this is going to create the repulsion effect. And if you analyze this, you can see the field line of plots for various conditions. And when the rotor is going to rotate in this direction, there will be another field lines will be available over here in order to attract the other magnetic pole of the rotor. So if I continuously play this, you will be able to get the idea about how the flux distribution is happening, and you can actually try to understand about the overall motor operation. So we have now seen the ANSYS Maxwell, and we have seen the RMxprt, we have seen the Maxwell circuit where it is represented as a three-phase inverter, and therefore ANSYS represents the complete multiphysics analysis for the motor design. So let's get back to the presentation, and you can actually export your analysis into a GIF file or maybe another animation file which can run standalone, and you can include that in your report as well. So this is what we have seen, and this is the part of inverter circuit along with the motor. And remember, the motor for its analysis requires some kind of excitation, so you need to know about inverter operation and how the three-phase windings are excited. Then you can do the analysis of the motor. So we have seen the difference between RMxprt and the Maxwell as well, and let's now make the concluding remarks for this short course. So motor power estimation is the first step for the motor design. You need to understand the application, you need to resolve the forces acting on the motor or the torque and speed requirement of the motor, and then you can start your motor design. So the next step after you have the motor power estimation or motor speed torque range estimation, the next step is the motor sizing and performance analysis. So for motor sizing and performance analysis, you need to solve a lot of equations, and for that we need a powerful software tool. And ANSYS electronic desktop along with ANSYS Maxwell and RMxprt is such a powerful tool where we can use it for our analysis. So the motor design is multi-physics activity, and different application demands different optimization. So for example, your electric vehicle motor can be very compact and low weight, but at the same time you need to take care of cooling of the motor as well. So it's not only about the material characteristics, you need to take care of the temperature in the different part of the motor as well. So the temperature in the different parts of the motor along with electromagnetics effects can be solved by multi-physics solvers such as ANSYS. So here the ANSYS basically supports both template based tool, which is RMxprt, and the new design can be also created with the Maxwell. So this is the end of this video. Thank you. Hello friends, welcome to Basics of Electric Vehicle Simulation using ANSYS course series by Skill-Lync. I welcome you all to learn the third module of this course series as DC-DC converter for electric vehicle application. In this module, we are going to cover how ANSYS can be useful for the design of DC-DC converters, which is one of the subsystem of electric vehicles. Let's start with about this course. This is a short course on understanding of DC-DC converters design and what are the features of the ANSYS which can be used for this design. So first we are going to cover electric vehicle power system architecture, and then we will be having a discussion at beginner level for DC-DC power converters used for electric vehicle application. So there are different types of power converters for electric vehicle. It may be a motor driver, it can be a charger, or it can be a DC-DC converter. We are going to focus on DC-DC converters for this course. We will also look at what are the product development stages for a power converter and how ANSYS tools are useful for this product development efforts, and how engineers can take the advantage of ANSYS tools for power converter design and development. So this is a short course and we are going to quickly review about the features of ANSYS tools. We will also demonstrate ANSYS PE expert, that is power electronics expert, and SI wave, that is signal integrity wave, for DC-DC converter design. So these are the two different tools that we are going to demonstrate in this short course. Before we proceed, let me tell you about the learning aids. So the topics which we are going to cover, they are going to mark with an I. The topics which are not included are going to have this symbol. The topics which we will be focusing on is represented by the symbol of a hand, and the topics which we are going to consider as a black box is having this black box sign. So these legends will help you to know about what is included, what is not included, and in what depth the typical discussion is going on. So let's start with the DC-DC converter course. So what exactly you are going to learn in this course? So the very first thing is we are going to have a look at the overview of electric vehicle power system. So electric vehicle power system consists of source and load. So if we classify into two, basically the power system can be divided into two major things. So one is the source, or we can say the supply, and the other is the load, or we can say the electrical loads which are going to consume the electrical power. So source will be generating the electrical power, load will be receiving or consuming the electrical power. So when we talk about a power system in electrical engineering, we talk about the overall electrical network feeding all electrical loads. But here we are going to talk about an automotive power system used for electric vehicles. So we are going to see the source as a battery, and we are going to see the load can be a motor and other auxiliary load systems. So we will see what are the propulsion system and the auxiliary systems for an electric vehicle. We will understand the basics of electric vehicle battery system and what is the choice of system voltage, and we are going to focus more on DCDC converter types for electric vehicle application, and we are going to select one of the DCDC converter and we will see how this converter can be designed using ANSYS tools. And there are various ANSYS tools available for different stages of design. So when you start your design, you may start with a template based design using ANSYS PExpert. So that is covered in the course. You can actually do the circuit simulation like any other simulator using ANSYS Twin Builder and ANSYS Simploader. You will be also able to see the magnetic analysis of high frequency transformer with ANSYS PEmag, and we will be also looking at electrothermal analysis of printed circuit board with ANSYS Signal Integrity Wave. And we can also do thermal design of power converter, or we can say the cooling design of or cooling system design of power converters using ANSYS iSpec. So there are various tools available over here, and this combination of tool are actually included as a part of ANSYS electromagnetic suite. So ANSYS electromagnetic suite comes up with a combination of all this, and that is also known as ANSYS electronic desktop. So we are going to have a look at the ANSYS PExpert, ANSYS PEmag and ANSYS SI Wave for DC-DC converter application. Let's start with the first video, and here what you are going to learn, you are going to learn about automotive electrical and electronic system. So what are electrical systems inside an automobile? That is what we are going to start with, and then we will also see what are the components, what are the subsystems inside an electric vehicle. After that we are going to cover why electric vehicle needs two different voltage level systems. So why there are different voltage systems required in an electric vehicle. We will also see why overall vehicle efficiency is given high importance and what is the reason for choosing the high voltage system. And then we are going to see the basics of EV battery pack system. So electric vehicle battery pack, how is it constructed and how it is made from using different cells and modules. We are going to look at the application of DC-DC converter systems. So these are the topics which are covered in this video. Let us start with introduction to automotive electrical and electronic system. So here let us understand why an automobile requires an electrical and electronic system. So there are many systems which operates on electricity. So which are the minimum systems or which are the bare minimum things inside an automobile which operates on electricity? So we are going to have a look at this, and we will also talk about what are the recent advancements. So if you look at this picture, you can see these are the bare minimum things which are electrical and electronics in an automobile. So starting from the engine starter system, right? So the engine starter system consists of an ignition coil, a spark plug, an alternator, a regulator and a solenoid or a starter motor. So these are the electrical systems which are required to start the engine. Now in order to operate and control the engine, there are other electrical systems required. So basically here there is a battery which will be part of an energy storage system, and this battery actually helps to run all this electrical load inside an automobile to satisfy the requirements. So here the alternator which is connected to the shaft of the engine will be generating more electrical power once the engine is started, and that can also charge the battery as well, or that can keep on maintaining the charge of the battery. So there are other electrical systems as well, which are lighting, audio systems, and the lighting can consist of the headlights, tail lights, the inside light, or we can call it as a room lamp, or it can be horn system, and so on. These are the bare minimum things required in an automotive. So we are talking about the IC engine based vehicle here, and over here there are many electrical electronic systems. So for example, there may be certain panel switches, there may be certain wiper systems, and there are many other electrical and electronic items inside a conventional IC engine based vehicle. And let's talk about what are the recent advancements. So the recent advancements are, now there are many systems added over and above this, and those systems are nothing but intelligent electronics for safety, control and telemetry of a vehicle. So if I show you the recent advancements, you can see in this picture there are so many things which are added, which are basically electrical and electronics. So if you talk about, for example, a power steering, so an electric power steering, short form is EPS, we see that there is a motor which will be helping your steering to move. There can be an electronic throttle control, there can be an electronic valve timing, idle stop start system, and there are lot of other features. For example, wiper control systems, for example, airbag system, driver alertness, right? And it can be instrument cluster. So nowadays you see there are a lot of advanced displays inside the car. Then you can have a digital turning lights, so, and you can have a regenerative braking system, you can have a parking assist through a camera, you can have electronic stability control, ABS like over here, and this list is going to be endless. So when you start using your car, right, the very first thing is you just open the door of a car, right? So that is the keyless entry. That itself involves a lot of electrical electronic items. So maybe a power window or electric power steering, and all the features listed over here are actually using the electricity, right? And therefore we need to have a battery system which is going to be very, very strong. So nowadays the battery is not only going to help engine starting, but the alternator and the size of the battery are increased in such a way that they are required to satisfy all this load demands. So this is about the introduction to automotive electrical and electronic system. Let us now learn about what is the difference between a conventional vehicle and what is the battery system, or what is the electrical system for electric and hybrid electric vehicle systems. So here are the things. For IC engine vehicles, as we have seen in the previous slide, there is an engine start system which requires a battery, starter motor and an alternator, and usually the battery is 12 volt lead acid type. So there are 6 number of cells connected in series where they have 2 volts each. So the 2 volts each lead acid battery consists of 6 number of units, 6 number of cells connected in series, and that will form a 12 volt lead acid battery. So the auxiliary items which are operating, like horn and headlamps and other things, they will be also operating at a 12 volt. So 12 volt is a standard automotive system which IC engine vehicles have. If you see, probably the automotive systems maybe 20 to 30 years back, people or automakers have started using 42 volt system as well earlier. But now most of the vehicles today running on road have 12 volt battery system, and some of the automakers or some of the component suppliers are also trying with 48 volt system now. So where this electrical system will be helpful apart from starting, so it's not only the starting of engine, but the control of engine will also be done electrical and electronics way. So the sensors, the pumps and actuators are all electrical and electronics operated. So this is one of the area where electrical electronic systems are required inside the vehicle. Now let's talk about electric and hybrid electric vehicles. So unlike IC engine vehicles, these vehicles do not have engine. So the propulsion power is provided by electrical system. So basically the battery and the motor are of high power rating, and they can provide the propulsion power required by an automobile. So electric propulsion system which is using the high voltage, and normally it is lithium ion type battery. So that is the difference between IC engine vehicle and hybrid and electric vehicle. Another difference is auxiliary items operating at low voltage from other battery. So we are going to have a look at why other battery is required, and still the auxiliaries are going to remain same, whether it's IC vehicle or electric vehicle. The auxiliary loads are going to remain as it is, or they are going to be common in both the cases, right? So for that we can use another battery. Now another difference is the charging of battery from external electrical supply. So how does a battery gets charged in case of an IC engine? So an IC engine, the battery is going to help starting. Once the engine has started, the engine is going to run the alternator, or which we can say as a electrical generator. So this generator is going to generate the electricity which is required by the all load, and it can keep on maintaining the charge of the battery. But in case of an electric vehicle, we do not have any engine. So how do we charge the battery? So the battery is getting charged through a charger circuit from external electrical supply. Now how about hybrid electric vehicle? So hybrid electric vehicle is actually the combination of IC engine based vehicles along with the electric vehicle. So we can say that hybrid electric vehicle is going to be sharing the power between engine and electrical system. So the whatever is the internal combustion engine power along with the electric vehicle system, that is going to be shared, and that type of vehicle is known as hybrid electric vehicle. So the hybrid electric vehicle may be using a higher rating of engine, or it may be using a higher rating of electrical system, downsizing the engine. And the reasons may be the engine is not going to be so efficient such as electrical systems. So there are many possibilities in case of hybrid electric vehicle that this electrical and electronic systems will be deployed in both engine control as well as electrical system control. Let us now learn about what is inside an electric vehicle. So as you see in the image, the electric vehicle has an electric traction motor. Basically the traction motor is going to provide the tractive power, or we can call it as a propulsion power, which helps the vehicle to move forward, and it has a high voltage traction battery pack. So what you are able to see in the yellow color are many different cells and modules of a lithium ion battery. So usually this is the traction battery pack which is configured at the lower side of a vehicle, and you can have a front driven like this or an EV can be a rear driven vehicle as well, and this is the electric traction motor in red color. So when we have a high voltage traction battery pack which is going to be useful for propulsion power, we also have some electrical loads which are operating at a lower voltage, and that is called the auxiliary load. And there will be another small battery or low voltage battery which will be helping the auxiliary loads to be supplied. So what you have is the other systems such as power electronic converter, and basically this is nothing but an inverter. So usually this traction motors are of three-phase type and AC type. So how do we get three-phase AC from a DC battery? So that is possible through an inverter circuit. So the power electronic controller in the blue color over here is actually a inverter circuit. Now how do the battery gets charged? So that is done by an AC to DC converter called as onboard charger. So this blue color is again an onboard charger. So the size of this power converters, so which are in blue color, is such that the highest capacity is of inverter. This is the usual case. Then it comes the charger, and then it comes the DCDC converter. So we are going to focus on this DCDC converter in our course. And there are a lot of other systems which are used for cooling of battery, motor and power converters. So we have seen there are total 3 power converters inside an electric vehicle. So these 3 power converters are nothing but DC to AC, which is basically inverter, and this is also known as a motor controller. From battery DC to motor AC supply, this is called an inverter. From single phase or 3-phase AC supply coming from the power system, or we can call it as a external electrical power network, from where you get the electricity to run your household appliances. The same can be used to charge the battery of an electric vehicle, and that type of converter is basically AC to DC converter, and we usually refer them as rectifier. And apart from this, the third category of power converter is a DC-DC converter. So we are going to focus on DC-DC converter operation inside the electric vehicle and how ANSYS can be used for design and development of this particular component. So once you had a look at the actual render image of the car, now we can see a simple block diagram of an electric vehicle. So if you see, we have a high voltage battery used for propulsion. This is going to supply power converter, and power converter will be controlled according to the user inputs. This user inputs are basically the throttle and the brake pedal, and the electric motor will be controlled accordingly through the power converter. So the battery supplies power to the motor through power converter. This motor will be actually driving the vehicle, and that is called a propulsion load. So here is the propulsion load power flow direction. It starts from high voltage battery, it goes to the power converter, then comes to the electric motor, and then comes to the wheel. So from battery to wheel is a propulsion load distribution. Now how does this battery charge? This battery gets charged from an external electrical supply, or we can call it as a grid supply. So the external electrical power supply network or grid is going to help this battery charge, and this charging station will be similar to where you charge your laptop battery pack, or maybe similar to your cell phone. So but actually this charger will be of higher power rating. So this is the charger which will get the high voltage traction battery pack charge. Now we actually have the auxiliary load as well. So for auxiliary load we need an low voltage battery. We are going to see the other reasons why we need another battery and usually this battery is of 12 volt, or in some cases it may be 36 volt or 48 volt, and this high voltage and low voltage battery can be interfaced or can be connected together through a DC-DC converter. So we are going to have a look at this DC-DC converter, which is going to be the part of an electric vehicle system. So the reason behind showing the bidirectional arrow is that this DC-DC converter can actually help those batteries in case when they are going to have less charge left. So the auxiliary load can be supplied from the low voltage battery system, or it can be supplied from the high voltage battery system, depending on the power availability and depending on the control of DC-DC converter. And this is not just one point where DC-DC converters are used. There may be other configurations as well. So this is one just simple example of a DC-DC converter. We are going to have a look at where exactly in the circuit DC-DC converters are required. So let us now understand why does electric vehicle requires different voltage level. So why can't we use the traction batteries for supplying the auxiliary loads? So let's have a look at this question. So the first reason is the standard design of automotive electrical system. So heating, ventilating and air conditioning system, the lighting, the control and the infotainment, or we can say the audio systems, usually works at a lower voltage, and normally this is 12 volt system. So all these automotive systems, whether you call it as a lamp or you call it as a compressor pump or you consider any engine cooling system, those systems are designed at 12 volt standard. So now 12 volt is a standard operating voltage for all these appliances or all these items inside an automobile. Now our question is, why can't we change the design of all such loads to the higher voltage, right? So it would be really difficult to change the design of all these standard appliances at a higher voltage level, and we are going to see what are exactly those higher voltage levels are. So it would be difficult to change those designs, and in order to satisfy these loads in an electric vehicle, we need to have another voltage system as well. So the reason why can't the high voltage battery provide the low voltage using a DC-DC converter? Why do we need a separate 12 volt battery? So there are other reasons as well where we have a 12 volt, or we can say the low voltage battery systems. So it is possible using a DC-DC converter that we can always supply all these auxiliary loads from a main battery, right? But there are a number of reasons behind this. So let's see what are the reasons. So the first reason is in case of a cutoff. So basically the cutoff is a situation where your traction battery pack is fully discharged, or it is fully charged, or it is discharging at a very high rate. So in case of the cutoff, or we can say the disconnection of high voltage battery in the vehicle network, then how do we supply the auxiliary items? So the auxiliary items such as steering, such as door lock and other emergency systems has to be powered on, right? So in case of a failure or cutoff of a high voltage traction battery pack, the low voltage battery continues to power the emergency and other important systems. So this is the reason why two battery systems are going to be useful in case of an electric vehicle. So now what about the low voltage battery type? So in case of an IC engine vehicle, those batteries are of lead acid type, but for new electric vehicle design, the automakers and the battery suppliers are actually making this low voltage battery, which is 12 volt, 36 volt or 48 volt, these batteries are also of lithium ion type. So there are n number of reasons behind that, because of the superior performance of lithium ion battery over the lead acid battery, and you may consider that this low voltage battery will be also sharing the power when it comes to the higher amount of auxiliary loads. And we are going to see further about the overall loads connected to the electrical systems. So let's now learn about electric vehicle voltage levels. So can we operate? Now we answered a couple of questions related to low voltage auxiliary loads and high voltage traction battery pack, but why can't we have a 12 volt motor and a 12 volt inverter system such that we can provide the required power on the wheels? So let's imagine that we are operating an electric four-wheeler on 12 volt battery system. So let's say an electric vehicle which is required to generate an similar amount of power as an engine does. Let's say the power required generate in order to move the vehicle forward at a required speed with a required weight is around 24 kilowatt. So we assume that the 24 kilowatt is the power rating of the motor used over here, and at 24 kilowatt the vehicle runs at a top speed. So if we calculate what is going to happen if the 24 kilowatt are going to be taken from 12 volt battery or at 12 volt. So if I calculate the value of the current, so the current going to be discharged from this 12 volt battery at 24 kilowatt power will be equal to 24 kilo, which is 24,000 watts divided by 12 volt, and this is going to be actually 2000 amperes. So when you are considering such a high value of amperes, you actually do this with a very large size of cable, right, or the cross section area required by the conductor to allow 2000 ampere to pass through, it's going to be very high, right? So if you consider this particular cross section of cable area is going to be used for 5 amperes, probably it requires higher size of conductor cross section for 10 amperes, right? So and when you consider such a high value of amperes, the cable size or the cable cross section area is going to increase drastically. Now what is the problem if the cable cross section area increases? Are the cable going to be costly? No, let's not think of a cost at this moment. Let's talk about the resistance of the cables. So let's say this is the cable used to connect the 12 volt battery from one end to another end, where the 12 volt battery positive terminal is over here, and this is the input positive terminal for a motor controller, and the length of this cable may be somewhere around a few meters, let's say 1 meter, and the total resistance per meter of this cable is, let's say, 2 milliohms. So if we have 2 milliohms of resistance of this cable, which is fairly less, and if we have this current, right, which is 2000 ampere passing through this cable, you can imagine the amount of I square R losses which is going to be resulted in the watts at this situation. So the I square R, which is nothing but the power rating or the loss in terms of watts, will be 2000 square times 2 milli, right? And that is going to be sufficiently high, and it can be correlated to what is a maximum kilowatt, and this is just 1 meter length of a cable, right? And now if you think of let's say the internal resistance of the battery, if you consider the motor winding resistance, if you consider all other cables, right, which are power cables, this efficiency is going to be very poor, right? So as I explained in this calculation, the I square R losses are going to be very high because the current is very high, and these losses are proportional to square of the current. So what is required? So the required thing is to come down to this amperes as low as possible. Now how is that possible? Now do you think that 24 kilowatt power requirement is going to reduce? No, because it is something similar to the engine power, or it may be 50 kilowatt or 70 kilowatt for a very high speed car or very high performance vehicle. So in case of such a power rating, we cannot compromise on the power level of the car, which is in this example 24 kilowatt. Now how do we achieve 24 kilowatt? The only option we have, because fundamentally the power is nothing but voltage times current. So if you have this fundamental equation, and if you want to reduce I square R losses by reducing the value of the current, the only option you have is increase the voltage level. And this is one of the fundamental reason why electric vehicle voltage levels are such a high, right? So it would be possible to run a vehicle at 12 volt, but those vehicles may be of very low power rating type. So maybe the 12 volt battery system can be used for a very low power application, right? So this is one of the reason why electric vehicle have higher voltage levels. So there are other reasons. So when I said electric vehicle and hybrid electric vehicle requires high propulsion power from the battery, and as I explained, the I square R losses in the cable, motor windings and converter circuits, those total is going to be very high, and you can result in such a efficiency which is going to be very poor, or it may be of the range of 50 to 60% if you are running a vehicle at this power level at 12 volt, right? So, and what is the reason? Let's say if we are achieving 60% efficiency, then let's say isn't it good value of the efficiency? Because IC engine vehicles, their overall efficiency is very low. So compared to IC engine vehicles, the electric are offering 60%. Isn't it satisfying? No. Why? Because even if you are operating at a 60% efficiency, your onboard energy is very less, right? So the frequency at which you will charge your battery is going to increase. So your efficiency goes down, the frequency of charging your vehicle is going to be very high, right? So if you think of such a case where your vehicle range is 100 kilometers, right, and you are getting 100 kilometers per charge of a battery, where you have a high voltage battery system. Now if you have a low voltage battery system and the efficiency is now reduced to 60%, your vehicle can actually travel only up to 65 kilometers, for example. So now instead of every 100 kilometer, you need to charge your battery every 65 kilometer, and this is not going to just be the disadvantage on the range per charge, but you are going to reduce the life of the battery as well over the period of time. So this is one of the reason why high voltage system are preferred for electric and hybrid electric vehicles. So we know that high voltage battery systems will be more efficient than the low voltage battery system according to our calculation. So instead of a low voltage battery system which is going to produce high current, it is always preferable to have higher voltage battery systems. Let us know more about electric vehicle battery packs, and we will also discuss about why high voltages and low voltages are required to be linked by a DC-DC converter. So if I take the overall efficiency of a vehicle, and if I do this assumption of stage-wise efficiency, so here let me assume the first stage from battery to power converter is going to have some efficiency, that is efficiency 1 of stage 1. Then power converter block itself will have efficiency 2, and the electric motor will also have the efficiency which is denoted by efficiency 3. And here there will be something called gearbox efficiency or mechanical power transmission system efficiency as well. So if we talk about the flow of power from battery to wheels, there are many different stages. And if I assume fairly that all efficiencies are 80%, which means this is 0.8, this efficiency 2 is also 0.8, which is basically 80%. This is also 80%. Now, what is the overall efficiency from battery to wheels? So these efficiencies are actually connected, or this effect of efficiencies are going to be cascaded and such that they will be multiplied with each other, right? So if you have the gain of the individual blocks connected in series, you can easily calculate how much will be the output in the final stage. So if you multiply 0.8 with 0.8 with again 0.8, your overall efficiency is only 51.2%. So basically, even if all stages are 80% efficient, the overall efficiency from battery to wheels will be reduced to 51%. So this is the effect of efficiency, and why it is taken care in case of battery electric vehicle, because the onboard energy is very less. And now if you consider that this battery is going to run the auxiliary power as well, right, and there are going to be a DC-DC converter over here which will draw some amount of power, and this particular load, which is extra than the propulsion load, will also discharge the battery. So look at the effect on the battery power rating. So for example, if you need let's say around 50 kilowatt hour of energy, right, so on the wheels per 100 kilometers, right, so here we are assuming some number that 50 kilowatt hour amount of energy is required by the vehicle to run for 100 kilometers. And now if you take the energy efficiency of all the stages and multiply that, the battery kilowatt hour may be as high as 80 kilowatt hour. So instead of 50 on wheels, now you are using a very high energy or a very large battery pack which is 80 kilowatt hour, and therefore these systems needs to be very, very efficient. So if they are less efficient, then it is going to actually hamper the overall efficiency of the vehicle. And larger the battery pack, higher is going to be the cost, higher is going to be the charging time, and there are so other disadvantages as well for a large battery pack. But when we consider the high voltage traction battery pack, then the efficiency of this particular stage, where we consider the efficiency of the connectors and the wires used over here, that is going to be far better, right, than a low voltage high current type of a battery pack. So let us now move ahead and have a look at the electric vehicle battery pack, how electric vehicle battery pack is considered, or how electric vehicle battery is actually made. So let's see this basics of EV battery pack. So usually one lithium ion cell produces only 3 to 4 voltage per cell, and actually this is very higher compared to a lead acid battery cell which produces around 2 volt per cell. But now lithium ion batteries or the basic element of a lithium ion cell can produce double of that voltage, and the capacity is also higher compared to the lead acid battery, keeping the volume same. So how the EV batteries are made? So usually these cells will not be able to make it possible. So your cell phone is going to have one cell, your laptop battery pack may be having 4, 6 or 8, 10 number of cells, but an electric vehicle requires 100 or 1000 number of cells. So these cells are configured into different modules, and for EV application the battery pack will be consisting of multiple number of modules. So this is the way in which the battery pack is made, and let us see some of the example. So if I give you an example, so a 12 cell series with X number of parallel cells in each module, and if there are 8 such modules, the entire battery pack will be around 96 cell series, and that is going to produce around 400 volts. Let us understand it clearly. So imagine that I am taking 18650 popular battery cells which are cylindrical in shape, and I am assuming all these cells are positive from the top. Now I have taken 6 cells and I am going to connect all this positive together like this, and all the bottom negatives together like this. So the red colors are actually the wires which are connecting this. Now how do I make a larger battery pack? This can be similar to your power bank which you usually charge your phone from. How to build a larger battery pack? We need to connect more number of cells in series. So this is a 6 parallel group, and we will call this as a 6P. So 6P is this group of blue color cells. Now if I take another series of cell and all this are negative from the top, and if we again connect their bottom like this and their top like this through a wire, then this is again a 6 parallel group but in reverse order. Now if I connect this positive with this negative like this, then basically what we are creating is a series connection of cells. So this is a configuration which I will call as 2 series and 6 parallel. So we can write as 2S6P. Now if I add one more such combination where I have all the cells connected positive on the top, and they are again connected in parallel and connected like this in the bottom, and if I now connect this part, this negative with this positive, let's say this configuration will be a series configuration, and this will be 3 series 6 parallel. So this is how the electric vehicle battery packs are created, and it can be as high as, so if you see the overall electric vehicle battery pack, it can be 96 cell series and maybe X number of cell in parallel. For example, let's say 4 number of cells in parallel. So there are around 400 cells in this kind of an electric vehicle battery pack, and because per cell voltage is around 3 or 3.5, we can consider that multiplying with the number around 100, this will produce 400 volts battery pack. So this is the configuration for an electric vehicle battery pack. How this battery pack is actually arranged in case of automotive. So inside an automotive, how this cylindrical cells. So let's consider this is one such module. So one module consists of many different cells connected in series and parallel, and there are many different modules like all this, and all these modules will be also connected, and that will together form a battery pack. So this is the overall configuration of an electric vehicle battery pack, and therefore you can see that how high voltage battery packs are built for an electric four-wheeler. So let's quickly move ahead and let's find out how much is the highest battery pack voltage level till now available. So we have figured out that high voltage battery pack will be efficient than low voltage one, but how much is the high voltage? So you will find around 400 volt or 300 volt of voltage level for an electric vehicle system, but people are now trying with higher and higher voltages as well. So one of the commercially available vehicle is Porsche Taycan, and this is having 800 volt battery. So what are the advantages of such a high voltage battery pack? So this is one of the image of Porsche Taycan, and you can see in this model all these batteries are configured like this. So whatever you see, the orange color are the cables running through different modules of a battery pack, and different modules will be consisting of many different cells connected in series and parallel, and together they are going to form one unit of a battery pack. What are the advantages? So the advantages are the high voltage system can give consistent high performance, right? So for example, if you take a very low voltage battery system where it's a, let's say it's a 36 volt or 48 volt system, that voltage range, right? So the 48 volt is nominal voltage. When the battery is about to be at, let's say 20% of the charge level, that 48 volt may reduce actually to 40 volt, and this may actually hamper the performance or actually affect the performance in a way such that the top speed of the vehicle may not be maintained when the charge or the percentage level of the battery is 20%. So if the battery voltage is enough high, this performance cannot be compromised. So this is one just example of how low voltage battery systems will affect and how high voltage battery systems can provide the consistent high performance throughout the range of state of charge of the battery, starting from full charge battery to fully discharged battery. The charging time is also going to reduce because the higher voltage chargers will be actually required to supply lower ampere of current. And when you consider the lower ampere of current, the battery capacities are in ampere hours. So if the amperes are lower, the battery can be actually charged in a less amount of time. So this is just a comparison with reference to higher ampere hour and the low voltage battery pack. Now, what is the another advantage? So another advantage is we are going to use less number of cells, and the space and the cabling are going to be reduced, right? So the heavy cables for higher current application will not be there in case of a high voltage battery pack. So the weight and installation space for those cables, which are shown in the orange color over here, they will be actually one of the greatest advantage. So handling and space and the cost of the cable will be reduced comparatively. So this is about a high voltage battery pack. Now let's learn more about why do we need DC-DC converter in an electric vehicle. So as we have listed out, there are more than one reasons. So let us first figure out, so we know that there are auxiliary loads which are operating at a lower voltage, and those auxiliary loads like the lighting, horn system, audio system, telemetry and so on, they require a lower voltage to operate. So therefore we need a DC-DC converter. The other reason is battery to charger station compatibility. So for example, you have an electric vehicle which has 400 volt battery pack, and your charger station is going to provide you, let's say, 300 voltage output. Now in order to match your battery voltage with the charger station output voltage, you need a DC-DC converter there also. So this battery to charger station compatibility is another application of a DC-DC converter inside an electric vehicle. This is again what we have seen in the earlier block diagram. To connect the high voltage traction battery with the low voltage auxiliary battery, there will be a DC-DC converter required. And you can actually use the low voltage less costly battery with a high voltage motor system. So for example, in a hybrid electric vehicle, you can use 400 volt motor system. So using a 400 volt motor system can be advantageous, and when you have a 400 voltage battery pack for a hybrid electric vehicle, the cost may be very high because you need more number of cells in series. So if you want to use a low voltage less costly battery pack, then you can actually have a 48 volt battery system supplying 400 volt bus. So you can have a 48 volt to 400 volt DC-DC converter for driving those higher voltage motor, and that is where you can say that you have a DC-DC converter which will actually reduce the number of cells which are required to be connected in series. So this is one of the application where DC-DC converter is required, and the last and final application can be combining more than one type of energy resources. So there are limitations of the battery, and people are adding ultra capacitors or fuel cell solutions along with the battery. So in an hybrid electric vehicle, you can have a combination of ultra capacitor along with the battery, and you can have a fuel cell also added with the battery. Now when you are going to combine these two, the ultra capacitor and the fuel cell will require a DC-DC converter in order to match the characteristics of the load and their own fuel characteristics, or their own voltage, current, or charge discharge characteristics. So here also you will need a DC-DC converter. So these are some of the areas or some of the reasons why EVs need a DC-DC converter. So let us consider an image, and let's try to see where exactly are these DC-DC converters located in the arrangement of electrical system for an electric vehicle. So this are shown in the figure like this. So here you have a higher voltage battery system, and this is going to be 400 volt battery system. Now this 400 volt battery system can be reduced to 48 volt battery system by a DC-DC converter, which is 400 volt to 48 volt system level DC-DC converter. Now you have a 48 volt bus in the yellow color over here, and this 48 volt can actually supply the 12 volt regulated loads, which can be a water pump, an AC compressor, or maybe any of the other loads. So here also you need a DC-DC converter module which will translate 48 volt to 12 volt regulated output. Now instead of a regulated output, you may require a different type of a DC-DC converter which will maintain just 12 volt as a fixed ratio. So whatever is the voltage available over here, according to the ratio of this converter, this will maintain 12 volt, and there may be a different types of load for this type of converter. Now you can actually directly feed 48 volt over here to the some of the loads which are going to need directly 48 volt, and you may need a 48 volt to 48 volt DC-DC converter as well. Now you may be wondering that why do we need a 48 volt to 48 volt converter? So what is the purpose of using that? We are not changing any voltage level, right? But actually this is going to change the power which is available to the 48 volt load. So from the bus to the load, it can actually regulate this, right? And so if you understand this DC-DC converters, there are two major categories. One is a voltage translator, we call it as a converter, where it can be 48 volt to 400, 48 to 12, and so on. And other category is called actually the controller, so which is called a voltage regulator as well. So the voltage regulator will maintain the 48 volt to the load irrespective of change in the input 48 volt, and it will also control what is the power applied to the load. So 48 volt regulated will actually control the current which is fed to this load, and therefore the power of this load. So for example, electronic power steering or headlamps and other systems which may require a control or a regulation, and these are the type of that DC-DC converter. So in an electric vehicle architecture, you need a system level DC-DC converter or a load side DC-DC converter, and so on. So these are the three major categories which we are going to see. So the first one, as we have seen, charging station compatibility DC-DC converters, the conversion compatibility such as this one, which is going to change 400 volt to 48 volt, and there will be some kind of a delivery DC-DC converters which are actually going to deliver the power to the load. So these are three major categories of DC-DC converters used in electric vehicle. So now let us take an example of 48 volt and 12 volt configuration. So if we see this example here, we are able to see there is on right side of the image we have 48 volt system where you have 48 volt loads connected between positive and negative wire like this, and this can actually include the 48 volt battery as well, and you have a 48 volt starter generator, or we can say the high voltage starter generator. And on the other side of this DC-DC converter, which is the main element over here, you can have a 12 volt system, positive and negative. So the 12 volt and ground can feed the 12 volt load connected in parallel along with a 12 volt starter, which can be a cold crank and which is going to be supported by 12 volt battery. So this is called a 12 volt and 48 volt hybrid automotive electrical system, and this is also going to be require a DC-DC converter, and this can be actually inside an IC engine vehicle or maybe an hybrid or electric vehicle. So DC-DC converters are going to be used popularly for EV and HEV applications. So this is the end of first video, and in the next video we are going to learn about how to use ANSYS for design of such DC-DC converters, what are the available options, how we can simulate this, and what are the different design stages in which the ANSYS tools can be beneficial. Hello friends, welcome to second half of DC-DC converter for EV application short course. In this video we are going to cover how to use ANSYS for design of DC-DC converter and what are the different tools available for simulation and validation of the power converter designs. Let's start with what is included in this course. So in this second video we are going to learn about fundamental DC-DC converters and their operation and their circuit arrangement. We will also see the types of DC-DC converter which can be classified into isolated and non-isolated. We will also see typical DC-DC converter which is known as full bridge DC-DC converter for electric vehicle application. We will see what are the design stages for a power converter, and after that we are going to cover various ANSYS tools for power converter design and development. So the various tools which we are going to see for this is actually the ANSYS PE-Expert is a tool which is for power electronic expert, and this is used for template based design. So similar to RMxprt, which is rotating machine expert, power electronic expert will give us a quick idea or quick start point for template based design. Then we are going to see the ANSYS twin builder. We will not see that one in detail, but we will see how twin builder is used for circuit simulation, and it is also known as ANSYS Simplorer. So Simplorer is now part of a twin builder. Basically this twin builder means that whatever is the system you have in physical world, you can make a twin of that. So you can create a duplicate of that system in a computer. Then we are going to see the power electronic magnetic design of high frequency transformer in ANSYS PE-Mag. After that we will see the electrothermal analysis of PCB with ANSYS SI wave. This is basically for signal integrity and power integrity. And then we will also see the thermal design of printed circuit boards using ANSYS IcePack. So this is what is included for this video. So let's start with fundamentals of a DC-DC converter. So let's say here I have a 100 volt DC supply available, and this 100 volt is required to be, let's say, changed to 25 volt on this load side, and which is load register RL. So how can we change the 100 volt to 25 volt output? So let's assume that we are using a simple resistor to drop down the voltage, right? And based on the voltage divider rule, you can calculate how much should be the value of this resistor to drop down the 75 voltage, right? So this ratio will be also in terms of 1:3, or you are having 25 volt over here, you will be having 75 volt here. So if you choose this also 25 ohms, this will be 75 ohms, and the 75 volt will be dropped across this resistor because this is going to have 1 ampere current. So the total series resistance is 100 ohms, so 100 volt divided by 100, that will be 1 ampere. So if 1 ampere is passing through 75 ohms resistor, 75 volt will be dropped across it and output will be 25 volt. So in order to get the variable output, you need to use a variable resistor like this. And imagine a situation where you have 1 ampere flowing through this and you have 75 volt drop across it. Imagine the value of the I square R. So let's say this RL equals to 25 ohms, and we call this resistor as a control resistor RC, which is 75 ohm. And if you consider the I square R drop in the control resistor RC, this is going to 1 times, or the square of 1, again the same 1 multiplied with 75. So here you will be having 75 watt as drop out of 100 watt which is delivered by this source. So power at source side is 100 times 1 ampere, which is 100 watt, and you have 25 watt output. So in case where you have such a high loss, this cannot be realized in terms of an actual circuit. So in order to do the actual analysis, you cannot use the control resistor or a voltage drop or any linear regulator like a transistor. So what is the preferable solution? Instead of this resistor, we can put a simple switch, and this switch is basically the switch which actually connects and disconnects the source with the load, and this is the origin of power converter system. So where this switch is basically not a physical or mechanical switch, it's a semiconductor control switch, and it can operate at a very high speed. So now you may imagine that if I have 100 voltage over here, and if I close down the switch, the output voltage is not 25, output voltage is 100 volt. But now when I open the switch, the output voltage is 0. So by combination of 0 and 100, I can actually generate the average 25 volt. How? Let's see. So let's say here is a thing where I'm turning on the switch. So when I turn on the switch for this duration, the output voltage is 100 volt, and let's say this is 0 volt line. Now when I turn off the switch, the output voltage is 0. Now I remain the switch off for a definite period of time in such a way that the average voltage over the period is going to be 25 volt. So let's say this duration, which is called off duration, will be around 75%, and this duration called on duration will be around 25% of the total time period t, and the cycle will be repeated after time period t. So that you can see this waveform as average voltage of 25 volt. So if I take the average of this, it can be 25 volt. And again, to calculate the average, you can basically calculate the area under this curve, and or this will give you an RMS value. So this area under the curve will be similar to what is available below constant 25 volt. But now you may see that this is what we expected in the output as a reduced DC output voltage, but what we are getting is the pulses of 100 voltages, right? So this pulses of 100 voltages are may going to, let's say, provide very high voltage instantaneously, But yes, definitely we will need some filter components in order to do the proper DC to DC conversion. But this particular phenomena is at the heart of power converters, and this is how the power converters are more efficient, because this power semiconductor switch is not going to make the losses which are as equal as a voltage divider circuit. Now, what are the losses happening in a power converter? Let's understand this from this phenomena. So we have this as output voltage waveform. So this output voltage waveform is actually developing the average 25 volt using the 100 volt supply. Now what will happen when you are considering the voltage across switch and the current through switch? So let's say we call this as voltage across switch and current through switch, and if we are using this as a MOSFET, I will call this drain, source and gate terminals, where gate is a control terminal and this is drain terminal and this is source terminal. So when you apply the pulse from gate to source, this switch will get turned on and the current will flow from drain to source in this arrangement. Now what will happen actually when the switching occurs? So when the switch is actually in the off condition, so here is a off condition. So during the off condition, the voltage across the switch will be actually the external circuit voltage. Now the moment you try to turn the switch on, this is the on period, where the current in the green color will start flowing and the voltage across the switch will gradually go down. Now whenever you talk about the losses during off state, there are no power losses. So this is the power across switch, which is basically VDS times IDS. So if you do the VDS times IDS, because one is finite value, the other is 0, when the current is finite value, the voltage is 0, so their multiplication results into 0 during steady state. So the conduction losses and the off state losses are minimum if you consider that the on state resistance or this voltage drop is almost 0. So if you assume this line is almost 0 volt, then you can say the conduction losses are also minimum. Now look at the transition period. So this is a transition period when the switch is becoming on from the previous off state, and this is the transition period when the switch is becoming off from the previous on state. So in this situation, there will be a power across the switch which depends on the value of the voltage and the current. And if we assume that the voltage and current are varying like this, it actually depends on the type of the load, type of the MOSFET and the junction capacitance and many other parameters. This two multiplication of VDS and IDS will result into some kind of a power loss, which can be a triangular loss. So this is the area which will result into let's say the power loss. If you calculate this area, you will find out basically the energy over the period of time, which is power over the period of time. You will get this value of energy. So the ideally this switch is going to be efficient than a voltage divider circuit, but this switch are also going to have practically some kind of losses, right? So all the practical switches, let's say in this case, if I consider an IGBT, which is again a popular device for a DC-DC converter in EV application, they will also have this kind of losses. So let's say these are this is emitter, this is collector, and this is the gate terminal. So for this IGBT, there will be collector emitter current and the collector emitter voltage, which will be having similar kind of a waveform, and there will be switching losses and the conduction losses happening. So once we know, so this is a case where it's an ideal power converter and its efficiency is 100%, and this is going to be the practical case where the switches will have some losses. So those losses in the switches will result into heat, and we are going to see how ANSYS deals with the thermal consideration of printed circuit boards which are for power converters. So after you have got this idea, now how do we build an actual power converter? So this is a simple circuit which is comprising of a simple switch, one source and one load. Now in order to actually build a more realistic circuit, we need to understand that these are the pulses which will be received by the load, and these are not enough. We need to make sure that the load is going to experience the smooth output voltage or ripple free output voltage. So what we can do, so yes, exactly, we can connect a capacitor in parallel with the load so that to minimize the voltage ripple. Now similarly, when we are going to do this on and off, the current will also get chopped off. So the chopping of the current will also result into the ripples in the current. So the ripple in the current can also be minimized by putting an inductor in series. So the simple solution is keep an inductor in series, keep a capacitor in parallel with the load, and that can actually make a practical DC-DC converter which is known as a buck converter. So the only thing I need to add over here is a diode parallel to the combination of an inductor L and the capacitor C, such that whenever the load current is going to pass through the switch off condition, that will pass through the diode. So the load current remains continuous. So the diode provides a freewheeling path, and this is where you have a buck converter. So this is the theory of a simple buck converter, where you have one level of voltage in the input and another level of voltage in the output, and here you can connect a load. So this is a simple buck converter, and let's now see quickly what are the different types of DC-DC converters. So the DC-DC converter, as we have seen, a buck converter is having a similar arrangement, and if we provide this type of gate pulses over here between the gate and terminals, we will have the transistor current like this. The transistor current will increase during on state, it will reduce during off state, and the diode current will be actually opposite of that transistor current, and you can see the transistor and the diode together will form the inductor current because they are connected at a common junction. So this is about a simple DC-DC buck converter. Now we thought about electric vehicle high voltage battery system and the low voltage battery system. So this particular converter can actually step down the voltage, but can we step up the voltage as well? Yes, it's possible to connect 48 volt to 400 volt system. So you can actually boost or increase the voltage level from 48 to 400, and that is possible by a simple converter known as a boost converter. So here is the arrangement. If you just interchange the connection of this diode, this inductor and this switch, you can result into a new configuration called a boost converter, and this boost converter will take again the gate pulses like this at this terminal, and inductor current will be again similar to combination of transistor and the diode current, and the output voltage will be boosted because of the LDI by dt developed using turn on period of the switch. So V in along with the LDI by dt, that will appear across the output voltage whenever the switch is off. So this is a simple introduction of a boost type of a DC-DC converter. Now what are the limitations of these two types of converter? These two types of converters are basically non-isolated, so the input and output share the common ground. So the negative terminal of the output voltage is same line and there is no isolation. So when you have, let's say, 400 volt and 48 volt, you have basically the low voltage and high voltage systems, and it is very important in automotive electronics to isolate the low voltage intelligent electronics from the high voltage side. So the isolation is very much required, which is not there. So these are called simple non-isolated DC-DC converters, and these non-isolated DC-DC converters are useful where you have applications such as developing 5 volt from the 12 volt input, or developing 3.3 volt for microcontrollers from 5 volt input. So those converters are going to be of buck converter type. And buck and boost, their inductor can actually be configured into a transformer where you have another pair of inductor coupled with this, and this transformer can actually isolate the input and output side, and this transformer will also provide the turns ratio through which the voltage can be scaled up or scaled down depending on the turns ratio. So this type of power converters have evolved from the basic power converters like buck boost, and they are called as forward flyback converters. So the forward and flyback converters are derived from fundamental DC-DC converters. So let us quickly go through the other types of converters, which we will see as a full bridge converter. And so flyback, push-pull and forward converters are also preferred at a lower power level. So within below 500 watt range, this non-isolated converters along with the forward, flyback and push-pull are preferred. Above 500 and above in few kilowatts of power range, the different power converters of isolated topologies are preferred, and we are going to see one of that type of DC-DC converter in this video. So let us now talk about what are the design stages of a power converter. How do we design? So we need to understand about what is the input voltage and output voltage, what is the input range of the battery voltage, for example, and how much output load can change from initial value to final value, or what is the range of the output current. So once the requirement specifications are done, then you can quickly move to ANSYS PE-Expert and PE-Mag to choose the type of the converter and to configure the template based design. So the next stage, what an engineer is going to do is the circuit simulation of the chosen topology. So whatever circuit configuration you have done, you have to then simulate a circuit, and in the circuit simulation you will basically identify which are the suitable components, and you will prepare a schematic from the circuit. So circuit is a conceptual arrangement of the components, but schematic is a more professional way of representing the circuit where all the components will be included. So this circuit simulation and the schematic can be added using Twin Builder and the Simplorer. So the ANSYS Twin Builder and Simplorer are the tool which will be used for circuit simulation. Now the next step, the design engineer will be doing converting this schematic into the hardware prototype. So the hardware prototype can be done by a printed circuit board design. So the printed circuit board design is the next step, and once the printed circuit board is available, you can actually do the testing and validation of the PCB using SI Wave and ANSYS IcePack. So the SI Wave and the IcePack are the tools which are used for testing and validation. So what kind of testing and validation are required over here? For example, signal integrity and power integrity, we need to check out on how much maximum heat will be generated if you consider typical efficiency of a power converter, and you can also check about how exactly the cooling system should behave, right? So how to design a cooling system and how we can actually be ready to deal with the thermal issues of which are resulting due to the lower efficiency of the power converter. So the power converters may not have efficiency at all percentage of load. So let's say if I draw a curve for percentage efficiency versus loading, so let's say this is the value of the efficiency and this is the percentage loading, then the efficiency curve of a power converter can exhibit a very high efficiency during this period of load, and during low loading condition it can be like this, during high load then overload it can be like this. This is one typical graph. We do not know for which power converter what will be the exact graph, but usually the efficiency varies with the load. So now during the low efficiency region the losses are going to higher, and even if you have a high efficiency, because your percentage of loading is higher, you result into the higher amount of losses, and these losses are going to result into heat generation. And basically the heat generation is the responsible cause for failure of most of the power converter circuits. So most of the power converters will end up having a failure because of the reason of thermal issues. So these are the overall design stages, and once you have testing and validation done, what is the next step? So the next step is redesign, right? And this can be iterative, and this can be done again and again in order to satisfy the performance, whether the performance criteria are meeting or not. So let us move ahead and see which are the ANSYS tools available. So let us now switch to the ANSYS and see how we can see all this in ANSYS tools. So we are going to have a look at PE-Expert and PE-Mag. We'll have a quick look at Twin Builder and a Simplorer, and we are going to look at SI Wave and iSpec. So here I have opened the ANSYS electronic desktop, which is basically the ANSYS electromagnetic suite, and I'm using 2020 R1 version. So what you can see over here are the basic 4 tools, which are HFSS, Q3D, Circuit, iSpec, Maxwell and Simplorer. So let us open the Simplorer and let's see how it looks like. So I have now opened the Simplorer project, which is a blank project, and I can actually add components from this library. So this is the component library, and basically you need to drag and drop over here from all these components. So this is a component library available, and here you can see my favorite components and whatever are the components which I have recently used. So if I explain you what are the basic elements available here, so you can see the basic circuit blocks where you have RLC parameters, where you have mathematical blocks, also you have voltage sources, current sources. So this is going to be almost similar to your SPICE simulator. So basically circuit simulator is very fundamental tool in order to do simple simulation. So here is where I have added one register in the blank file, and I can basically do the connection with a voltage source, and I can prepare any circuit I want. And once I prepare the circuit, then what I will be able to do is I will be able to create a netlist, and I will be able to do the next stage of the PCB design. So this is about ANSYS Simplorer. Let's try to have a look at what all we have as readily available examples using all these component libraries. So now I'm going to open the examples, and let me go to the Twin Builder. You'll not have any folder such as Simplorer, but it's now part of a Twin Builder, and inside the Twin Builder what you have as applications and add-ons. And if I go to add-ons and see the power electronic blocks and SMPS, here you have most of the examples related to power electronics. So if we go to SMPS, we have a power converter, and we can see the average where it's a DC-DC converter, isolated and non-isolated. If we see the non-isolated, then we have example of a buck converter and boost converter and buck boost converter. So let me open this example of a buck converter. So once we open any example, what we need to do is we need to save this example to our folder. So before I click on run, these are ready to run example, but before I click on run, let me save this example somewhere in the folder. And you can have a look at the circuit where we have a 25 volt DC input, we have an ideal switch, and we are giving this controlled output voltage at a given frequency with a 50% duty cycle, and we are expecting somewhere around half of the voltage, right? So we are going to run this simulation and we will see how do we check out the output voltages. So let me first save to the temporary folder. So this is the buck converter simulation. So here let me save the example for the buck converter. So now I will be able to do the modification and run this simulation. So if I click on analyze over here, which is on the top panel, I will be basically do the simulation. So what is that simulation I'm going to do? So I'm going to analyze the transient result of this circuit, and what we are able to see is the inductor current and the capacitor voltage. So let's run the simulation and we will be able to see some output voltage and current. This is similar to any circuit simulation software, and this is how you can see the output voltage and the current for an average mode of buck converter. So these are about the SMPS library components and how do we deal with them. And so basically you can modify the output voltage, you can modify the parameters of this circuits, and you can probably work upon your converters. So let us close this. So now let us start with a template based design for a full bridge converter. And before we start with a full bridge converter, let us try to understand what is a full bridge converter. And before that, let's see some more examples. So if I go to examples and Twin Builder, we have certain examples related to applications, and we have some examples related to hybrid electric vehicles, and we have a commercial vehicle application, we have EV application and HEV application as well. So if I open this, we can not only simulate the circuit components, but we can simulate the system level stuff as well. So here is a driver block. Here is where you can see this is a motor controller, and where you can see the terminals are going to this motor, and this motor is connected to the wheel, and wheel is basically connected to this vehicle body. And here is the battery management controller or charge controller, and here is your battery. So these are built-in simulations which you can try and which you can see what are the output. So these are some of the examples which will give you an idea about what can be done in a Simplorer or a Twin Builder and how you can utilize for your study and engineering. So let me show you a few more examples. So if you go to examples and Twin Builder and go to applications, and if you see the power converter application, here you have matrix converter, here you have a cyclo converter, which is single phase to single phase cyclo converter. If we open this, you will be able to see that there is a single phase input and a single phase output, and here you have a P converter and N converter connected back to back, and this AC supply will be converted to different frequency and different voltage of AC supply in the output at register R1. So almost all types of power converters, almost all types of motors and drive systems are available as a model block in the Simplorer. So let us close this, and let us now get back to a full bridge DC-DC converter for EV application. So here we have a circuit arrangement of a full bridge DC-DC converter. So this is the overall arrangement of a full bridge converter. And what is different than a simple DC converter? So the simple DC converter was using only one switch and an inductor, Now instead of one switch and inductor, we have many different switches, and instead of the inductor we have this as a high frequency transformer. So what will happen in this circuit? So let's say this is the positive of a DC supply and this is negative terminal of a DC supply. If switch number 1 and 2 are closed with the gate pulses applied to their gate terminal, then this winding is going to experience the current flowing from top to bottom in this direction. And similarly, if this is going to be the positive, this dotted terminals, according to the sign convention, they will be also positive, and they will also develop the EMF in their winding like this, and that will produce the voltage accordingly. So let's say positive and negative like this diode will be conducting, this diode will not conduct, and the output voltage will be rectified and the current will be smoothened by this inductor, and this capacitor will maintain the output voltage ripple to certain limit. Now what will happen if we turn on switch number 3 and 4 and turn off 1 and 2? So when you turn on 3 and 4, the direction of the current through the winding is actually opposite, and now instead of this diode will be conducting, and again what kind of current or what kind of voltage will be available in the output? That will be DC. So basically the full bridge converter is consisting of a full bridge inverter. So the input side is basically a full bridge inverter comprising of 4 switches which are turned on as opposite pair, and this full bridge inverter output is given to a transformer, and the transformer secondary is connected to a rectifier. So the rectification will be done in the output side of a transformer. Now this high frequency transformer can be a single or multiple winding. So there can be 1 winding or 2 winding or 3 winding depending on the design of the full bridge converter. So this full bridge converter will be very much useful in case of a high power converter along with a high ratio. So imagine a situation where you want to have 400 volt DC side and you want to get 48 volt output. So basically the step down ratio from 400 volt to 50 volt, this is approximately 50, where you have this ratio as 8. So 50 times 8 will be around 400. So 48 times 8 will be nearly 400, and you can see the ratio which we want to get is 8, and it cannot be handled by a single switch. So you can either use a multi-phase buck converter, or if the application is higher power, let's say high power, which means that greater than 500 watts or around 750 watts or and so on, then it is very much required to use the circuit arrangement similar to this. So here the stress of the devices are distributed among the 4. So whatever is the voltage blocking capacity of the device and the current carrying capacity of the devices, they are shared. This transformer helps in the turns ratio, and this turns ratio will decide about the input voltage and the output voltage. And it is also possible to have multiple winding, where one winding can generate 48 volt, the other winding can generate 12 volt in the output. But this 48 volt and the 12 volt generated from the same transformer secondary will not be called as isolated. So the 400 volt is isolated from 48 volt, 400 volt is isolated from 12 volt, but these two are not isolated from each other. And in some applications such as SMPS for a computer or a desktop computer, this type of power supplies are used. So the very fundamental requirement over here is the transformer secondary side diode are required to be very fast reverse recovery time. What will happen otherwise? So let's say if you are switching 1 and 2 and 3 and 4 combination of IGBTs at, let's say, 10 kilohertz, and this 10 kilohertz switching frequency will result into faster on and off of the current through this diodes. So if the diode currents are not becoming 0 at given period of time, then basically this reverse recovery of a diode may result into the failure. Less reverse recovery or faster reverse recovery time diodes are required, and sometimes in order to get it achieved in a better way, and because the on-state resistance of the diode are also very high, the synchronous rectification using the MOSFET is what preferred by designers. So this is the overall circuit arrangement of a full bridge converter, and let's try to understand this from Power Electronic Expert in the ANSYS. So how do I open the Power Electronic Expert or PE Expert? So I need to go to Simplorer, and from Simplorer I have an option from the Twin Builder window over here. So this is the Twin Builder option from the Simplorer, and here is where you can launch Power Electronic Expert. So let us launch the PE Expert and let's learn about the full bridge converter design. So I will go to Twin Builder and launch PE Expert. So this is a template based tool as I have explained, and let's see what can be done. So I'm going to create a new design, and this tool can basically help us to develop a design based on the waveform or based on the converter. So let's say if I choose an inductor, what kind of design I can build? I can build a buck converter, boost converter, or buck boost converter. What if I'm going to choose an inductor? If I choose an inductor, I'm going to be asked for design of an inductor for my case. So you can actually design an inductor for your own application. So if you click on waveform based and click on OK, here is what you can do the design. So we can basically provide how much is what is the voltage waveform, what is the voltage level. Let's say our voltage level is 50 volt and we want to design this inductor, and we do not want the ripple to be, let's say, below some value, right? And the frequency is 200 kilohertz, then the value of the inductance will be 5 microhenry. So it's possible to have a continuous conduction mode with this case where average current is 2 ampere, the ripple is 20, and in order to reduce the ripple to, let's say, 1 ampere, this inductance value is going to become 100 microhenry, and you can actually define the inductance value, or you can define the duty cycle as well. So as I change the duty cycle, what you are able to see is this voltage and current waveforms are also changing. So if I change this duty cycle, you can imagine what is the maximum current, minimum current, how much is the ripple, and what is the average value. So here you can see as I increase the duty cycle, the ripple is increasing, and now in order to maintain that ripple to, let's say, 1 ampere, then we need to have a 230 microhenry of inductor. So now you can actually go ahead and design this type of inductor. So here we have 3 steps. One is waveform, one is design input, and another is the modeling option. So if I go to design input, I can choose all these options and I can basically go for modeling of this inductor, and I can figure out which inductor is going to be useful if I start the design process. So what I need to do as a next step is go to calculation and click on start design process. So let us start the design process for full bridge converter. So let me close this. So here we have a new file, and I'm going to now work upon a transformer based power converter where we have this options where we have a forward, classic, half bridge and full bridge. So let us select the full bridge. So I'm going to select the full bridge, and here the template of the full bridge will be available. So what you guys can see is the transformer over here and the input voltage, and the secondary of the transformer over here in the output, and you can fundamentally see the waveform as well. So if I change the duty cycle, you can see what will happen in the output voltage and the current. So you can choose to see the current in the secondary side or the primary side. So let's start our design, where we have the input voltage as 48 volt and the output voltage as 400 volt. So this is our voltage requirement, and let's say we want to design this for 5 kilowatt. So 5000 is watt is the design, and here is what you can see the current on the output side, which is 400 times 12.5 will be 5000 watt. Now you can define the current ripple, and you can actually choose the ratio of the winding turns as well, and this winding turns ratio can be chosen from primary or secondary. I can select the waveform from here, which waveform you want to see, primary and the secondary. Only the levels will be different, and if you want to see this currents, you can see the primary winding is 48 volt side. You can see the maximum voltage is around 50 volt, and the current at the same time is 200 amperes. So for 5 kilowatt and 50 volt, this is going to be the level of the current. So the peak value of the current will reach to 200 amps, and we can actually decide the current for this case. So the average current will be again be dependent on the duty cycle, and you can see the waveform on the primary side and the secondary side. So the secondary side is 400 volt side, and because of the inductance of the transformer, the highest voltage that switches are going to experience, that is 1000 volt, right? So this is about the fundamental step. Now let's go to the design inputs, and over design input you can actually choose how much is the spacing for the winding, how much is the ratio for this, whether you want to consider the thermal consideration or not, whether what is the variation in the turns ratio which is allowed, how much is the maximum flux density versus saturated flux density ratio. You can see the limiting value of the temperature. You can select the winding setup, and there are so many other things. So whether you want to select the ANSYS I-spec, basically the ANSYS I-spec is for temperature and the flow simulation, and you can choose the natural or force or any type of simulation from here. So if you do this, then there will be certain modeling options over here, and before we actually do the design process, let us save this model. So I'm going to save this model in the project files, and let me create a new folder. Let's say design 1, and I'm going to save this full bridge file. So now once you have saved this, you will be able to start the design process from the shortcut available over here, or you can go to calculation and select start design process. Once I click on start design process, here is an error coming up. Let's see what is this error. This is related to no design library selected. Let's understand what is a design library. So what you see over here is a design library, and these are the material available in stock for your case. So these are the stock libraries, and here you have AVX cores, EPCOS cores. These are basically the companies who are manufacturing this cores. So here you have bobbin, wire and material. So all those libraries required for designing of this transformer are added over here. So what we need to do, we need to basically add this library into our design library. So if I add this, now I have an EPCOS design library where I have EI type of core, and let's say EE type of core. Let's see one of the EI type of core. So this is the arrangement for EI type of a transformer, and if you can see those dimensions, all this core and the dimensions are mentioned over here, and these are the actually commercially available core materials, and you will be able to see the material related to bobbin, wire as well. And go to wire, you have these 4 options: foil, lids, round and the square, which are popular for design of the high frequency transformer. So the entire template is going to work upon the high frequency transformer selection and its analysis. So all other analysis can be done quickly in case of a circuit simulator, but this is going to give us an idea about the magnetics of a high frequency transformer. So let us go ahead and select the start design process. So if I click on start design process, it is going to ask me that there are no cores selected. So what I can do manually selection of my core material and bobbin and wire. Otherwise this tool can automatically assign for us. So I will click yes over here, and the same is true for the wires and materials, and it is going to choose the competent material for us. So what is the output of this exercise is we have got 162 valid design from 1539 designs, and the top 10 designs are selected over here. So now we can see in the output, after this modeling options, we have the constructive results, performance results and list of results. All these 3 tabs added over here. So I can choose the constructive result. Here is where we can actually see the transformer magnetics, and we can see what is the core size, and say for this design PM62/49 is the core selected for this case, and here are the dimensions in the millimeter. You can convert it into inch as well. So this is the transformer design which is there, and it has a multiple number of winding. As you can see, the cross section area are also changing over here, and you can see the type of the wire and their standard wire gauge number. So this is also available in the tool. What can be done in case of a performance result is you can see what are the total losses inside a high frequency transformer. So for a high frequency transformer, there is a core and a winding. So the winding filling factor, the winding rate and the losses are explained over here. The magnetizing current is shown like this. So this is the value of the magnetizing current for our application, and you can see all other parameters like how much are the total losses. So for example, I have input 5000 watts, and for those calculation we have total loss of around 21 watts, and with whatever input we have given. And you can see the window occupancy percentage, the flux density value in millitesla, the highest temperature is 100 degrees centigrade, and so on. This is based on the material property available in the tool. So here we have a list of results, and for which we can choose any, and then we can move ahead with modeling with either Maxwell 2D or the power electronic magnetic tool. So what is the next step after doing this? We need to select the modeler over here, and from modeler you can select the generate model. So when you select the generate model, you will be actually able to translate your design into Maxwell 2D or any other options. It is also possible to translate your design into Twin Builder or PSpice or Sabre, which are other than ANSYS tools. So let's click on generate model, and I'm going to select the default option over here, I'm going to open this model with PExpert, and PExpert modeler is PE Magnetics, and optionally I can generate finite element analysis 2D based or 3D based with considering capacitive effect or without considering capacitive effect. So let me click OK with the PE Mag option, where it's a power electronic magnetics option, and when I do so, I'm going to now open this design in PE Mag tool. So this is a PE Mag tool, and this is the overall arrangement of the transformer winding. So what you are able to see over here is the transformer design done in PE Mag. So here we have this coil, here we have this insulator. So all these green colors are insulators, all these are winding, and all these windings and insulators together will be connected to the terminals. So here we have AA, BB and CC as a pair of 3 terminals. So this is going to be the transformer design, and if we see the winding arrangement, that is also possible to be seen from here. So this is the winding arrangement done, and this is a cross-sectional view of that winding arrangement and how you need to isolate one winding from another winding. And so when you have let's say this group of conductors in yellow color and this group of conductor in red, you need to provide the insulation material as well, and that is taken care by this design. So here what you have is the current design, where it's a core, bobbin and the winding, and you have a design status. And from here what you can do, you can call 2D modeler, 3D modeler, or you can go to eddy current analysis, you can go to FEA electrostatics and so on. So this is the PE Mag model available over here, and you can analyze the results. You can transport this model to any other tool. So this is about template based design using PExpert and PE Mag. So we created a full bridge DC-DC converter, and we analyzed that how ANSYS tool will select the components from the available library and how it is suggesting us. What if you do not have any readily available component or any off the shelf component? Well, that is the case with most of the power converter. So the resistor, capacitors and other components like diode and switches, they are available off the shelf, or we just have to choose them. But when it comes to magnetics, you have to design them. So the power converter engineers will have the magnetic design exercise using inductor design and the transformer design, and this tool is going to be very effective for new design of a transformer or an inductor for a power converter. So these are the templates, and over here you can create your own component of transformer or inductor as well. So now let me close this, and let us now go back to PExpert, and what you will be able to see as the values of transformer chosen, and you can actually have the core material properties, and you can see over here additional parameters. You can find out the core losses. This is based on the data sheet of a transformer, and you can see the BH curve as well. So these are the BH curve for both the cases, and here you can see what are the electrical properties of this material, and you can see most of the things related to core. An N87 type of core is actually commercially available type of a core. So if we see this type of our core design and dimension, we can actually verify them with a core material and the core commercially available cores. So if you can search for PM62x49 type of a core, you will be able to find this type of core, and you can actually start your first step of hardware design with this type of a core. Now along with the core, you need to figure out a compatible bobbin. This is possible to include over here. So this is the end of demonstration with PExpert. Let me close this now. And now let's say we are back to Simplorer, and basically in Simplorer, as I explained, you can drag and drop all the components and create your circuit. So we have talked about theoretical full bridge DC-DC converter and its template based design based on PExpert and PEMag tool. Now let us try to understand how the actual design can be implemented. So I'm showing one of the image from ST Microelectronics, and this is a company which generates or which provides a solution for gate driver, gate protection, current sensor and control unit ICs, and even MOSFET devices as well. So this is a semiconductor manufacturing company, and they provide the solution for EV DC-DC converter. So what you see over here is a high voltage battery pack, and its positive is connected to the primary side of a bridge, and its negative is connected like ground over here. The gate pulses are generated from a microcontroller unit, and this gate pulses will be given to the gate driver, and this gate driver will provide 4 different pulses to this MOSFETs, and there will be a sensing as well in order to determine what is happening with the output and input, and with reference to voltage and current. On the secondary side, what you have is a synchronous rectification, where this MOSFET will conduct from actually source to drain in the top direction. So this LV battery will get charged, and this current will be flowing in this direction. So let's say this is the positive part, and from which the current will be flowing like this in this direction, and the current can actually flow in the top direction from the switch, and whenever the battery is discharging, this can be reversed. So whenever the battery is discharging, the current through the MOSFET can be flowing down from top to bottom. So there are gate drivers and protection required for the secondary side, and there will be an isolation as well for sensing, and there has to be a signal conditioning circuits as well. And let's say this is the LV battery, which is 48 volt or 12 volt battery, and this converter together with primary and secondary power switches along with the transformer can act as a fully bidirectional converter. For a fully bidirectional converter, probably you need more number of switches for a battery control. So secondary side, instead of diodes, the MOSFETs are used, and it is known as a synchronous rectification. So the modifications are required for a bidirectional power flow. So now we are going to actually have a look at the entire design, which is suitable for a battery charger from 400 volt bus. So we are going to see this design example, and here we have 400 volt input side and 36 to 60 volt, or we can say 48 volt nominal output side, and this is constructed using 4 MOSFETs on the primary side of a transformer and 4 MOSFETs on the secondary side of a transformer, along with a clamp MOSFET and the capacitor. So this is a particular design which will do the bidirectional power flow. So the power can flow from high voltage to low voltage in this direction, or it can flow from low voltage 48 volt to 400 volt in this direction. And this is such a design which can actually be built for an EV application as well. So the reference is a bidirectional DC-DC converter reference design with this number, and you can actually study the entire design and its working in the documents available on the Texas Instruments website. So what we are going to do with this design, we are going to use this PCB design files, and those PCB design files we can include these files in the SI wave, which is signal integrity tool from the ANSYS, and we can analyze the overall output or overall performance of the PCB under a certain situation. So this is the image of the actual board, and what you are able to see in this image, some power switches which are mounted on this big heat sinks. So there are 4 power switches, let's say, on this heat sink, another 4 power switches on this heat sink, and this is the yellow color is a high frequency transformer. So this is an actual image of the power converter board, and this power converter board can actually supply 2 kilowatt of load. So this is the image of an actual prototype built by Texas Instruments, and we are now going to do the PCB design analysis or electrothermal design of this PCB, which is used for full bridge DC-DC converter. And this is a typical design example of 400 volt to 48 volt, and which is very much similar to the requirements of an electric or hybrid electric vehicle. So let us go into this design example. I'm going to show you some PDF files for this design example, and then quickly we will go to ANSYS SI wave, and in that tool we will analyze this printed circuit board. So over here, let's say we will be analyzing this printed circuit board, and we will be able to do the fundamental signal integrity and power integrity analysis. So what I am showing you here is the fundamental layout of the printed circuit board, and what we see as a circuit and what we see as a schematic are completely different, because we have to include all the involved components over here. So for example, on the high voltage side, you have this gate driver circuits like UCC21520 for each leg, and for each leg this is going to be another design or another add-on cards. So similarly over here we have another add-on card which is TIDA01141, which is for sensing the current, and here you have a control card which is TIDA01281. And what we are going to focus on is a power stage architecture. We are going to see the PCB for the power stage. So if I scroll down through the schematic, and these are the components, and this is how the entire schematic is developed. So what you are able to see are these are the 2 top MOSFETs and the bottom MOSFETs. They are connected with the input side of the transformer T2, and here on the secondary side you have again combination of top 2 MOSFETs over here and the bottom 2 MOSFETs over here, along with a third switch. So what we have as a power architecture, these are all FETs along with the transformer, and these 2 are the input terminals where we can see over here, and these 2 are the output terminals, and we are going to see this architecture in the PCB as well. If I show you the PCB layout of this, so what we are able to see in this PCB layout is, on one side you have this 4 switches mounted. So these are the 4 MOSFETs along with the heatsink. So the heatsink is through long like covering entire all 4 switches over here, and there are another 4 or +1 switches over here, and this is the main area for transformer T2, which is the main transformer. And here you have big capacitors on the input side. These are the 2 capacitors on the output side. So this is the overall power architecture of the design. So if I show you the layout of top layer and the bottom layer, so this is something the PCB design will look like this, and this is what we are going to import into SI wave. So let us start with ANSYS SI wave and import our PCB design, and I'm going to open ANSYS SI wave. So basically the SI wave stands for signal integrity wave, and it is a tool from the ANSYS in order to perform power integrity and signal integrity. So this is the window of SI wave. This is how it will look like, and what you can see in the middle is the area where you can see the PCB design. So you can see the PCB design over here, and it will be possible for you to include the PCB over here. So what you need to do, you need to translate your PCB design files into the format which are supported over here. So with the help of Altium Designer 20 software, I translated the design files into IPC 2581 standard. Basically these are the export file for the manufacturer. So when you export those PCB design files into IPC 2581, you will be able to import them over here. So let me open this project, and let us see how it looks like in the SI wave. So here is the PCB design project which we have, and as you can see, this is a 2-layer design, the top layer and the bottom layer, and you can see the terminals over here. This is the transformer, these are input terminals, and here you have 4 number of switches, 1, 2, 3, 4, and actually 5, and here you have another 4 number of switches which are through hole MOSFETs. So here these are the power devices, and this is what you can correlate with the design document. So I have imported this, and I can actually now do the analysis. Let me close this part, this, so that we are able to see the entire design, and probably now you can see design in a better way. So this is the entire board which we have imported, and it is basically 173 mm by 185 mm. And let's start DCIR analysis. Now what is DCIR? So basically we are going to do a DCIR drop analysis, and this can be done from the SL Wave workflow wizard from this option. So this is a kind of a short key over here, and through this wizard we can quickly launch a typical analysis. So we can also configure the power integrity analysis. That option is also there. So let's start with the DCIR, and as you from the name itself, it's basically the voltage drop analysis, and what will happen if you have that much level of voltage present in your board, how much current is flowing, and what will be the effect of voltage and current across the plane of a PCB. Now if you have voltage and current, and if you know the track width and the track material and the track properties, you can basically calculate how much will be the voltage drop. And if you calculate the voltage drop, which is nothing but I into R, you will be able to calculate the power loss as well. So you can from here do the complete electrothermal analysis. So let's start with the DCIR drop analysis, and in the configuration what I need to do, I need to basically select some of the nets available from the design. Let me select some of the nets. So what I'm going to do, I'm going to select high voltage ground, and I'm going to select V bus. So V bus and high voltage ground are selected like this, and I'm going to select battery positive and negative. Why I am selecting this, basically this is from the design example. So I'm assuming that we are giving 48 volt input from the low voltage side, and we are going to get 5 ampere current on the output side, and this you can configure. And once this is done, you can basically select what are the type of the current, and whether you have the voltage source or current source over here, whether you want the distributed current or the constant voltage type of current source, and you can actually add the magnitude of the current as well. So for simple analysis, just to start with, I'm giving these values. So I will click on configure simulation. So these values will be assigned to the simulation, and this simulation will be configured over here. And the next step is validation. So let us validate the design, and if I click OK with the default settings, this will validate all the connections, and it will come up with a result report. So once the design is validated, we can basically start the simulation. So if you have any errors in your design, you can basically select the auto fix, and this will be done automatically. So let's say if we have all the 0 available over here, we are ready to go with the simulation. So what you can see, the stepwise DCIR configuration. So the green tick mark over here in the configuration simulation is done. We have validated the design, and now I am ready to hit the simulation button. So let's start simulation. When I am going to start the simulation, I can actually configure the tick mark for ANSYS iSpec option, so that I can create ANSYS iSpec project and export that power dissipation from here. And what I need to do, I need to basically select at least one ground for the node, so through which I'm going to select the 0 volt reference. So let me select this high voltage ground and click as a negative, and I'm now ready to launch the simulation. So I'm going to now launch the simulation, and you can see what is happening in the simulation manager over here. So I'm able to do the 100% setup, and simulation is also now going to finish. So this simulation gets done quickly, and here we can have some messages from the SI wave. So what happened with the simulation, and we can figure out about the results. So how to view the results? So in order to see the results, you need to click on the results window over here, and we perform a DCIR. So I need to click on DCIR and DCIR sim. So if I click on DCIR drop and do this analysis, we can actually figure out how the voltage and currents are on the power board. So on the power converter board, we are going to now plot the voltages and current. So let me select plot voltage and current, and here is where the output will look like. So let me select J, which is basically the current, and if you see the current, we can see in the power card that how the current is flowing and what is the current density. So here we have around 4.5 ampere per meter square current density for the red color, and you can see how the current is coming out from one terminal of the input 48 volt and going into this, and where else the current is flowing. And you can actually see the distribution of the current in different areas as well. So I just define the high voltage grounds and high voltage input and output, or battery positive and battery negative, which are these two terminals. So I'm able to see over there itself. So if I have decided to choose many other connections, I could have got some value of the currents over here as well, but this is what is happening, and you can see those arrows of the current representing the current density over here. So apart from this, what we can see in the output is not only the current density, but we can choose to have the voltage as well. So let me uncheck current and check the voltage on the top layer and the bottom layer, and let's see what are the voltage levels. So as we can see, we have given the excitation input as 48 volt over here in the red color. You can see all these planes are red color, which is 48 volt, and the blue one is the 0 volt. So because we have considered the output as a sink, current sink type of a load, we are able to see this. And this is just one of the possibility where we can see the output, and you can analyze actually the temperature as well. And if you have configured the ANSYS IcePack, what you can do, from the result tab you can click on export IcePack power map. So you can get the details of what are the losses happening on the board and how this losses will be observed, and this can be exported into an image as well. Or if you want to see this in the simulation result itself, you can click on plot IcePack power map. So when you click on IcePack power map, you will be able to see the power levels at different part of the circuit. So these are basically the losses happening over here, and as you can see, the track width, and since the PCB is very large, you see a very little amount of losses happening. But you can configure your input case, and you can see in extreme conditions what are going to be the power loss in the PCB and what is going to be the temperature rise. So this is what you can do with the SI wave. And now let us switch to ANSYS IcePack. So you can actually export this to ANSYS IcePack, and you can open the same project, and you can check on the part where whether it's possible to have circuit without cooling, right? And you can analyze the performance of PCB without any cooling or with cooling using ANSYS IcePack. ANSYS IcePack is basically the temperature and flow solver, and temperature and flow related simulations can be done separately in IcePack tool. SI wave over here, you can set up the electromagnetic related thing. You can select about resonant mode. You can check on the crosstalk. You can do the RLGC result. You can do the AC current, and so there are many signal integrity and power integrity related checks are possible through the SI wave. Now you may be looking at or you may have heard this signal integrity and power integrity terms very first time. So let me explain you what is the meaning of signal integrity and power integrity, and why is it very much important once the virtual design of the board is available. So let me close this. So signal integrity is basically the quality of the signal. The power integrity is basically the quality of power. So integrity itself refers to whether it is satisfying the demand or not, or whether you are getting the correct signals and correct power levels in the circuit or not. So signal integrity is a set of measures of the quality of an electrical signal, and it is very much important in case of a circuit which is communication related circuit, or in case of power converter circuits you have switching frequency of, let's say, more than 20 kilohertz, and then your signals should reach to the gate terminal of the device properly. And what happens if there are any noise? What happens if there are any kind of a disturbance added to the signal, right? So this is what you can check as a signal integrity. What is power integrity? Power integrity is another analysis to check whether the desired voltage and current are reached from source to destination. So let's say if I apply 400 volt and whether I am getting 400 volt and required current on the other side of the board or not, or how much is the voltage drop, how much is the leakage current, or what's happening actually on the board. So these two analysis can be done using ANSYS SI wave. So this is the end of our demonstration with the ANSYS SI wave. Now let's move on to ANSYS IcePack. Now in ANSYS IcePack, I'm going to show you a built-in example, and we will see how ANSYS IcePack can be used for power converter simulation. So I'm going to open the ANSYS electronic desktop, and through which we can access the ANSYS IcePack. So in the ANSYS electronic desktop, what you can do, you can select the ANSYS IcePack from here and insert a new design, or let's work upon the example. So I'm going to go here and open the example. We are going to run a built-in example for the ANSYS IcePack. So I will go to IcePack folder and I'm going to select graphics card. So here is a PCB for a graphics card, and we are going to see the simulation of that. So what you are able to see now is the actual 3D model of a PCB along with heatsink and all other components. So these components may be some of the connectors or capacitors or the heatsink. So what you are able to see is a readily available built-in project, and what you can see in the ANSYS IcePack, you have a geometry, but the purpose of the analysis is to get the temperature distribution. So here the analysis is in terms of solving the thermal and the flow simulation. So if I do this and if I check on what is the analysis setup, I can see here the problem type which we are going to solve is the temperature and the flow. So basically the ANSYS IcePack is a sophisticated tool which is used for cooling, or we can say the thermal analysis of printed circuit boards or electrical and electronic item. It can be used for the case of let's say a panel or any such enclosure, right? So when you come to a mechanical design of a cooling system or thermal design of a power converter, this ANSYS IcePack can be very useful. So if I go out of this, here we have created a box, and this is going to have its boundary as well, and we are going to see the simulation results of this example. So in order to get the simulation result, what we are required to do, we are required to do the analysis and select analyze all. So if I right click on analyze all and select this, it's going to take around let's say 10 to 15 minutes depending on the type of analysis which we are doing. So I already have the result available, and I can actually plot the temperature for this case. So I'm interested to plot the temperature distribution curve for the setup example. So let me open the example which I have already run, and I have saved it to my hard disk. So I'm going to close this and I will open IcePack example. So this is the same example which I saved and run earlier. So here what you are able to see is the same arrangement, and we are interested to know about how will be the temperature distribution. So let's see the temperature distribution for this graphics card. So this graphics card PCB, how to see the results? the results are available in the results section, and you can calculate the field overlays as well. So if I click on the results and if I check the solution data, these are the solution data available to us. So in terms of monitor, in terms of residual, and the profile which we have set up, these are the results which we have got. So the x velocity, y velocity, and energy, these are the plots, and this is what we are getting as the output, which is the temperature, flow, and the speed. So we are plotting temperature, and which is basically the red curve, and speed, which is the green part. So this is how you can analyze the results. Apart from this, you can plot the temperature field. So if I double click on the temperature, here is my temperature distribution available. So as you can see, the highest temperature is there where you have this boards, or we can say that this typical ICs. So here is the memory IC1 and the memory IC2, and these ICs are actually having most of the higher temperature, and look at the value of the temperature for this two. So it is around 75 degrees centigrade. So with the default solution setup, I simulated this, and I can decide to see some of the temperature layers, and we can see how the temperature is distributed in ANSYS IcePack. So here not only you can analyze the distribution, but you can look at the animation as well, right? And you can actually set up the cooling as well. So if you have cooling from, let's say, negative x direction, right, and then this heat sink will actually cool down the major part of the board, and you can see what is happening with the board. So, and it's also possible to do the animation. It's also possible to see the results with cooling and without cooling, and this is what ANSYS IcePack can provide the solution. So in case of an EV DC-DC power converter, we can actually translate our design from PCB to SI wave, and from SI wave we can export our design to the tools such as ANSYS IcePack, and we can run the flow and the temperature simulation, and for this results can be there with cooling and without cooling. So we can also decide on how much cooling is required. And in fact, this is not the end of the design stages. So let us look at the design stages again, and let's try to understand what are the all things which we have learned. So in a typical design stage, we started with the requirement specification. We have seen PE-Expert and PE-Mag. We did the circuit simulation and schematic using Twin Builder and Simplorer. We have seen some of the example. We exported our PCB design output files in SI wave and performed the analysis for DCIR drop. This IcePack, we have seen one built-in example of a graphics card. Now it is not like the end of the design phase, right? And in actual case, the engineering team will be working as with power electronic engineers along with the thermal engineers, and they may start their activity from this phase, and they just have a look at the dimensions, right? So requirements are not only in terms of voltage and current, but it can be in terms of volume of the product as well. So how much is the volume available, how much is the size available, and whether you want cooling or not. So in case the cooling is required, how this cooling will be provided. Is it going to be the air cooling or liquid cooling? And in case the losses of the power converter are going to increase, whether this much of cooling will be sufficient or not. So all this electric vehicle related simulations can be done with all different sets of ANSYS electromagnetic suite tools, and they are going to be interrelated each other. So from PExpert and PEmeg, you can actually connect your transformer in the Simplorer. From Twin Builder and the Simplorer, you can have your schematic ready, and you can do the PCB design in a PCB design tool, and those PCB design output files you can feed into the SI wave and the ISPAC, and you can check finally how is your thermal performance, how is your electrical performance. So this is how the ANSYS tools can be useful for power converters. So this is the end of the course. Thank you for participating in the course.
Hey guys, hope you're all doing good and welcome to our new course on Basics of Electric Vehicle Simulation Part 4. As always, pay attention to the learning aids that occurs throughout the course. It helps you understand the topics that you need to really remember and topics that are not included in this particular course. Now, what will you gain from this short course? So the first and the most important thing that you will be gain out of this course is to understand the importance of aerodynamics. You will be able to understand the quantitative parameters that aerodynamists look at, which are typically called as drag and lift. So you might have encountered terminologies like drag coefficient, lift coefficient, or drag force and lift force. You will be able to understand these terminologies and how these terminologies come into existence. And then finally, towards the end of the course, you will be able to perform virtual wind tunnel tests using ANSYS Fluent. Now, who will benefit from this course? If you are an undergraduate student who has never done aerodynamics, you will gain a lot of value from this particular course because this course also teaches you the fundamentals of fluid mechanics, and hopefully when we teach fluid mechanics and aerodynamics together, you are more motivated to concentrate on the theoretical part of fluid mechanics. Now, if you're a graduate student who is venturing into the EV domain or automotive domain and you want to learn about aerodynamics, then this course is going to be marginally helpful for you, because if you are a graduate student, chances are that you are already quite comfortable with fluid mechanics, and hence the theoretical concepts that we cover in the short course might not be that fulfilling for you. But if you're interested in quickly learning how to do a CFD simulation for aerodynamics applications, then this course will definitely be of value to you. Now, if you're a working professional with no background in computational fluid dynamics or passenger car aerodynamics, right, then yes, this course is great because this course is a very short course and it helps you get the importance of aerodynamics, and it also tells you how to do a quick aerodynamic analysis study. Now, if you are a professional in EV domain and you are already comfortable with CFD, then the content is going to be extremely basic for you. Okay, so what is covered in this video? In this video, we are going to be looking at the course curriculum. I'm going to be talking about what are the things that you will be learning in this particular course, and that's what you will learn in this video. So the course is going to start with the fundamentals of fluid mechanics, right? At the end of the day, aerodynamics is essentially the study of air and how air interacts with bodies, right? So you need to understand primitive fluid properties, because at the end of the day, all key parameters that aerodynamists use are defined based upon these primitive variables. So you need to understand them. Obviously, I will be talking about why optimizing airflow is a big deal. Most of you already know it. Some of you might not know it. So I want to kind of give you an example for it, which will make the point crystal clear. Then we'll talk about techniques to evaluate aerodynamic performance. And then we'll talk about the need for simulations, and we will perform we'll be looking at two cases. I'll be showing you how to set up one of these simulations, and you will be attempting the second simulation, which is simulating the flow over a two-dimensional passenger car. Okay, the simulations have been kept at a basic level because at the end of the day, the course is fairly simple. Now, in terms of basics of fluid mechanics, the key concepts that we will cover are, the fundamental laws of fluid mechanics, also called as the governing equations in fluid mechanics. We will be learning them, and we will be understanding what physics do these equations capture. When you're talking about deriving the laws of fluid mechanics, they are all derived with the assumption that a continuum exists. So it's very important to understand what continuum means and what Knudsen number means. And then we'll talk about key terms, right? Key fluid terms, pressure, density, temperature, velocity. And we'll talk about key equations. So this is where we'll be doing pen and paper calculations to actually figure out the various aerodynamic forces. And in fact, you will actually see that there are only two types of aerodynamic forces that you need for any type of problem, right? It does not have to be just passenger car aerodynamics. Even if you're designing a jet fighter, right? The fundamental aerodynamic forces, the number of fundamental aerodynamic forces are just two. The only problem is that estimating these two forces becomes very tricky when the application becomes complex. For example, a hypersonic flight, right? So nevertheless, I will be proving it to you that there are only two parameters that you need to understand in order to get into aerodynamics. And then every engineering terminology, every engineering term that is used in aerodynamics is a combination of these two fundamental forces along with some critical geometric properties and flow properties. And then once we have done that, we'll talk about key fluid flow regimes. So here we will primarily talk about inviscid flow and viscous flow, and we'll talk about compressible flows versus incompressible flows, and we'll talk about flow regimes based on speed of sound. Now at the end of the day, for aerodynamic flows, you're primarily going to be looking at viscous flows, meaning the effect of viscosity is taken into account, and you will be taking a look at compressible flows, right? But it's very important to understand what inviscid means. It's very important to understand what incompressible means. And finally, you will learn how speed of sound determines the validity of the compressibility assumption. Okay, I know that at this point, the last point might sound a bit complex, but trust me, it should be fairly straightforward when we get to it. So when it comes to helping you understand why aerodynamics is a big deal, we will be taking a look at the fuel consumption of Class 8 trucks in the US. And essentially, I will be calculating the market size for drag reduction strategies. Why is this important? At the end of the day, if you take a look at any engineering company or any engineering services company, they are all catering to a particular market. And it turns out that the market for drag reduction strategies, that is any techniques, right? It could be hardware based techniques or it could be software based techniques which could help reducing drag, has a huge potential, because it turns out that, you know, aerodynamics for heavy duty trucks is $1 billion market, and I'm talking about just Class 8 trucks here. If you're wondering what a Class 8 truck is, do check out Wikipedia. But in short, Class 8 trucks are very heavy. They weigh around 15 tons. Okay, and then when it comes to techniques to evaluate aerodynamic performance, there are two techniques: experimental techniques and computational fluid dynamics. Now there could be one more technique that we could potentially add here, which would be analytical methods. For example, vortex panel methods. There are multiple analytical tools that are available at our disposal. But to be very honest, as of 2020, none of these analytical methods would give you the results that you're looking for, complex geometries under complex flow conditions, right? So that's why I've not mentioned it. But yes, technically, analytical methods, right? Pen and paper calculations are really, really important. And because at the end of the day, these pen and paper calculations are the basis for doing computational fluid dynamics. So, since this is a simulation focused course, I'll be talking about need for simulations. I decided that we don't have to have a separate lecture on it, because I think the point is fairly easy to understand. You know, let's take a truck that weighs 15 tons, right? If you're basically running experiments on the truck, you need a facility that can actually hold this truck and can perform tests on it. Whereas if you're doing simulations, all you need is the CAD model of that particular truck. So from that aspect, it's fairly easy to see that simulations are going to be really cheap. The thing that you might not understand at this point is that simulations are very fast, and hopefully, you know, when we actually set up the simulation towards the end of the course, you will be able to understand that point. Alright. In terms of projects, there are two projects in this particular course. The first project is a fairly simple project but extremely useful one to learn aerodynamics, which is flow over a cylinder. And then the second project is a flow over a 2D passenger car. The second project is something that you guys are going to be working on your own, right? So which I think is a great thing to do. And you will be given all the details, of course, including geometry and operating conditions, so that you can carry out that study. That being said, I would like to conclude this video. We are really excited about this short course because a lot of students have asked for it. I hope you would consider enrolling into this course and you would learn a lot from it. Thank you so much. Bye. Hey guys, hope you're all doing good and welcome to a new video. In today's class, we will be looking at some fundamental concepts of fluid mechanics. To start with, we'll be looking at the governing equations of fluid mechanics. Now, these are very interesting, right? So these equations are what you would use to basically solve your homework problems. The same equations are used by a software program like ANSYS to simulate fluid flows. You would use the same equations to basically make sure that the nozzles of your rocket can withstand the temperatures that are achieved due to combustion, right? So these laws are fundamental laws. They're very easy to understand, but when you look at them from a mathematical standpoint, they are so rich of information, and that's why they're so complex. So we will spend some time looking into it. And interestingly, these equations have been derived based upon certain assumptions, and one such important assumption is the assumption of continuum, right? So we will try to understand what the continuum assumption means and how a number called as the Knudsen number helps us understand if we are violating this assumption. Once we have done that, we will be looking at the basics of coordinate transformation. At the end of the day, you're dealing with forces. So you need to be able to understand vectors, calculating components, how to transform vectors, how to calculate resultants, how you would convert forces into moments and vice versa. And that is what we will focus in that module. So then we will finally define pressure, velocity, temperature and density in a formal way. And we will be looking at some animations to kind of understand what these actually mean. And hopefully when we show you these animations, you will see that the molecular velocity of the fluid in a way kind of dictates majority of your physical properties except for density, right? So that's an interesting observation that I hope you will be able to make. Finally, then once we have done that, we will be looking at techniques to evaluate aerodynamic forces by performing a surface integral of pressure. Now this might seem complex, but the whole point that I'm trying to make here is to prove that there are only two forces that are very important in the world of aerodynamics. Most of the parameters that you want can be derived from these two fundamental forces. So I will be performing pen and paper calculation to estimate the pressure force and shear force and show you the relationship between these quantities and the normal force and axial forces. So then we will talk about fluid flow regimes. So here we will primarily focus on viscous flows, or at least understanding what viscous flow means, and we will talk about the difference between compressible flows and incompressible flows, and we will look at the effect of Mach number in determining the flow regime of the problem. And in this topic we will finally look at the effect of Mach number in determining if a problem is compressible or incompressible. Once all of this is covered, we will be able to give you a simple, easy to understand definition of what aerodynamics is all about. So let's get started. So the first thing that I want to show you is laws of fluid mechanics. You can have these laws in two ways. In English, it essentially says that mass, momentum and energy can neither be created nor be destroyed, but they can be transferred. Now that's plain English for you. However, if you want to write it in a mathematical form so that everyone understands this exactly the same way, then you get this messy looking second order partial differential equations. So these are what you would call as the Navier-Stokes equations. Now historically only the momentum equations were called as the Navier-Stokes equations, correct? But as time passed, in the community of computational fluid dynamics engineers and fluid dynamics engineers, it kind of seemed acceptable to call the continuity equations, the momentum equations, and the energy equations together as the Navier-Stokes equations. Okay, so the Navier-Stokes equations, each of them represent a particular rule. So if you take a look at continuity equation, this partial differential equation says that mass can neither be created nor be destroyed. And if you look at these momentum equations, they are nothing but a force balance equation. It is essentially telling you that rate of change of momentum is equal to the resultant force on the object, right? That's what x, y, and z momentum equations are. And energy equation tells that energy can neither be created nor be destroyed. So if you take a look at the momentum equation, this is essential time rate of change of momentum. Okay, so time rate of change of momentum is being computed, and in other words, the derivative is with respect to time. And if you take a look at these convective terms, you call them as convective acceleration, right? These terms are essentially derivatives with respect to space. So these are what you call spatial derivatives. And similarly here you have spatial derivatives. For example, this is kind of an important term. This is called as the pressure drop term, right? It essentially tells you how pressure changes as a function of x, changes as a function of y, and changes as a function of z. Now from your calculus you might recall that in order for these things to be computable, in order for you to be able to compute derivatives, pressure should be a continuous function, right? You might have studied this, and I hope you recall that. So essentially what it means is, if you have a fluid, if there are spaces, right, in between or voids, then it kind of says that, hey, this equation is not applicable. But here's the thing, at the end of the day, fluid is made up of molecules, right? And molecules have spaces in between them. We all know that. Exactly. So if you are at that scale, right, if you are at a very small scale where you are dealing with molecules, then this set of equations are no longer applicable. Okay, these set of equations require that you do not look at the problem at such a zoomed in level, and in fact you have to kind of zoom out so that it looks like the molecules are all together and essentially you see that there are no gaps, right? That's kind of the whole idea. And in order to reiterate and give you a better explanation, I've made an animation for this which I'm going to show you. So here, for example, what I have here is a cup filled with water. Okay, now what I'm going to do is I'm going to mark these points. Okay, so I have a few red points, and in those red points I'm going to measure a fluid property. The property that I'm going to measure is called as density, which tells me how tightly the fluid molecules are packed. Now when I look at this water at this level of zoom, right, you can see that I'm just seeing water, right? I don't see the individual molecules move around. In other words, everywhere I look, it seems that water is always present. But what's going to happen, if I zoom in between any of these 2 points, right? For example, let's take these 2 points. Again, between these 2 points, let us try to add a few more sensors where we are measuring densities, right? Say these smaller balls. Now again, when I look at this, it seems like there's water everywhere, and there is no region, say, between these 2 balls where the water is not there, right? In other words, we are still in the continuous domain. So now what I'm going to do is I'm going to repeat this process again, right? So this time we have zoomed in even more, and it looks like again it's not a problem, it's completely continuous. But at some point I'm going to be looking at it at a molecule level, right? I'm playing with molecules at some level, and I'm going to be looking at the molecules on an individual basis. So this is kind of an exaggerated picture, right? This is not real molecular simulation, so it's just a simple animation, right? So if you see this image, you can see that all of them are molecules, right? The blue balls represent water molecules. Okay, again, these are not technically correct because the molecule of water is shaped differently, but that's not the point here. The idea is you have water here, and then to find the next water molecule you have to travel some distance. Between these 2 molecules you don't have water, right? There's no water in there. Similarly, from this molecule to this molecule you don't have anything in between. So if I'm computing density here, right, for example, if you look at the location of our sensor, density sensor, the density is nothing but the weight of water in 1 meter cube of space. But here, if you look at this, there's no water there, right? in that particular location. So wouldn't density be 0? Technically yes, and that's why you should not measure density at this level. You should measure density by zooming out so that you continuously see water, right? So in other words, at this level it's okay to measure density, whereas if you are zoomed in at this level, it's not okay to measure density. And this is what you call as the continuum assumption. In real life, when you zoom in really close, you are going to be seeing molecules, whereas in the continuum assumption, we just assume that no matter how far we zoom in, there is always water going to be present. And this is what you call as continuum assumption, and this is the foundation of the Navier-Stokes equations. So in other words, you cannot use Navier-Stokes equations when you're dealing with rarefied mediums or mediums where the density is very low. What can be an example of that? Well, outer space. In outer space, the density is very small, right? It's almost close to 0, right? So in order for you to find molecules, you might have to travel several meters, several kilometers to find those two molecules. So in those type of problems, you cannot use the Navier-Stokes equations because your derivatives are no longer computable, right? And in such cases, there's a technique called as the lattice-Boltzmann method, which is used to perform computational fluid dynamics. Okay. In other words, Navier-Stokes equations would be a subset of the lattice-Boltzmann equation. Okay, I hope that makes sense. Now in this example, we have a cup of water, right? And when I showed you the first image, right, or the first section, the water in the cup is still, right? It's not moving. But when we are looking at the molecules are all moving, right? And when they are moving, they have a particular velocity, they have a particular kinetic energy, right? This kinetic energy essentially dictates the temperature of the water molecules, right? So you can see that the water molecules are moving randomly, correct? They are not being pushed, they are moving randomly. The speed at which these molecules move is essentially proportional to the temperature, right? So the higher the temperature, the faster the motion is, the faster the velocity is. And that's why at the start of the lecture I mentioned that the molecular velocity is an important parameter, because even though it's actually velocity, it essentially tells you what the static temperature is. And though the water looks stationary, you can see that the molecules are continuously moving and they might collide with each other, right? Because these molecules move, they have a particular momentum, and because the momentum also changes since the motion is random, there is going to be a rate of change of momentum, and rate of change of momentum is nothing but force. And when this force is applied on, say, the neighboring water molecules, right? Again, you should not be looking at this at a water molecule level. Again, think of a continuum. The whole point is, because of the molecular motion, there are forces that are inherent even in a still cup of water. These forces, when they're applied on an area, essentially give us a pressure value, right? And this pressure is what you call as a static pressure. So static pressure arises because of the random motion of these molecules. But again, if you look at random motion of molecules, the primary thing that you want to describe there is their velocity, right? And that's why the molecular velocity again is a key parameter. At the end of the day, the number of molecules that are present in a given unit volume. But again, you should not be measuring it at this scale. You should be zoomed out of it. All right. So one interesting thing, right? So when you look at it at this level, this is what you would call as a continuous domain, right? Whereas on the right hand side, the example that we have is essentially, you might have guessed it, is discontinuous domain. Okay. I hope that makes sense. So let me just close this video and I'll show you another video. So in this video, we just have a bunch of molecules, guys. And what I'm going to do is, as these molecules are randomly moving, all right, there is a distance called as lambda. So lambda is what you would call as a mean free path. So essentially, mean free path is the distance that a molecule will approximately travel before it collides with another molecule. Okay, so you can imagine that lambda is a very small number. All right, again, lambda is the mean free path. Now if I take a look at the domain size, for example, if I take a domain size, meaning I have if you take a look at the size of this video frame, right, and if this is lambda, can you guess how big the frame is? The frame is 10 times lambda, right? So Knudsen number is essentially lambda divided by essentially the length of the domain, so which would be 10 lambda. The length of the domain is 10 times lambda. So lambda divided by 10 lambda is 1 by 10. And that's what a Knudsen number is. When Knudsen number is 0.1, that means you are really zoomed in. You are at the molecular level, and in that case, continuum assumption is not valid. So how do we make sure that continuum assumption is valid? Well, you need to zoom out, right? In other words, the frame size of the video should be much larger than lambda. So for example, let me just zoom out really big. So now the frame is 1,000,000 times larger than the mean free path. So hence the Knudsen number is the inverse of that, 1e minus 6. So these are key concepts that you need to understand, right? So you need to make sure that when we are dealing with aerodynamics for automotive applications, we primarily use Navier-Stokes equations for it, which means continuum assumption has to be valid. So which means the Knudsen number has to be 1e minus 6 or smaller than that. 1e minus 8, 1e minus 9, that works. It cannot be really small. It cannot be really large, like 0.1 or 0.2. That means if that were the case, you cannot use Navier-Stokes equation for describing that particular problem. Okay, so now let me move back to the slides. Okay, so now let's take a look at pressure, velocity, temperature, and density, right? So fluid static pressure, right? As I mentioned, even though the fluid might look still, its molecules move. Because of that, there is locally at every point in the fluid, there's change in momentum, which results in a force, which results in a pressure, and that pressure is what we call as the static pressure. Now, when you take velocity of the fluid contains two components. One, there is random motion, which is what we saw, right? The second thing is the bulk motion. So what do I mean by bulk motion? In the same example, right, the water cup, if I was taking the cup of water and if I was pouring it down on the floor, right, that is what you call as bulk motion, meaning when I'm really zoomed out, right, when I'm really zoomed out, the water is moving as a whole, which is what you call as the bulk motion. In addition to that, if I were able to somehow zoom in into the water as the water was falling down, the molecules in the water would still have the random motion. And that's why I mentioned that there are two components. Now, temperature. Temperature is essentially how fast the random motion is, right? And density at the end of the day is how close these fluid molecules are packed together, okay? So at the end of the day, these are the fundamental or primitive variables in fluid mechanics. Essentially, with these variables, you can determine the property of any fluid system or any thermal system that's out there. So you need to make sure that you understand these terms very well, you know what their units are, and you need to be able to define these variables and remember how they are computed if you are really serious about getting into aerodynamics or CFD. Okay, all right. So the next thing that we need to be really familiar is fundamentals of vector calculus. So we are going to be first looking at the basics of vectors, right? So primarily we are going to be looking at something called as dot products. Before we look at dot products, we will refresh our fundamentals in trigonometry. Then look at dot products, we'll look at its physical meaning. And we'll jump onto an Excel sheet where I explain what coordinate transformation is all about. So that being said, I think the video is already long enough, so it would be a good time to take a short break right now, and I'll see you guys in the next one. Thank you. Bye. Hey guys, hope you're all doing good and welcome to a new video. So in today's class, we will be looking at these topics. So I'll first help you refresh your fundamentals of trigonometry. Then we will look at the basics of vectors, talk about dot product and its physical meaning, and then we will jump into coordinate transformation. Okay, so let's talk about trigonometry, right? So at the end of the day, trigonometry from most of the examples, doesn't matter where you go to school, primarily at the end of the day, the applications are with respect to a triangle. If you have a triangle, how do you compute the sides? How do you compute the angles, right? That's essentially what trigonometry deals with, or at least one of the things it deals with. And you will see that there is always a right angle triangle, and there is an angle, right? So then the side that's actually opposite to the right angle triangle, that's the hypotenuse. So the other side, which is used to make the angle, right, that's what you call as the adjacent side. I'm pretty sure most of you know this, but one thing that I always try to do is imagine a crocodile, right? So imagine a crocodile that has its mouth open. My drawing of the crocodile is pretty bad. It looks like a lizard, but that's fine. right? So this is theta. Okay, so the upper jaw of the crocodile is the hypotenuse and the lower jaw is the adjacent side, right? Remember that the opposite side is this, right? So the opposite side is essentially where you have no parts of the crocodile, it's just the air, right? It's how big the jaw opens. Okay, so now once you have this, you know, there are so many things that you can calculate. So the first thing that we all know is that we know that cos of theta, right? Cos of theta is what? It's adjacent side by hypotenuse. In other words, the length of the adjacent side is nothing but h cos theta. And if you look at sin theta is nothing but opposite by hypotenuse. So the length of the opposite side is h times sin theta. So this is actually a great thing. What I can then do is I can use these two formulas to compute the adjacent side and opposite. So let's take a look at a few iterations here. So the first thing is I'm going to draw a triangle like this, and I'm going to say that this is theta. Okay, so we know that this is the adjacent side, right? Again, going by the crocodile example, and this is the hypotenuse, and this would be the opposite side. So the thing is, the length of the adjacent side is always going to be equal to h cos theta, and the length of the opposite side will always be h sin theta. The reason why I'm stressing on this so much is that you won't believe the number of people that have confusion with this concept, and at the end of the day, if you're able to get a firm hold of this concept, you can actually go a long way in learning mechanics, fluid mechanics, dynamics and whatnot, right? Because at the end of the day, what we are essentially doing is we are calculating components, right, which at this point might not be super clear to you, right? So now let me come up with a trickier example, right? So what if you have something like this, and this angle is alpha? So what is the length of this, right? And let us call this as L. Okay, well, this length is going to be L cos alpha. Okay, so essentially the thing that you can think of is, imagine that there's a light source here. If there's a light source here, and if the light actually falls, the length would essentially be the length of the shadow, right? And this is L cos alpha, and the opposite side would be L sin alpha. So similarly, let's take one last example. Okay, I promise. So if you have an example like this, where this is gamma and this is equal to r, right? Maybe I'll do capital R. So what is this length going to be? You should be able to tell me instantaneously. This should be r cos gamma, and this length should be capital R sin gamma. Okay, so make sure that you're comfortable with this, right? This is very, very important. And why am I talking about only these two components? Well, if you know these two components, right, the length of the hypotenuse is very simple. It's just Pythagoras theorem, right? It's r square sin square gamma plus r square cos square gamma, and if you simplify this, it's essentially going to be r square into sin square gamma plus cos square gamma. Sin square gamma plus cos square gamma is 1, so you have square root of r square into 1. That's going to be equal to square root of r square, which is going to be r, right? So a fairly roundabout way to basically calculate the length of the resultant is r, right? But that's the whole point. The reason why we remember components is calculating the resultant is so much easier. You just have to remember the Pythagoras theorem, which I'm pretty sure most of you, or in fact all of you, know, right? Especially if you're watching this course. Alright, so let me clean up this mess a little bit. Okay, so let's go back here. So I think that's essentially the basics of trigonometry that I want to talk about. I hope you guys are comfortable with this. If you want, feel free to think about what tan theta would be. Again, you should be able to calculate that. Okay, so now coming back here, the second thing that I want to talk about is basics of vectors. Okay, so vectors are quantities that have direction and magnitude. Okay, so if you take temperature, right? If you take temperature, and what I'm going to do is I'm going to take a room. So this is a simple room that I have. Okay, so at each and every point in space, for example, say that in the top there is a ceiling fan, right? That's a very bad looking fan, right? And say that you're standing here. Okay, so the fan is going to hopefully keep you a bit cool. So the temperature maybe somewhere here is going to be lower, right? The temperature at that point is lower, whereas the temperature maybe somewhere away from the fan, maybe at this point the temperature could be higher, right? So at the end of the day, temperature just depends on that location. There is just one value. Now from this point, if you are at this point, right, say that you are a person who is standing here, you will see that you are not cool enough, right? That's it. That because you're feeling that you're warm, right? But there is no direction sense to it, correct? If you close your eyes and if you kind of in the same spot just turn around, you will still feel the same lack of cool air there, right? And that's essentially what a scalar quantity is. What's a vector quantity? Well, a vector quantity is a quantity that has magnitude and direction. Okay, a great example for this is displacement. Okay, for example, if I'm asking you to go from here, for example, say that I have a planet, okay, right, and this is the center of the planet, and I have a control center at this point. Okay, now what I'm doing is I'm telling you that, hey, this is my x-axis and this is my y-axis, and this distance is the radius of the planet. Okay, so if I tell you that, you know, okay, you start from the center of the planet. Okay, so center point is the starting point, and for the ending point I'm saying that, hey, just travel a distance equal to the radius of the planet. In that case, I can end up anywhere. I can go here, I can go here, I can go here, right? And essentially there are infinite combinations for me. But what happens if I tell you that, hey, start from the center of the planet but travel along x-axis? This is what you would call as a vector quantity. There is a magnitude component, which is the distance that you're traveling, which is r meters, but in addition to that there is a direction, right, which is what you call as a vector quantity. Okay, so then the next point that we want to talk about is how vectors are represented. So for example, if you take velocity, the velocity vector is represented with an arrow on top, right? So this is what you would call as velocity vector. Okay, so I'm assuming most of you already know this. Remember, I'm not trying to teach you vector calculus from the start. I'm just trying to help you refresh the concepts that you might have learned in the past. So now let's take the coordinate system, x-axis and y-axis. The next thing that we're going to learn is something called as unit vectors. So unit vectors are essentially vectors that go along your coordinate system. So along x-axis, it's a common practice to say that the vector is called as I vector, and along y-axis it's called as the j vector. Okay, so it's essentially a direction. It's a vector quantity, but the vector has a magnitude of 1. Okay, is it 1 meter or is it 1 millimeter? Essentially unitless. It has only direction, right? It just says, hey, go along x by 1 units. The actual unit depends upon the value that gets multiplied. So for example, if I say I vector, that just means x-axis. But say that I want to travel 5 meters, right? So let us say the displacement is 5 meters. Okay, then d times I vector would essentially be the vector quantity, right? So where d is 5 and I vector is the direction. So the vector v is equal to 5 times I, which means I'm traveling 5 units, which is 5 meters along the x-axis, and this is what you would call as a vector quantity. Okay, and this is where we are slowly going to start applying the rules of trigonometry, right? So if you have a vector like this, well, it has two components, right? It has an horizontal component and a vertical component. So what is going to be the horizontal component? The horizontal component is essentially v vector cos, if this angle is theta, cos theta times I vector. Okay, and what about this guy? What about the y component? Well, it's v vector sin theta times j vector. Now notice that I'm essentially applying the same trigonometric concepts that we used before, and that's why I mentioned that those concepts are very, very important, because when you're dealing with vectors, which is everywhere in engineering, you need to be able to apply the same concepts again and again. So this is how you basically calculate the components of a vector. So now let's define vector multiplication, and primarily let's define dot product. Okay, so what's a dot product? So if I take a vector A and if I dot it with vector B, that's equal to magnitude of vector A and magnitude of vector B multiplied by cos of the angle between the two vectors. So if I have a vector like this A vector, and if I have a vector like this B vector, and the angle is alpha, so what is the right hand side? Well, let's just rearrange this, right? So this is A vector cos alpha times B vector. So what does magnitude of A vector mean? Well, the magnitude of A vector is very simple. So if I take a vector which is A1 I vector plus A2 j vector, the magnitude of A vector is equal to square root of a1 square plus a2 square. So the magnitude of the vector represents the length of the vector, right? And that kind of makes a lot of sense if you're talking about displacement. If you're taking the displacement vector, the magnitude of the displacement vector is the amount that you are displacing in meters or kilometers or centimeters, right? But if you have a force vector, the magnitude of the force vector is essentially the value of force that you apply. Okay, I hope that makes sense. So imagine that a vector is essentially the force. Okay, so in other words, I'll just call this as f vector, and then I have another vector called d vector. So d vector is my displacement vector, right? So you can kind of think of this as, alright, I have an object like this, right? I have a box like this. I am trying to move that object by applying a force in this direction, and I'm moving it in this direction by d units or whatever, right? And the angle is alpha. So when I do f vector dot d vector, I get the magnitude of f vector, the magnitude of d vector times cos alpha. Now just rearrange this a little bit. So if we take f vector cos alpha times d vector. Now what is f cos alpha? Well, that's the component of force along this direction, right? So in other words, this is nothing but the component of force, or it's the magnitude of force along the direction of displacement. Okay, I hope that makes sense. So in other words, this is kind of giving me a small f. I'm going to call it a small f. Small f times d. I have force times displacement, which is nothing but the work done. Okay, so dot products are really awesome because it helps me calculate work done in a particular direction, right? And if you think about it, for example, if you have a 3D coordinate system like this, you know, x, y, and z, and say that I take a box like this, right? Say that I'm taking it in a very complex direction, okay, something like this, and I'm applying a force like this, right? And you can kind of immediately see that by applying a force like this, it's going to be very hard for me to take the object here. And especially if this object is constrained to move, for example, if it's a link, right? If it's a link or if it's a joint which can move only in this direction, applying a force like this is not going to make me move it. And if you kind of want to understand this in a better way, think of a door. So let me try my best to draw a door, right? So this is a door, okay? And this is the door knob, and this is the hinge. So the constraint is that the model rotates about this axis, right? So this is a door. Now if you want to try to open the door, if you would apply the force like this, correct? And that would essentially displace the door in the radial direction. So that's how you make the work happen, correct? Now for the same doorknob, what happens if you do the work like this? If you put the force like this, you might break the doorknob, but you're not going to get work done, right? And that kind of shows up in the math by the cos angle, right? So cos of 90 is what? 0. So if your displacement and forces are 90 degrees inclined, then it doesn't matter how much force you put, you will end up maybe breaking the doorknob, but you will not be able to move it. So that's why dot products are very, very important. And I hope now you know how to actually compute the dot product. So a few rules about a dot product. So what is the dot product of I vector dot I vector? Well, it's nothing but magnitude of I vector, magnitude of j vector, and cos of the angle between I vector and I vector, which is 0, right? Cos 0 is 1, the magnitude of I vector is 1, and magnitude of j vector is 1. So in other words, I vector dot I vector is 1, and similarly I vector dot j vector is going to be 0, right? So these are important concepts that you need to remember. Alright, so that being said, now let's take a look at coordinate transformation. For example, let us say that I have a coordinate system like this, x-axis and y-axis. And now what I'm going to do is I'll say that I have a vector called as a vector. Okay, I'm just going to call this as a vector. Okay, now what I'm going to do is I'm going to think of another coordinate system which I'm going to call as x1 and y1. Okay, and I'm going to say that the coordinate system is rotated by an angle of theta. So this would be theta and this would be theta as well. The other thing that I need to define are my unit vectors. So what I'm going to do is along the xy coordinate system, my unit vectors are going to be I vector and j vector, and along my x1 y1 coordinate system, my unit vector is going to be I1 vector and j1 vector. So alright, so now let me define a vector. in the x, y coordinate system. I'm going to say that A vector is A times I vector plus B times J vector. Okay, so for the sake of clarity, what I'm going to do is I'm going to draw the xy coordinate system separately, and I'm going to represent the A vector there. Okay, so what is A? Well, A is the component of the vector A along the x-axis, and B is the component along the y-axis, and that's why A vector is equal to AI vector plus BJ vector. So in x1 y1 coordinate system, right, I kind of drew it like this, right? It's inclined x1 y1, and my A vector is kind of maybe closer to the x1 axis, right? So here this one would be A1, right? The magnitude or the component would be of different length, and this length would be B1. Okay, so in the x1 y1 coordinate system, A vector is going to be A1 I1 vector plus B1 J1 vector. Okay, but here's the interesting thing, right? At the end of the day, they are both A vectors, but in one coordinate system it has a particular component, and in the other coordinate system it has a different component. Now the question we need to ask is, how do I go from one component to the other component? Well, it's very simple. So what I'm going to do is, I'm going to take the first equation. Okay, I'm going to say A vector is equal to AI vector plus BJ vector. Okay, and what I'm going to do is, I'm going to multiply this with I1 vector on both sides. So A vector dot I1 vector is equal to A vector times I vector dot I1 vector plus B times J vector dot I1 vector. I made a small mistake. This is not A vector, it's just a component of A. Alright, so what is I vector dot I1? We know that I vector is here, I1 is here, right? So this is going to be magnitude of I vector times magnitude of I1 vector cos theta plus B times, so what's the angle between J vector and I1 vector, right? So that's a bit tricky, you might not be able to see this, so let me just draw that separately. So this is J vector, okay, and this is going to be I vector. Okay, I and J have an angle of 90 degrees in between them. Now this is I1 vector, right? So this is I1 vector and this is an angle of theta, correct? So what should this angle be? Well, this should be 90 minus theta. So in other words, if I'm trying to compute the dot product, it's very simple, right? It's a magnitude of J vector multiplied by magnitude of I1 vector cos 90 minus theta. So what is A vector dot I1? Well, that's going to be A1, correct? So A1 is going to be A times the magnitude of all the unit vectors are always going to be 1. So this and this and this, all of them are 1. So I'm left with A cos theta plus B cos 90 minus theta. Similarly, so if I simplify this one more step, I will get that A1 is equal to A cos theta plus B sin theta, right? Because cos of 90 minus theta is sin theta, and this is what you call as coordinate transformation. Think about it. If I know my angle theta, I can use the values of A, B and to compute A1, and that's exactly what I have done here. A and B are the components of vector in the xy coordinate system, and theta is the amount by which the coordinate system is rotated, right? Based on just these three information, I can compute the components. I can do a similar exercise. So instead of doing a dot product with I1 vector, if I do a dot product with J1 vector, I would get an expression for B1, and feel free to do that as part of your exercise. Okay, and this is what you would call as coordinate transformation. The reason why this is so important in aerodynamics is when you are measuring aerodynamics forces, it's always with respect to one coordinate system. In one of the upcoming videos, I will be deriving the force equations for an airfoil, where the coordinate system will be centered based upon the chord of the airfoil. Whereas when you're trying to estimate the aerodynamic forces, that coordinate system will be placed on the surface of the airfoil, right? So you need to be able to calculate the net aerodynamic forces based upon the chord-based coordinate system at the end of the day, right? And that is where coordinate transformations are very, very useful. Alright, in addition to this, if you come from a solid mechanics background, or if you're interested in solid mechanics or multi-body dynamics, coordinate transformations are used all the time so that you can convert quantities that are calculated in one coordinate system into quantities that are calculated in a different coordinate system. Okay, so I'm going to show you one more example, but since the video is already too long, I will talk about that in the next video. Thank you so much. Bye. Hey guys, hope you're all doing good and welcome to a new video. So today I wanted to give you a practical example of coordinate transformation. So here what I have is I have a two-dimensional space and a replica of that is here. Okay, now I actually have 4 position vectors, right? So essentially for each and every point here I have the vectors. Alright, so now assume that there is a coordinate system that's attached to this particular box here. Okay, and if I am rotating the coordinate system, right, for example, take this box and say that I'm rotating it by 45 degrees. The relative position of those points with respect to each other is not going to change if I'm rotating all the points by the same amount, right? So the question is, now say that you are in the rotated coordinate system. Okay, so for example, in the original coordinate system, this point is 0, 0 and this point is 0, 1. Now if the coordinate system is rotated by 10 degrees about the origin, then what would be the coordinates of this point? And that's essentially the problem of coordinate system. So for example, if the coordinate system was rotated by 10 degrees, okay, in the original coordinate system this point is 0, 1, but if the coordinate system has been rotated by 10 degrees, meaning assume that this is x-axis and this line right here is y-axis, right? Now in the new coordinate system, the position of this point is still the same. It is still 0, 1, right? Because when the coordinate system rotates, this point still stays in the same place. But with respect to your original coordinate system, this point has now moved. And you can see here that this is what I'm calculating here. So I have in the first 4 lines here, I have the coordinates of each and every point. So this would be 0, 0 and that's typed here. And for this point, it's 0, 1. And this point it's 1, 1 and this point it's 1, 0, and then finally coming back to the origin to close the loop 0, 0, right? Now when I rotate this by 10 degrees, you can see that the first and the last points don't change because they are origin, but the other points are actually moving, right? And you can see that it's essentially a combination of cos and sine transformation, right? Which we derived. We essentially derived that for just the x coordinate, right? And I told you that in the previous video that we could derive the same equation for the y coordinate as well. What I've done is I've just derived it and essentially I've put in the formula. So for x coordinate, you can see that the formula is cos theta times the coordinates plus sine theta times the coordinates, whereas for the y coordinate there is a minus sign, okay, that comes out. But essentially that's the transformation that I apply for all the cells and I'm able to do this. So what I would definitely encourage all of you to do is build up an Excel calculator like this, derive the coordinate transformation equation so that you can essentially see what happens when you rotate the coordinate system and what happens when you rotate the coordinate system and how the coordinates of each and every point change with respect to the original or the global coordinates. Okay, with that I would like to conclude this video and I'll see you guys in the next one. Thank you. Bye. Hey guys, hope you're all doing good and welcome to a new video. In today's class, we will be deriving equations that can be used to compute the aerodynamic force on any objects that you want. But before we do that, I kind of wanted to talk about the 2 most important reasons why aerodynamic forces exist. So first is going to be pressure force and the second is shear force. So what's the difference? So I'm going to use my poor drawing skills to draw a car, okay, and let us say that this car has a spoiler. Okay, so now what I'm going to do is I'm just going to be focusing on this spoiler. Okay, I'm just going to zoom in and let us say that it has this particular shape in it. Okay, So we're just taking only the top part, right? So there's a connector which we are just ignoring, okay? So when the car is actually moving, in this direction, right? The air essentially moves in that direction, right? In other words, if you imagine that the car is stationary and if you move the air, it's essentially the same effect. So we are assuming that the air actually moves from left to right. So if you look at a region away from the wall, and maybe I'll use a different color here to kind of show what's happening. Say that I am following the fluid particle, right? The fluid particle, these are the positions of the fluid particle at each instant of the time. Okay, and if I'm drawing a line, if I'm essentially following this particular fluid particle, this is what I would call as a streamline. And the streamlines, if I'm looking at a region away from the wall, is going to be close to parallel. So what happens if there's a fluid like this, right? When the fluid basically moves like this, you can definitely see that the fluid is going to hit the wall. And when it hits the wall, that particular force can be translated, right? So if I'm having a force like this, I can resolve this force into a normal component and the tangential component. So let me just zoom into that area. So this is that particular surface, and say that I have, let us say that the fluid just hits the wall as it is. I can construct a component. I can use a local coordinate system there to construct a component like this. So this is my coordinate system, right? This is not the direction of the forces yet. Okay, so I can have one force along, you can call this as y direction and x direction. So at any given point, there is a force along the local y coordinate system. Remember, this is a local system, and there is a force along x. So this along y, right? I can say that this is essentially force normal to that surface at that point. Okay, so let's kind of break this sentence. Force normal to the surface. So what does normal mean? Normal means perpendicular. So for example, if I have a surface like this, right, at this point the normal is like this. So the way you draw the normal is, when I'm looking at this, this angle should be 90 degrees. So for example, if a surface is like this, the normal is going to be like this. So at each and every point there is one normal, correct? And you can see that the rate at which the normal changes essentially tells you the curvature, how the object is getting curved. For example, if you take a plane, the normals don't change at all, right? They are always in the same direction. But if I have a slight curve, I can actually show you that the normals actually change. How much do they change? Well, I can essentially take this, construct an angle, and that's the angle, right? That's essentially how much the angle changes. With this normal change, I can compute the radius of curvature. And if the normal change is too steep, right, if the angle changes, that means the curvature is high, right? If the curvature is very low, that means it's not turning too much, right? The reason why I mentioned that is, at the end of the day, is something that people look at, because a gradual change in curvature leads to lower pressure losses. A sudden change in curvature leads to higher pressure losses. Okay, so coming back to this point, so the force normal to that surface at that point, that's what you call as the pressure force. So the pressure force always acts normal to the surface, and then you have the shear force, which always acts tangential. Okay, so it doesn't matter which shape I have. So for example, if I take this particular location, in this particular location, assume that this is the normal, this is the tangent, right? So the force in this direction is the pressure force, and the force in this direction is the shear force. So now that you have understood what pressure force and shear forces are, right, I want to explain a sign convention. We generally assume that pressure forces always act normal to the surface and towards the body, right? So when you say pressure force, I would essentially say this is how it acts. So for example, if I want to show you the pressure force here, I'll say that, it acts like this, right? And if I want to show it here, I'll just say the pressure force acts like this. Well, the tangential force essentially would depend upon direction in which the fluid is flowing. So if the fluid is flowing this way, I would basically say that the shear force is in this direction and it's in this direction in this case. Okay, I hope this makes sense. So now we've talked about sign conventions, but from a physics point of view, right? From a physics point of view, what does pressure forces mean? Well, pressure force would essentially be the force that's imparted on the surface, right? It would be the forces that's getting imparted on this particular body because of molecules that are just banging on the surface in a direction that's normal to the surface. Then you might ask, what is shear force? Well, so shear force is essentially a pull that the object experiences because of airflow. Now when you're driving a car on the road, if you try to put your hand outside and if you try to keep it parallel to the road, you will experience that on top of your hand you can feel the air, right? The air is actually shearing your skin, right? It's trying to shear your skin, and that's what shear force. It's the pull force that your hand would experience because of layers of air shearing over your arm. So in terms of molecules, right? So if you remember in the previous example, I said that like if you're really far away from the wall, the streamline would be just parallel, correct? But as you approach, the closer you are to the wall, the slower your velocity is. Because if you zoom in really, really close, what's going to happen is the wall is essentially going to try and stop the air molecules that are really, really close to the wall. So in other words, you can essentially say that the fluid velocity there is 0. So what's going to happen is, right? So the fluid velocity here is 0, right? Whereas on top of this, right, there is a layer of air molecules, right? And those air molecules, they get pulled, they are slowed down because of this 0 speed molecules, but they can still travel. So that's why their velocity is slightly larger. So the length of the arrow represents the velocity. Now what about the layer of molecules above this? The layer above the second layer would travel a bit more faster, and the layer above that would travel a bit more faster, and at some point you will see that a particular maximum value is reached, and then after that the velocity is pretty much the same. Now when you're really far away from the wall, you essentially get the mean velocity, which sometimes people call as V infinity. And when you're closer to the wall, the velocity is 0, right? And up until a point where you are at 95% of V8, this is what you would call as the boundary layer, right? The boundary layer is where the shear forces are really dominant, and after that the shear forces are essentially 0. Now with respect to the shear forces, why is one layer of air slowing down the other layer? Well, if you think about it, that makes a lot of sense, right? For example, consider that you are on top of a road. I'm putting a box and I'm tying a rope here, and I'm giving you this rope, and I'm asking you to pull this rope in this direction. Now you will feel some resistance, correct? And that resistance depends upon the friction between these two boxes. So if the road was not smooth and if the friction was too much, you would definitely feel the effort. And similarly, if it was a polished surface, then the box would basically slide very easily with just a little smaller force. So if I say that in the first scenario it's F1 and in the second scenario it's F2, F1 is going to be much greater than F2, right? We have all experienced this. Now similarly in fluids, you have a layer of molecules and then you have a layer of molecules on top of this, right? Now just like you have frictional force here, because of the relative velocity, for example, this guy is traveling at say 5 meters per second and this guy is maybe traveling at 3 meters per second, right? There is a force, and the level of shear force depends upon the difference in velocity, right? Because if I'm traveling the same velocity, for example, take one more layer on the top which is also traveling at 5 meters per second, there is no force, right? There is no difference. But in this case there is a relative velocity, there is a difference in velocity, and the shear force is going to be proportional to that velocity, and the proportionality constant is the fluid property called as viscosity. And so if you think about it, viscosity is super important when you are near the wall, right? So when you are near the wall, when you are within the boundary layer, you need to make sure that viscous effects are included. However, when you are outside the boundary layer, you can see that the velocity is pretty much the same. In other words, the shear forces are pretty much close to 0, which means the effect of viscosity is also 0. And this is what you would call as inviscid flow. So in inviscid flow, you are not saying that viscosity is 0, but you are just saying that the flow is as if viscosity is 0, right? In other words, the viscosity of the fluid really doesn't matter outside the boundary layer, whereas inside the boundary layer it matters. Okay, this is actually very important, because when you are trying to simulate flow over any object, right? It could be a bike, it could be a vehicle, it could be a bicyclist. It really doesn't matter. If you are interested in capturing the shear force, then you need to include viscosity, right? Now the reason why I'm saying that is, for all practical aerodynamic applications that you might deal with in the future, you will always have to consider viscous effects. Now here is an important thing. Depending upon the physics of the fluid, the viscous effects might be smaller, right? The viscous effects might be smaller, but for engineering applications, it's not going to be negligible, right? And usually when you're trying to perform aerodynamic analysis, you always want to capture the pressure forces and the viscous forces. Okay, all right. So coming back to the above image, from a physics point of view, pressure force is essentially the normal force that a body would experience by bombarding of molecules in a direction perpendicular to the surface. Shear force is essentially the pull experience that the surface is going to experience because of the difference in velocities along the normal to the surface. Okay, I hope that makes sense. Okay, all right. So the next thing that we are going to be looking at is how engineers look at these pressure forces and shear forces together, because we understand that it's basically computed at each and every point, right? You can see that at each and every point I can compute the pressure force and the viscous force. But what do engineers look at? Do they look at the set of all data, or do they just look at one data together? That's what we are going to be looking at next. So to do this, I'm going to take an airfoil geometry. So for those of you who don't know what an airfoil is, let's take the wing of an aircraft. Okay, again, I'm going to use my poor drawing skills to draw a plane, and hopefully this looks like a plane. Okay, all right, I hope you're satisfied with my drawing. Now if I take a cross section of the wing, I'm essentially going to get a shape like this, and that's exactly what I'm showing here. I'm just taking the cross section of the wing, and I'm saying that, well, you know what, V infinity is the speed at which air is flowing, and if this, what I'm going to do is I'm going to mark a point here, and I'm going to say this is my x-axis and this is my y-axis. I'm going to say that this is my global x-axis and y-axis. Now here's another thing. What I can do is I can take this point, which is what you would call as the leading edge, right? It's called as the leading edge because this is the edge that the fluid first experiences, and then this is what you call as the trailing edge, right? Trailing as in behind, right? So the fluid is going to experience the trailing edge later. Now if I draw a line between them, I get a line, right? So what I can do is I can say that this right here is my x1 prime and this right here is my y1 prime, and I kind of hope that you start seeing the importance of coordinate system here. Now from a world point of view, for example, if you're an observer here standing, this is your x coordinate system, right? This is your x and this is y, and what you are essentially interested in is, if this is an airplane, you want to capture what is the total force along the y direction. What is the total force along the y direction? This is what you care about, because that will help you explain, that will help you understand if your plane can essentially lift. That will actually help you understand if your wing is good enough to generate the required force or not, right? So an example, say that I say that my weight is 100 kg. I don't weigh that much. I'm just giving an example so that the math is easier. So how much is this in force? Well, so it's going to be 100 times 9.8, and for convenience I'm just going to assume 100 times 10, so that's going to be 1000 newtons, right? If my wing generates 1500 newtons, that means it can carry me, right? It can carry a single person. Obviously for commercial airliners you will multiply this with a silly number, right? Like 200 or 300 minimum. This is the minimum force that it needs to be carried, right? Think about this. I'm not including any other weights, right? The weight of the engine, the weight of the plane, you know, I'm not taking any of that into account. But the whole point is, if I'm trying to create a wing, I am interested in the value of Fy, because that tells me what is the force that is going to be used to lift the plane, and this is what you would call as the lift force. And similarly, I would look at the force along the x-axis, because that is the force that's trying to stop my plane, right? See, think about this. If the flow is going like this, any force that acts in this direction is going to pull my plane, right? It's going to stop my plane. And this force which drags your plane is what you call as the drag force. Okay, so I have Fx and Fy. Now in that case, why did I draw x1 prime and y1 prime? Well, it turns out that they are also important. So this right here, the line that I've joined, that's what you call as the chord line, CHORD, chord line, and the length of the line is chord length, right? So this is basically the chord axis, right? And this is the direction that's normal to the chord axis. And generally, this direction is called as the A direction, and the perpendicular direction is called as the N direction. So I might be interested in calculating the force along the axis of the chord, and I might also be interested in calculating the force along the normal direction. So now suddenly what happens is, I might find myself in a position where I have Fy and Fx, and I need to convert that into Fn and Fa. And this is where coordinate transformations are used all the time. And for Fy, if I basically say Fy is actually L and drag force is D, you can actually apply coordinate transformation to this, and what you will find is that the lift force is equal to the normal force. In fact, what I'm going to do is, for the normal force, I'm just going to use the letter N, N times cos alpha, which is the angle of attack, minus A sine alpha. And similarly, I will have for drag, I will have N sine alpha plus A cos alpha. Oh, I almost forgot. I did not say what alpha is. Well, you can see that the plane is actually tilted, right? The wing is actually tilted. So this angle is called alpha. It's what you call as the angle of attack. Now guys, you might ask me, hey Sarang, why are we interested in normal force and axial force? Well, the answer is very simple, guys. See, if you look at the airfoil, right? You know, so essentially this airfoil looks flat, correct? The wing is at 0 angle of attack. Similarly, what I can do is I can draw a steep airfoil, right, so that I can kind of show that the angle of attack is modified. Now the thing is, the coordinate system along the chord axis and the normal direction, right, this is what you would call as a local coordinate system, correct? And essentially, when I'm computing the quantities in local coordinate system, right, if it can be drag or pressure force, I really don't have to worry about it, because it's a local coordinate system. In other words, I can just say that, you know what, this is my A and this is my normal direction, and what I can say is, I can put my airfoil in an horizontal direction, and I can then say that, you know what, for example, let's take this picture. You know, if we assume that air is flowing in this angle, what I have done here is I made the airfoil horizontal, which means the air would actually go like this, correct? I hope you can imagine. So in other words, let me see if OneNote allows me to rotate this. For example, if I take this image, unfortunately I don't think I'll be able to rotate this. Let me see if there is any option in view to kind of rotate this guy. Okay, so looks like there is a rotation option. Maybe let me see if I can rotate it by 45 degrees. Alright, so you kind of see that, right? When you actually rotate this, this also changes. And this is the advantage of it, because now I can actually get the components along my normal direction and axial direction, and to convert it into the global system I can use this transformation here. Okay, so in fact let's just walk through a simple example. Alright, so what I'm going to do is I'm just going to draw the same picture. Okay, I'm going to have my coordinate system along the axial direction and normal direction, right? So I have my x and y. Okay, and I'm assuming that the flow is coming in at a particular angle, alpha, correct? Okay, so now let us say that this is point A, right? Point A, and this is point B. What I'm going to do is I'm going to take an arbitrary point here, and I'm going to first draw the pressure force. Pressure force, as I mentioned, always acts perpendicular to the surface, correct? And what about shear? Well, shear would be in the direction of fluid flow, so I'll just draw it like this, right? So this is what I'm going to call as the pressure force, and this is what I'm going to call as the shear force. Alright, and then what I'm going to do is I'm going to take a small sized element here, right? I'm going to take this small length, I'm going to call that length as a ds. So I'm looking at the pressure and shear in that small area. Okay, so let's compute the forces. So if I just draw the small area ds, and if I take pressure, correct, now the pressure is going to have an horizontal component and a vertical component, right? So how is that going to be? The vertical component is going to be down and the horizontal component is going to be like this, correct? And I know that this angle is say theta, right? I'm just assuming that it's theta. So now how do I compute the pressure force along x-axis and y-axis? That's the problem. So let's just do this again. I'm going to just draw x and y-axis separately, and I have ds, right? This is my area, and I'm going to say that this right here is my pressure force. Okay, and this is theta. Okay, so then what is the vertical component? The vertical component is along y, so the vertical component is along y direction, right, which is also nothing but the normal direction. So the vertical component along the normal direction force is going to be pressure times area, right? So but here's the thing, I have to calculate the vertical component, so which would be p times cos theta. This is where you have to use vector components. I'm taking p, projecting p cos theta times ds. But here's the thing, what's the direction of the force? It's going to be downwards, which is opposite to the y-axis, so you will get a negative sign there. Now similarly, let's take the shear force, right? And let's create a separate diagram for it, maybe on the top here. Okay, it's the same thing. I have my same surface ds, right? And this is direction of the shear, and this is theta. So what would be the normal component? Well, the normal component would be this right, which would be tau s times sine theta, correct? Oh, sorry about that. The normal component would be downward pointing. So the normal component would be tau s ds times sine theta. It's also going to be negative, correct? So this is basically the expression for f along the normal direction, or I can also call this as fy. Okay, now what is going to be fa? Well, let's do the math. So if you go here, if you look at this, the horizontal component is going to be negative, and I know that that's going to be negative because it's along the negative direction, and it's just going to be minus p sine theta ds. And if you look at the shear stress, in the shear stress, the horizontal component is going to be positive because it's the horizontal component is going to be along positive x-axis. So then in that case, that's going to be tau s times ds, and what will I need for it? I'll use the cos theta parameter. So there you go. With just pressure and shear stress, I can calculate Fn and Fa, and if I scroll up, I can use this particular formula, right? So n is equal to Fn, right? N and Fn are the same, so I can basically use Fn here and Fn here, and I can use Fa here, and I can use Fa here. And using this formula again, I can calculate lift and drag force. And the entire field of aerodynamics, especially with automotive applications, is all about computing L and D. That's it. We have solved the problem of aerodynamics. But here's the thing, what we have done is extremely theoretical. The issue is, how would you know what tau s is? Everything else is a geometric quantity. Think about it, guys. Everything else is a geometric quantity. ds is known. It's a length, right? I can measure, I can use a CAD package to get what my ds is. I can figure out what sine theta is. It's a geometric parameter. But where am I going to get p and where am I going to get tau s from? That's the problem. And that is where, you know, we have to figure out a way to determine p and tau s. And unfortunately or fortunately, there are two ways to estimate it. One is you can do an experimental method where you can use a pressure sensor, a static pressure sensor, to get pressure, and getting shear stress is far more hard experimentally because you will have to somehow compute the rate at which the velocity is changing, right? So you'll have to make very, very tiny measurements, and it's going to be very hard to do that in a complicated model. So that is why what people generally do is they measure static pressure. Okay, static pressure can be measured very easily, and the thing is you can easily measure the lift force and drag force. Lift force and drag force can be measured, and then you would use an analytical technique or computational technique to get the value of shear stress so that your lift and drag matches. That's it. Because if you know your lift and drag and if you know your static pressure, think about this. You can calculate your shear stress, correct? So that's how it works. But here's the thing though, we have not solved an important piece here. How am I getting the total force, right? So here I'm getting Fn, but isn't that the force only in this particular element? You would absolutely be right. So the way you would actually get the true Fn, and I should have made this a bit clear. In fact, this should be like dFn, right? Because it's force over a small element. The way I would get capital Fn, or the total force, is essentially by integrating that equation. In other words, I would split this into so many individual elements, right? And then essentially I would just calculate the resultant Fn, which is nothing but, if you think of this as a curve, I have to go from A to B and I have to basically perform an integration, right? I have to integrate all my dFns, right? And I also should do the same thing while going from B to A as well, correct? And I would have to do the same thing for my axial force where I integrate dFA. Okay, I hope that makes sense. So in fact, this is what a computational tool would do. In a computational tool, it's going to divide the surface into individual pieces, which you would call as mesh elements. And for each mesh element that is near the wall, it would compute the forces, split it into components, and calculate the resultant force, which would be your drag and lift values, right? So that's method number 2. It's computational method. But the problem with computational tools is that you don't know if your answers are correct, and that's why you first perform experiments for a few cases, right? If possible, you get your lift values and you get your drag values. When you do computational fluid dynamics, you will essentially calculate P and tau s. So you would be able to get tau s and P. Then you would do the integration. And once you do the integration, you will actually get a lift and drag force, but these would be computational values. So I'm putting a small c there to stand for computational. And you would compare how well these match with your L and D. And that's basically it. This is exactly how aerodynamics is done, right? But the thing that we have missed, and that's where the cream of the engineering lies, is, hey, how do I modify my geometry to reduce drag? How do I modify my geometry to reduce lift? Well, that is something that you worry about at an advanced level, and we are not going to be doing that in this short course. It's clearly out of scope. But the whole idea is, if you're able to come up with a framework which estimates lift and drag, then you can do all sorts of modification and learn from that framework. This is exactly how people learn in experiments as well. You do a lot of trials and figure out what happens with it, correct? Similarly, if you have a computational model, then you have a computational framework which will help you perform a lot of experiments and learn from your model. But the biggest issue is that the computational model has to be accurate. If it is not accurate, then anything that the computational experiment teaches you is totally wrong. And that's a big risk. And that's why it's very important to do this very carefully. When you do a computational study, you always do the validation first to see if you're getting the answers with the right quality and with the right quantity. You do it at least for one case. Once you're satisfied with it, you move on to a larger problem which is still similar to the original problem that you had performed the validation for. Okay. Alright, that being said, I would like to conclude this video. I'll see you guys in the next one. Thanks. Bye. Hey guys, hope you're all doing good and welcome to a new video. So in the last class we had derived the aerodynamic forces that actually matter, which would be the pressure forces and shear forces. We computed them in a chord based coordinate system, and in the video before that we learned how we can actually convert results from one coordinate system to another coordinate system, primarily how you would transform vectors from one system to another system. Now that we have done that, we should probably talk about fluid flow regimes, because if you're interested in aerodynamics, you should understand the key differences between inviscid flow and viscous flow. If you had watched the previous example where I talked about boundary layer and how the effects of viscosity is very important, that's what you would call as a viscous flow. And if you want to take the simple approach here, and if you feel like you want to get into aerodynamics, then purely focus on viscous flows. There is going to be very rare cases where viscosity is not going to be playing a major role. And then the next thing is compressibility effects. So what I mean by that is fluid has a particular density, correct? And when you say that density is constant, that's what you call as an incompressible flow. And when density changes, that's called as a compressible flow. Now, when you're starting from the governing equations, right, the Navier-Stokes equations, depending upon the choice that you make, you will end up with different equations. Okay. For example, if you have taken a class on thermodynamics, you might have studied something called as the steady flow energy equation, right, which you would essentially get by assuming compressibility, meaning you would assume that the flow is compressible and you would end up with such an equation. So we say that the fluid is incompressible when its density is not changing. And if you have taken any thermodynamics course or fluid dynamics course, based upon incompressible flows, you can figure out the relationship between pressure gradient and velocity, correct? And similarly, if the flow is compressible, you can get another set of governing equations, correct? One is going to be compressible and the other is going to be incompressible. But which is going to be correct? Well, it turns out that the correctness depends upon the speed of sound, right? So speed of sound is calculated by square root of gamma RT for gases, right, and for fluids. So what I have done here is I have essentially used the modified steady flow energy equation, right? And you might have seen an expression like this: 1 plus gamma minus 1 by 2 multiplied by Mach number square whole power 1 divided by gamma minus 1, right? Pretty sure you have studied an expression like this. If you do not refer to any standard gas dynamics textbook, and you will be able to find that information. So what I've done here is in Excel, for the density ratio, right, for the upstream and the downstream density ratio, what I'm basically doing is for different Mach numbers, I'm looking at the density ratio. So when the Mach number is really small, you can see that density really doesn't change. But when Mach number increases, right, this is essentially steady flow energy equation, guys, meaning fluid is actually moving. It's an open system. If you do an energy balance where you would compute the energy entering into the system versus energy leaving the system, you would get this equation. Okay, what I'm looking at is the density ratio. So if the density ratio is 1, that means the densities are the same. In other words, for that Mach number, you can actually use incompressible flow equations. But you can see that when the Mach number keeps on increasing, right around 0.3 is where the difference or the ratio is 1.048. So if the ratio is 1.048, that means that the outflow density is 5% more, right? And this is where engineers agree that we should switch to compressible flow equations. And why are we deciding 5%? Well, 5% is, it's not an analytical number. It's just whenever you perform engineering, if the error is less than 5%, people are generally okay with it, right? That's how the 5% is chosen. If we are living in a different universe where 10% is okay, then we would basically say that See, if the Mach number is greater than 0.43, use the compressible flow solver. So, but in the current world that we are in, 5% error rate is generally what you would see engineers are okay with, and for that 5% change, the Mach number corresponds to 0.31. So that's why you will see that people say that if Mach number is greater than or equal to 0.3, it's always better to start using compressibility, right? That being said, in general, if you're dealing with gas, I would say just straight up use compressible flow equations. That way you don't have to worry about this problem at all. Okay. Alright, so with that I would like to come to the final slide of the presentation, where we are ready to define what aerodynamics is. Essentially, aerodynamics is the study of how air flows and interacts with objects. That's it. The object can be a passenger car, it can be an electric vehicle, it can be a fighter plane, it can be a drone, right? Doesn't really matter. And aerodynamics, as we discussed so far, it's all about resolving two forces. It's all about getting the pressure force and the shear force. And in order to do that correctly, you need to make sure that viscous effects are taken into account. And you always use compressible flow equations if you are studying about aerodynamics. Remember these rules so that you won't make mistakes when you are starting to work on large aerodynamics based projects. Thank you so much for watching, and I'll see you guys in the next one. Bye. Hey guys, hope you're all doing good and welcome to a new video. In today's class, we will be looking at some high level things. First is, why care about aerodynamics? So far in the course we have actually learned how to calculate the two most important aerodynamic forces, but we really did not talk about, why we even bother to calculate them, right? And for this, to give you the 50,000 feet view, we will be taking a look at a very simple problem, right, which is essentially oil consumption in United States. Why are we doing this for the US? Well, the data is available at a very high quality. I couldn't find similar data for any other country, that's why. And then when we talk about oil consumption, you will see an amazing problem which can be solved only by aerodynamics. And hopefully that will give you the motivation to learn more about this great subject. And obviously, I've kind of given you a hint. The problem is always about drag forces, right? Drag forces essentially drags the body, meaning you need to kind of give more force and then spend more engine power or battery power to overcome the drag. And that's essentially the problem. The idea is to get a big picture of how big this problem is, okay? And that's kind of what the focus of this video is. So, big picture, why care about aerodynamics? Well, if you take class 8 trucks, class 8 trucks are really heavy. They weigh about 15 tons and they consume 10% of the total petroleum in the US. Now remember, this is 2007 data. I could not find data later, but assume that it's 10% still. That's perfectly fine. In 2019, US consumed 40 billion gallons of diesel. So if you assume that 10% of that was used by class 8, that's 4 billion gallons. Now the silly thing here is 65% of the fuel, guys, is wasted by the class 8 trucks to just overcome drag force. That's it. 65% is just wasted. In other words, 65% of 4 billion gallons is 2.6 billion gallons. I have a typo here. This is not dollar. This should be gallons. So think about this. 2.6 billion gallons of fuel is essentially wasted. Now if you assume that each gallon is worth $3, that's $7.2 billion. And here's the thing, this is only on class 8 trucks. And that's why the market for drag reduction strategies or drag reduction experiment is huge. People spend on that. If you are a company that makes trucks, you would be ready to spend $1 billion, because if you don't do that, you will be spending $7.2 billion every year. So if you are a big truck company and if you have the money, and if I go there and say, hey guys, listen to me, I have this wonderful technique to reduce drag force that's going to reduce your fuel consumption from 2.6 billion gallons down to 1.3 billion. The company would be saving how much? It would save $3.6 billion per year. And the company would be happy to give me $1 billion. Okay. But we all know that that's never going to happen, right? But if there is a solution that can give such a drastic reduction in drag, I'm very sure that any truck company is going to be offering a huge amount of money. We don't know if they will offer $1 billion, but it's going to be a huge amount of money savings, because they're going to save $3.6 billion every year. So in 10 years, they would have saved $36 billion. And to give $1 billion for that, it doesn't seem like a bad price, right? That's essentially the business case of the problem. Now, here's the thing. Class 8 trucks would basically be a part of it. If you take a look at trucks in general, they consume around 25% of the total fuel consumption. So the market size is actually double of what I just now described. So it's not 7 billion, it's actually 14 billion. So it's a lot of money. And that's why a lot of companies have a major incentive to reduce drag. In other words, you see a lot of software companies come up with standalone CFD programs that can be used for external flow dynamics, right? That's because that becomes a handy tool for designers to quickly check if their designs reduce the drag or not. Alright, so remember, it is still a huge market, and that's why people spend a lot of money on experimentation, coming up with new ways to reduce drag and so on. Now, here's an important question. How would you measure drag? Well, it's very simple. You would just put your vehicle in a wind tunnel, and what you're essentially going to do is force air through the wind tunnel. You would basically measure the pressure forces at each and every point, right? And then what you would do is you would integrate the pressure forces, and you would get them in two components. One is going to be the lift and the drag. However, for trucks, lift doesn't matter, right? You would be looking at downforce, which is the opposite of lift. The other technique is computational fluid dynamics, where you can simulate the fluid flow and you can calculate the shear forces, the normal pressure, and then you can integrate the normal pressure and the shear forces on the entire object and compute the drag and the lift forces. Alright, I hope through this video you kind of understood why we care about aerodynamics so much, right? Remember that this is just one side of it. If you look at racing applications, the reason why people look at drag force is completely different, right? It's enhanced performance, but that's something that we don't care about in this particular course, so I have not mentioned it. But hey, if you're a fan of race car aerodynamics, I think that's a field of its own, and you should definitely check it out. Thank you so much, guys, and I'll see you in the next one. Bye. Hey guys, hope you're all doing good and welcome to a new video. In today's class, I'll be teaching you how to simulate flow over a cylinder. We will be looking at the entire pipeline from pre-processing all the way up to post-processing. And then once that has been covered, you would be all set to work on your project. Okay, so this is what we are going to primarily talk about. And then I have a few more topics in this particular slide. So let me first finish the demonstration and then come back to the PPT. Alright, so as you can see, I've already set up my project here. I started off with the fluid flow fluent, and then what I did is, for the geometry, I used the space plane geometry. So let me show you how that looks like. So this is how the geometry looks like, guys. So this right here is going to be our computational domain, and you can see that I have a rectangle here, another rectangle here, a circle here, and another circle here. So what's going on? So what you're looking at here is actually a two-dimensional case, right? So if you're basically taking a really long cylinder and if you're taking a slice of it, this is how it's going to look like. For example, let's just imagine a cylinder like this, okay? And let us say that you're trying to simulate how air flows over the cylinder, right? And what is essentially the drag force that's actually generated on this particular object, right? So now, if you assume that this cylinder is really long, right? If the cylinder is really long, then what I can do is I can just take a thin slice, right? Okay, I can take a thin slice of it. Essentially, I'm cutting the entire geometry, right, with using a plane. Now, if I do that, I will end up with a rectangle, right, which defines my computational domain. This is where air is going to flow, and in the place of a cylinder, I'll just have a cutout. Okay, and a flow would take place around it. This is the entire idea. Now if I switch back to space claim, you can see that that's exactly what I have. In addition to that, what I also have is I have another region, right? I have a couple of regions. I have one rectangular region and one circular region here. These have been created so that I can make the meshing easy. Now as far as this particular thing goes, right, you can see that this circle has a radius of 0.5 meter, right? So this is actually 1 meters in diameter. Now this geometry has been shared with you, so you can start loading this and get this up and running. Okay, so this is a 2D case, and now in order for you to be able to run a two-dimensional simulation in ANSYS Fluent, make sure that the plane that you choose is the XY plane, right? Only then it's going to take it and run it. So I have the geometry set up, so let me just close this. And let us take a look at how the computational mesh has been done. Alright, so in the ANSYS mesher interface, if I click on the mesh, you will hopefully start seeing why I created those rectangles in the circular regions. So the reason why I created the rectangular region is to have a tighter mesh density, right? So here you can see that outside the mesh size is a bit big, and then inside this rectangular region that we created, the mesh is slightly finer. And as we get closer to the cylinder, I'm making it more fine, and then I have an inflation mesh on top of my circle. So how did I do these? Well, I did them by adding 2 phase sizing and 1 inflation. So first what I did is I applied a phase sizing for this phase, right? So I used the phase selection tool to first click, and then that's basically my geometry, right? I selected that, and then I used an element size of 100 millimeters. Now if you click on the mesh, that has my global settings, which is 200 millimeters. So the mesh size that you see here, right, that's actually 200 millimeters, and in this rectangle the mesh size is 100 millimeters. And then I have another phase sizing which is applied to the circular region where the mesh size is 50 millimeters. And then what I did is I added an inflation layer, right, on this boundary. So you can see that this particular edge is red in color, right? So that's essentially the edge that I've selected here, and I was able to select edges using the edge selection tool. And if you look at the number of layers, it's 6 layers, and I use the total thickness option. So if I go back to the mesh again, you can see that I have this very nice layers of mesh, right? That's what you call as the inflation layer. And if I click on inflation again, the total thickness of that inflation layer is 75 millimeters. In other words, from if I just go here, I hope you can start seeing it, right? So this black bar that you see here, right, so that distance on the screen is 75, right? So you can see that for 75 mm I have this inflation layer, right? That's exactly what I have done there, and I'm said that there has to be 6 layers and the growth rate should be 1.2. Here 6 represents 1, 2, 3, 4, 5 and 6 layers, and you can see that each layer is subsequently bigger than the previous layer, and it's exactly 20% bigger than the previous layer. Okay, and we do that till the total layer size is 75 millimeter. And then as far as named selection goes, what I have done is I have an inlet boundary, right? I use the edge selection method to select this inlet, and I've created a named selection for it called as inlet, and I did the same thing for the outlet, and I did the same thing for edges as well. Okay, so that's how I was able to do it. Once I'm done with the mesh, the things that I need to look at are the statistics, right? So first I'm looking at the number of nodes that I have and the number of elements that I have. I have 5,000 elements, so this is fairly small. And then what I'm looking at here is the mesh quality. The way I'm doing that is, if I go to quality metrics, and then there's something called as mesh metric. So here I'm looking at element quality, right? Element quality is a fairly complex concept for a beginner level course. But essentially element quality controls 2 things. It controls the accuracy of the results that you get and the speed with which a solution can be obtained. So it's very important to look at the histogram of element quality to make sure that you have really low number of cells at a low quality. So you can see that the minimum quality is 0.29, that means 30%, which is fairly good, but that's not a surprise because the geometry is unbelievably simple. Right, if you're dealing with a realistic model, the element quality can go really low. So the ballpark recommendation for quality control with respect to complex geometry is 5%. So if the model quality is less than 5%, sometimes you might have to simplify the model to remove really small components that are not adding any value to the simulation, but they affect the quality of the simulation, right? So that is something that you would look at when you're dealing with really complex models. So that being said, we can actually move on to the next step, which is setting up the problem in ANSYS Fluent. So let me go ahead and open up ANSYS Fluent. And these are the options that I used. I used double precision and I used 4 processors. So you can see that my model is visible here along with the mesh. I have one inlet, one outlet. So now what I'm going to do is I'm going to go over the setup of the physics. So first I'm doing a transient simulation. In other words, I'm looking at how all the primitive variables like velocity, pressure, density change as a function of time. And I'm using a density based solver, right? Because I'm assuming that the flow is air. And what I have done is, if I go to material properties, I'm using the air material, which is the default material that's available in the database, right? So you should be able to get these properties for density and viscosity straight away. And then make sure that you click on viscous and make sure that the K epsilon turbulence model is enabled with the default constants. All right, so then let's click on OK. And then if I go to boundaries, for the inlet boundary, if I click on edit, what I have done is I've set up the inlet velocity to be 1 meter per second. Now remember the geometry, the diameter is 1 meter, the inlet velocity is 1 meter per second. Based upon these, I will be able to calculate the Reynolds number. In fact, that is something that you would be doing as part of your exercise. When you're setting up the simulation, you always first calculate the Reynolds number, because technically the Reynolds number dictates the choice of turbulence model that you would end up using. Alright, then once we have done this, what I ended up doing is there is actually a couple of things. There is a boundary called wall triple F surface. If you don't know what that is, if I click on display mesh, first I'm going to unselect everything and I'm just going to click on display. So now nothing is displayed. So if I select wall triple F surface, that shows me the top and bottom walls, right? So that is exactly what that name represents. So I'll select everything now, click on display, come back here. So for the top and bottom walls, what I've done is I've set up shear condition as specified shear, and I've set the shear stress to 0. So essentially this is in a way you are saying that there is no shear stress on these walls, which is kind of what we want, right? We don't want a boundary layer to be forming on the top and bottom walls, and that's why I've set it up like this. And if I just click OK, I can move on to the next step. Now in the geometry, you can see that I have a small circular mark right here. This is what you would call as a monitor point. So let's talk about how that has been set up. So if I go to solving, the first thing I need to do is I need to set up my step size and time steps. So you can use these default parameters for it. And then make sure that you press t equal to 0 and initialize the solution. I'm not going to do this because I've already run the simulation completely. Okay, so initialize the solution once, and what I want you to do is I want you to go to definitions first, and I want you to click on new, and I want you to click on force report, and I want you to click on drag, because that's what we are going to be looking at. Now for the drag, what you need to do is you need to give it a name, right? Use any name that you want, something like drag report or whatever you feel like. In my case, I already have this created, so I'm not going to do this again. But here's the thing, when you select the report, it's going to ask you the surface on which you want to create the drag report. Now the near cylinder region, right, that's essentially the cylindrical region on which I want to get the drag force. Now I'm going to be looking at drag force and not drag coefficient, because we have not discussed what drag coefficient is. So just click on drag force. So I'm just going to cancel this guy because I've already created that report. Okay, so let me cancel this and let me go to definitions and click on edit to show you the reports that I already have. So you can see that I have this report def 0, which basically calculates the drag coefficient in the wall near cylinder. Okay, it calculates the drag force. Okay, remember that. The other thing that I did is, I added the point. And how did I do that? I went to post processing, and what I did is in the surface option I created a point. So to create a point, what you have to do is you have to click on this point and you have to type the coordinates. So I created my point at 2.5 meters, right? So my origin is at the center of the cylinder, so I created a point 2.5 meters away. So just for an example, I'm going to do 5.0. okay, and I'm just going to call it as point number 10. Just click on create. So when you click on create, you will see that it doesn't appear on the screen, right? That's because you have to make it appear. So I'm going to go to setting up domain. I'm going to click on display, and here you can see that point number 10 is there. I also have another point number 11 because I actually accidentally clicked on create point 2 times. So if I display this as well, you can see that I have my second point as well. So this right here is my wake region. Okay, in the wake region I have 2 points, and what I was able to do with these 2 points is I was able to create the average velocity in those points. Essentially it is like putting a velocity sensor there to measure the fluid velocity. So how did I do that? Well, again, if you go to solving, if I go to definitions, I created new, and then what I did is I looked at a new surface report, and I was looking at something called as vertex average. So what vertex average does is it basically calculates the average of all the vertices in a given surface. So here when I click on that, you need to give a separate name for it. You should select your points. Now if I zoom in, you can see that your points occupy a particular cell, right? So when I select vertex average and when I select that particular point, Fluent is going to compute the average pressure in this case, but I can always change it to velocity or any other quantity that I want. And for example, let me just compute this for point number 10, right? And I can say that, hey, I want this plot to be reported. Okay, I want this plot to be reported, and you can just click on OK. All right. Then all you need to do is hit calculate, and the simulation is going to run, and you will be seeing a bunch of output, right? You will be looking at the drag force, you'll be looking at the velocity in the monitor points. But before I do that, I want to show you how the solution looks like for this particular case. So since I've already run the simulation, let me close this guy and let me open up the solutions. So here you can see that the upstream data of the cell has changed. Do you want to refresh this cell? I'm going to say no because I'm interested in showing my previous solutions. So now if I go to post-processing, I can click on solution playback. Now again, you will not have this information because you have not run the simulation yet, I hope. So now if I click on this play button, you will actually see the velocity animation. You can see that initially it's taking some time for the velocity to settle down. But then what's happening is after some time you will see that vortices start to shed, right? You can see that you start getting these oscillations, and this is what you call as vortex shedding, right? It's a common phenomenon that's observed in flow over a cylinder whenever the Reynolds number is fairly high. So this is how the animation looks like. Now let's actually close this guy. Now that I've shown you the results, let me close this guy, click OK, and what I'm going to do is I'm going to go back to ANSYS Fluent interface, and we are going to reinitialize the solution, and we are going to be looking at how the data in the monitor point looks like, how the residual looks like, and how the drag force looks like. Okay, so now if I go back to post-processing, you can see that a lot of things are have been disabled, and that's why I said that it's important to initialize the solution first. So let me click on initialize, and this is going to reset everything, right? So the animation object will be reset, which I'm perfectly fine with. Okay, so now that I have done this, if I go to post-processing, now you can see that everything appears. So now what I can do is I can click on contours, and I can create a new contour, right? And I'm just going to call this as pressure contour. Okay, and I'm just going to be looking at the pressure values, okay, in all these regions. All right, and if I click on save/display, it's going to show me the pressure values. Right, and here you can see that it is set to global range, and here you can basically see that it is set to global range. I'm going to set it to auto range. Now in case of velocity, what I did was I set it to global range, and I specified the min value for velocity and max value for velocity. Okay, that is something that you need to remember. So let me close this guy, and what I can do then is I can go back to solving, and I can look at my definitions, and I can just see if there is any other definition that needs to be added. Okay, so velocity at point is there. The pressure animation that we showed, that we created, is not showing up. So now what I'm going to do is I'm going to click on create, click on solution animations, and here you can see that pressure contour is being shown. This is titled as animation number 2, and I'm just going to click on OK. So that way this is also going to appear. So now if I hit on calculate, the solution is going to start, and you can see that I'm kind of getting multiple plots, right? So these are all the data that I requested for. So let's look at the residuals. The residuals teach us how well each and every equation is being solved, and you need to kind of wait till the residuals drop. But that's not the only thing that you look at. You look at other things as well. Here you can see that the lift force is changing, but the lift force has not reached a particular value, right? So you know that the simulation is not complete. And that is why it's very important for you to run the simulation long enough to kind of see some type of steady state behavior in the solution. So we are just going to let this go. If I look at the other points, so here you can see that the velocity at the point is being shown here, and this is the velocity at a different point, right? You can see that I have area weighted average in one and vertex average in one. If for a monitor point, it should really not matter, right? Because you're getting data from a single point. So the vertex average and area weighted average should be very close to each other. Then I have contours of velocity magnitude, and here you can see that for each and every time step it's getting updated. We don't have the animation yet. And similarly for contours of static pressure, okay, looks like that's not being displayed because again the range is currently just 0 to 0, right? So it's not being displayed. Okay, so this is how I would set up the entire problem, guys. I'm just going to let this run till 500 iterations, but I think I'll stop the video before that because treat this as a project. The reason why kind of did not give you a complete walkthrough is at this point, you know, I want you to kind of think about the steps, right? So we first had our operating conditions, right, which is our velocity, and based on that I can calculate my Reynolds number. And then using ANSYS workbench, once the geometry is done, set up the computational mesh using the mesh parameters that I already showed. Generate the mesh, look at the mesh quality, and then in ANSYS Fluent, all you need to do is work your way from left to right, right? Setting up the domain, setting up the physics, solving, post-processing, and that's it. I want you to do this, and I'm kind of giving you less pointers here because I want you to encourage yourself to kind of explore the tool. From the physics aspect, I think I've already given out a lot of information. Now here's the thing, I'm fairly sure that a lot of you will get stuck in this exercise, and if you do get stuck, it's perfectly fine. Reach out to us for help and we will be happy to guide you guys. Okay, so now let me jump back to the presentation. Now simulating flow over a 2D car, so that's another project that you will be working on, and for that project you will be given no guidance. The only thing that you will be given is the geometry, everything from scaling the geometry to applying the right boundary condition. You are going to be making the choices for it, right? But you will have to kind of show me your calculations when you submit your assignment, because your grades will be given based on that. So couple of points to ponder, right? See, if we have a car, if we have the same car that is made at two different scales, right? So imagine your favorite car, okay? Now take that regular car, and now imagine that we can make the same car 1.5 times bigger. And say that I'm asking you a question, hey, which is more aerodynamic? What would your answer be? Now I've seen that some people pick a choice. You know, they either say that, hey, the regular car is more aerodynamic, and some people say that, you know what, the bigger car is going to have more resistance and hence that's more aerodynamic. Well, now if you have finished the course, then you might basically tell me that, hey, you know what, I will basically go and look at the object that has the least drag force. Now obviously the larger the body, the more force it's going to experience, right? But does that actually make sense? No, it does not. If you have the same shape, technically, even though the aerodynamic forces are different, from a qualitative aerodynamics point of view, these two objects are similarly efficient when it comes to moving air around it, right? Because they have the same shape. In other words, it's kind of like this. For example, if you're a student in India, in your college, you know, they might have a percentage-based system, which means you might have scored 80%, which is 80 out of 100. Now, I might come from another college where I have a CGPA system where I have scored 4 out of 5. If I just look at the numerators, right, you have scored 80 and I've scored 4. And if you tell that, you know, 4 is less than 80, that doesn't make any sense, right? In other words, you always try to normalize it. 4 divided by 5 is also 80% in a way, right? In other words, these students more or less are same academically, right? Similarly, aerodynamically speaking, you need a basis, or you need a number which you have to divide the drag force by, so that you can compare drag coefficients across different shapes. And it really doesn't matter how big or how small that shape is. And that's essentially what you would call as the total pressure. Okay, so the total pressure, half times rho times AV square. What is A? A is called as the frontal area, meaning if you're looking at, say, a car from the front view, right? That is basically the area that you would use there, and V is the velocity, the inlet velocity. Now, I made a small mistake here. This drag coefficient is going to be drag force divided by the total pressure. In other words, instead of 1, it should be drag force. Let me actually take a quick second to modify the formula. Alright, there we go. That looks much better. So drag coefficient CD is equal to FD, which is the drag force that, a tool like ANSYS Fluent would give us. Divide that by half times rho times AV square. Rho would be the density of air that's coming through the inlet, and V would be the velocity at the inlet, and A is just a frontal area. If you do this, you will get the drag coefficient. The smaller the drag coefficient, the better the body is from an aerodynamic standpoint. Alright, with that guys, the short course comes to a conclusion, right? So here's the key summary of whatever we did in this course. We looked at the basics of fluid mechanics. We identified that drag force and lift force are what people look at. Identified two important forces that aerodynamists care about, pressure force and the shear force. And in order to calculate pressure and shear forces, you can either use experiments or you can use CFD. CFD is cheaper and it's fast, and we looked at one sample problem using ANSYS Fluent and we were able to determine drag force. And then finally, by using the drag coefficient formula, we can actually just with a single number explain if a car's shape is aerodynamic or not. As simple as that. Now, it doesn't matter how many cars you try to design, you can always look at the CD value for the same operating condition and determine which shape is the best. Okay, now remember, this is a basic course, and whatever you have learned so far will help you get into aerodynamics, right? And you will be able to run 1 or 2 simulations, and you will be able to approach those problems in a logical way. This is by no means a representation of what goes on automotive companies, right? So that's something you need to keep in mind, right? And that kind of leads me to my next point. So what is it that they look at? Well, in companies, they actually use CFD as a tool to basically create better designs. So the focus is more on understanding the physics of the flow, right, with respect to the geometry. And usually that's the type of information that doesn't get out of the industry. It's typically the IP of the industry, right? It's the intellectual property of that particular company. And the thing, they look at better mathematical models that can make their simulations more accurate. They try to come up with correlations, right? So in other words, you run enough simulations, you kind of will be able to say that, hey, if I change this particular design parameter, my aerodynamic forces goes up or below, right? And then they develop correlations with it to understand how the various aspects of geometries affects the aerodynamic behavior of the object that they care about. Okay, alright guys. Now in addition to passenger cars or electric vehicles, aerodynamics is used in plenty other applications, right? For example, aircrafts and fighter jets. So there things are looked at a much more higher level. The thing that we have not touched upon is high speed flows where Mach numbers are greater than 1, right? In those cases, additional physics needs to be captured. And if you crank up the Mach number very high, and if you're looking at hypersonic zones, then you actually need to be able to understand energy equation very well, because now there's going to be way more heat that gets generated, and you also need to model chemical reactions that take place at such high levels of speed, right? So essentially what I'm trying to say is that aerodynamics is a vast field, and through this course we are just looking into the entire ocean of aerodynamics, but you're looking at just one aspect of it, which is passenger car aerodynamics, and that too at a base level, right? So if you want to grow in this area, it's a fascinating field. There's so much to learn. So yeah, good luck, and I hope you enjoyed the course. Thank you so much. Bye.